Welcome to this algorithm analysis deep dive course taught by Dr. Hao. He's an experienced professor of computer science. This course will help you truly understand how and why algorithms perform the way they do. You'll explore the mathematical foundations and analytical techniques that underpin asymptotic complexity, divide and conquer strategies, randomized and probabilistic analysis, and amortized analysis. Unlike typical DSA courses, this course focuses on building your intuition and connecting abstract math to real code. The course features detailed walkthroughs, code examples, visual explanations, and hands-on exercises. And by the end, you'll not only know how to analyze algorithms, you'll also understand the reasoning behind every step.
Hi, I'm Dr. Hao, a computer science professor, and I would like to welcome you to this full-length course on algorithm analysis. In this chapter, I'll give you a quick overview of what this course covers, who this course is for, and how to get the most out of it. This course is designed to help you truly understand how to analyze the performance of algorithms and data structures, not just memorize time complexities. We focus on foundational tools like asymptotic notation, the recurrence tree method, the master theorem, and probabilistic and amortized analyses. And we use real data structure examples to ground the theories. By the end, you'll be confident in analyzing time complexities with tools like recurrence tree and the master theorem, understanding different analysis models like worst and average cases, and applying the learned techniques to analyze algorithms and data structures like heaps, hashtables, and binary search trees. This course is ideal if you are self-taught and want to fill in your algorithm analysis gaps, or if you have finished a bootcamp or taken an algorithm class that felt too abstract, or you are preparing for technical interviews and want to move beyond brute force memorization. All you need is basic familiarity with programming, arrays, and recursion. If you are ready to move beyond surface-level DSA and develop a deep understanding of how algorithms behave and their performance, this course is for you. The course is about 6 hours long, divided into clear chapters, each with quizzes, problems, and labs. You can go straight through or jump to what you need. You can find all the quizzes, problems, and the labs corresponding to each chapter in this GitHub repo listed here on the screen. If everything sounds good so far, let's get started and happy learning. This lecture aims to introduce you to the topic of time complexity. Here is the roadmap of what we will cover. In this lecture, we will introduce you to the concept of time complexity and provide a definition for different terms such as algorithm, random access machine model, and time complexity. So why do we need to study time complexity? Or say, why does it matter? Think about how many searches you would do via Google on a daily basis. Every query could potentially lead to hundreds of thousands of results, and they all need to be ranked by relevance. Ordering so many results for one search is expensive. By saying that, I mean it takes time and computational resources to do this task accordingly, even for one search. Now think about how many searches are handled by Google on a daily basis, given the large number of users. The same thing can be said for any other computational tasks. As a result, we always seek more efficient algorithms that take less resources and less time to get things done. How do we measure the efficiency of an algorithm? That's what time complexity does, and why we need to learn a bit about it. Before we introduce you to the formal definition of time complexity, let's start with a simple question. How do we measure the efficiency of code? To be specific, we can ask this question in a different way. How do we measure the speed of a given function or method? To answer this question, you can think of a few options. For example, you may think like this. Can we use the actual time it takes to run the function or methods? If you do so,
the measurement may not be exactly fair, depending on where you are running the code. If you aim to compare the efficiency of two algorithms A and B, but you have A run on a personal laptop and B on a cluster of supercomputers, the actual time it takes to run those two algorithms may not fairly reflect which one is faster, because the setup is already skewed. That said, the actual time it takes to run the function or methods may not be a great measurement of the efficiency of the code. Then you may be thinking, how about the steps it takes to execute the function or method? Well, let's use an example to figure that out. Here on the screen, you can find the algorithm that searches for the max value given a linear data structure, like an array. It uses a variable named result to contain what's eventually returned. It starts by picking up the first element in the array, and then traverses through the whole array and compare to see if there's a bigger element. If there is, then we put that element's value inside the result variable. In the end, the result is returned. If the input array size is 1, roughly 4 steps are executed. Assigning the first element to the result variable, the if condition in the for loop, as well as the statement underneath the if condition. Lastly, the returning statement, of course. So because we are only doing an estimate, so we won't bother figuring out which line of code actually gets executed or not underneath the for loops. Let's just roughly estimate that, so we can count that as 1, 2, 3, 4, 4 steps being executed. When you have an array with 3 elements, it will take about 8 steps to execute the function. The for loop runs for the same number of times as the input size, which is 3, but there are 2 steps underneath it, assuming that both would get executed, so you would have 3 multiplied by 2, which gives you 6 steps. Don't forget that there is the initial step that assigning the value to the result variable, as well as the last step to return the result. So you need to plus 1 and another 1. That will give you 8 steps in total. Again, that's a rough estimate. We won't bother to figure out which line underneath the for loop really gets executed. Similarly, when you have an array with n elements, it will take 1 plus 2 multiplied by n plus 1 steps to execute the function. As you can see, different input size will lead to different numbers of steps to be executed. Which one of these is really representative of the speed of the function? If you account for the varied input size and ask yourself this updated question, how about the steps it takes to execute the function or method in relation to the input size? It will become a better measurement of the function speed. Let's use the same example we saw earlier to make sense of it. Well, the same function, find max, that searches for the max value given a linear data structure. To account for the varied input sizes, we will use Tn as a function to stand for the speed of the function, where n is the size of the input. It can be any positive integer, say 100 or 2000. Regardless of the size of the input, we know that the first line of this function will always be executed. I mean, the assignment of the first element to the result variable will always be executed. That's one step. If we just want an estimate, we can assume that both the if condition and the statement underneath the condition will be executed, which makes 2 steps. The for loop runs for n times, same as the input size. In the end, the return statement is always executed. So that will give us 2 multiplied by n plus 2 steps in total. In summary, the way that we measure time complexity of a given function or method depends on the input size, and is typically expressed as a function in relation to the input size, which is a better measurement than just the actual time it takes to run the code, and also better than the steps it takes to execute a function, because it fails to account for the varied input sizes. That said, This is everything about an informal introduction to what time complexity is. Now let's introduce you to the formal definition of time complexity. Before we do that, we need to start by defining what algorithm is first. So what's algorithm? An algorithm is defined as a finite procedure that takes an input and produces an output. It's an effective method to solve problems, typically. An example of algorithm can be the findMax function that we examined before. It's a finite procedure that takes a linear data structure like arrays as the input and produces the identified max value as the output. So formally speaking, we will use random access machine model to analyze the efficiency of algorithms. The random access machine model, short for RAM model, is a theoretical model of computation, and it assumes a simplified, idealized version of computer system that processes instructions sequentially. The RAM model has a few key features, or say assumptions, that will be very important when it comes to analyzing the time complexity of a given algorithm, such as the computer has infinite amount of memory. Each access to memory location, or say read and write, takes constant time. This is actually on the input or say the output operations. Basic arithmetic operations like plus minus, logical operators like and or, comparisons like bigger than or smaller than take constant time. Executing a single instruction such as assignment, branching, or looping takes constant time. The time complexity of an algorithm is determined by counting the number of basic operations it performs. Of course, this is based on the assumption that input size has already been accounted for. So based on such assumptions, let's try to analyze the time complexity of a given algorithm example. Again, we will stick to something similar to the findMax we saw earlier. Well, it's still findMax. So what you can see on the screen is the pseudocode of the findMax, along with the line numbers at the right side. The input is still an array. The first step assigns the first element to the variable y, which is the first line. The second line starts the for loop. Under the for loop, you have two steps, an if condition and its statement, corresponding to lines 3 and 4. The if condition checks the value of y against every other element in the input array as you traverse it. If the current element is bigger than y, then you will assign its value to y. In the end, you return y, which is step 5. From the RAM model, we learned that the steps such as assigning a value to a variable, or returning a value, or comparison all take constant time. To simplify things, we are going to mark all those things as taking a single step to execute. So line 1 and line 5 both take one step. The for loop runs for n steps, which is the size of the input array. Under the for loop, the two lines, the if condition and its statement, take 2 steps, depending on if the if condition is being met. As you can see, the different input may lead to algorithm taking different number of steps to execute. So what characteristic should the input array have for the algorithm to take the least number of steps or the most number of steps to get executed? If you try a few examples, you will see that the key difference lies in whether both steps 3 and 4 are both executed or only step 3 gets executed. The best scenario, or say the best case, is when only step 3 is executed. That literally saves us one step underneath the for loop, because the for loop runs for n times, which is the size of the input array. That could potentially save us n steps in total. Okay, so the best case only happens when the input array is in descending order. In that case, the if condition will never be met, because A is initially assigned of the value of the first element in the array, That's the biggest element in the array. So the if condition would never be met, and the statement underneath the if condition would never get a chance to get executed. The worst case is when both steps 3 and 4 are always executed, and that only happens when the input array is in ascending order. In that case, the if condition is always met because A is initially assigned as the smallest element in the array. As you traverse the whole array, every new element you encounter will be bigger than the current value of A. So both the if condition and the statement underneath the condition would be executed. Okay? So from our informal introduction of time complexity, we know that the time complexity Tn is expressed as a function in relation to the input size n. This is the same when RAM model is applied. So you can compute the Tn for both the best case and the worst case accordingly. For the best case, because only step 3 is executed, you can calculate the Tn as n plus 2. Where does the 2 come from? 2 comes from the initial assignment of the first element to the variable y, and the returning of the y variable in the end. So for the worst case, the only thing that would change is that you need to multiply n by 2, because both steps 3 and 4 are getting executed in every iteration of the for loop. Beyond the best and worst cases, you can estimate an average case that sits in between. If you plot the best and the worst cases in a 2D plane, the average case will sit somewhere in between. You may notice that we have simplified our estimate of time complexity by assuming that each step takes just one step, except for the loop. That's not exactly what the RAM model says. The RAM model says that the simple operations such as assigning a value to a variable or returning something, all these basic operations take constant time. Okay, constant time. That's why you're likely to see a different set of notations like C1, C2, or C3 in a lot of textbooks. C is short for constant, and they all stand for constant times. If you stick to the same notations and strictly follow the RAM model, it will express the time complexity for the best and worst case differently, basically replacing all those ones with constant time symbols like C1 or C2. Okay, for the best case, Tn will be expressed as C1 plus n multiplied by C4 plus C5. So here C1, C4, and C5, they all correspond to the line 1, 4, and 5, and they stand for constant numbers. Similarly, for the worst case, Tn will be expressed as C1 plus n multiplied by C3 plus C4. In the end, we would plus C5. You may think that, well, here all these C1, C4, C5, they are just some constant numbers. Maybe we can somehow simplify them. For example, in the best case, you have C1 plus C5. Could we replace that with just a single symbol instead of 2? Yes, you can. Actually, it's very common to replace multiple constant number symbols with a single symbol, like using D to replace C4 plus C5 in the best case, or using C subtext B to replace C3 and C4 in the worst case. Okay, so both C subtext A, C subtext B, or D, they all stand for constant numbers. So using single symbols to represent constant numbers make it easier for us to see the nature of the time complexity functions. In our case, both the functions in the best case and the worst case are just linear functions. So far, we keep using the phrases like best case or worst case, but we have never really defined them formally yet. Well, to summarize from this example, the best case is when you have some input that leads to an algorithm to take the minimum number of steps to run. Okay? The worst case is when you have some input that leads to the algorithm to take the maximum number of steps to run. It's rare for the best case or worst case to happen, given a random input. So that's what average case comes into play. The average case is the estimate of the algorithm to run given arbitrary input. It's typically sitting between the best and the worst cases. Now you have a basic understanding of time complexity. The next step is to make sense of all these via a concrete example. This lecture continues the introduction to the topic of time complexity. Here's the roadmap of what we will cover. In this lecture, we will use an algorithm example, the insertion sort, to deepen your understanding of the different terms and operations of time complexity. In case you never learned how insertion sort works in the past, or if you have learned it somewhere but your memory blurred, we will go over how the algorithm works first. On the screen, you can see the pseudocode of insertion sort algorithm. The line numbers are on the right side of each line, either in red or blue. The blue line is a comment. So first thing first, insertion sort takes a linear data structure like an array as the input, and performs the sorting directly on the given array. In other words, insertion sort performs sorting in place, as no new array is being created. So how does insertion sort work exactly? Before we dive into the code, let's try to gain a basic understanding of the concept of insertion sort first. The big idea of insertion sort is about using a moving wall to separate the given array into two parts, which sits on the left side and the right side of the wall. The left side is the sorted part, and what sits on the right side of the wall is the unsorted part. By sorted part, I mean all the elements in this part are sorted. Let's assume that our goal is to sort the given array in ascending order. So as is shown from the example on the screen, the sorted part has 5 and 7, and they are in the right order. That's everything about the wall. To sort every element, you need to move the wall from left to the right. So how do you do that? You will gradually move the wall from left to right until every element is in the sorted part, or say until the wall is at the right end of the array. At each step of the moving, you will focus your attention on a single element that neighbors the wall, but in the unsorted part. In our example, that's number 3. Our goal is to incorporate 3 into the sorted part. After that, you can move the wall towards the right side by 1 step. To achieve that, we need to place 3 into the right position in the sorted part by comparing 3 to the elements in the sorted part. The key is how you do the comparison. You will start from the element that neighbors the wall and gradually move towards the left side. So you will start by comparing 7 to 3 first. If 3 is bigger than 7, then that's great. You don't need to do anything. Just move the wall 1 step towards the right. If 3 is smaller than 7, then keep up your comparison until you find an element that's smaller than or equal to 3, or until you are at the left end of the array. In our case, you will keep comparing 5 to 3, and 3 is still smaller than 5. But we can't move towards the left anymore because we are already at the left end, so we stop. However, we have identified the right position for 3. It should be at index 0 prior to both 5 and 7. It should be on the left side of both 5 and 7. So we would move 7 1 step rightward, and then move 5 1 step rightward. In the end, we will move 3 to sit at the left side of 5, which is index 0. That's what happens at every step of the insertion sort, and that's how you move the wall step by step towards the right. So let's use this array on the screen as an example and apply insertion sort to it to demonstrate the full process of insertion sort. You will start with the wall separating the sorted and unsorted parts. That is the very left side. To be precise, that's when the sorted part only contains one element. To move the wall rightward, you need to focus on the element neighbors the wall in the unsorted part, which is 7. You need to compare the elements in the sorted part to 7, and you will do that from right to left, one element after another. Luckily, there is only 5 in the sorted part, and it's smaller than 7. So they, 5 and 7, are already in the ascending order, the right order. Then all you need to do is to move the wall rightward. Next, your focus will become 3, the element in the unsorted part that neighbors the wall. You will compare 3 to the elements in the sorted part, from right to the left. As long as an element in the sorted part is bigger than 3, you will move that element one step rightward. So for 7, it will move one step rightward. For 5, it will move one step rightward. You may worry that moving such elements rightward will overwrite 3. Don't worry. We will save 3 to a variable named key beforehand, so we won't lose access to its value. So in the end, you will either encounter an element that's smaller than or equal to 3, or you will be at the very left side of the array. In that case, you will put 3, the value that you stored in the key variable, to where you stopped. So now the wall has moved to between 7 and 2. Your focus is 2 now, the element that neighbors the wall and is in the unsorted part. You will save 2 to the key variable first. You will compare the elements in the sorted part to 2, starting from 7, then gradually move towards left. As you do the comparison, as long as an element in the sorted part is bigger than the key, you will move it one step rightward. That applies to all the elements in the sorted part. So for 7, it's definitely bigger than 2. We will move it one step rightward. Then we go to 5. It's still bigger than 2, so we move it one step rightward. Then we go to 3. 3 is still bigger than 2, so we move it one step rightward. In the end, you are at the left end of the array, so you can place the key's value 2 into the position of index 0. Now we have merged the 2 successfully into the sorted part. We can move the wall one step rightward. Now, your focus becomes 1, the element that neighbors the wall in the unsorted part. We will store 1 to the key variable first. After that, you will compare elements in the sorted part to 1, starting from 7, and then gradually move from right to left. 7 is bigger than 1, so we move it one step rightward. Then we go to 5. 5 is bigger than 1, so we move it one step rightward. Then we go to 3. 3 is still bigger than 1, so we move it one step rightward. Then we go to 2. 2 is still bigger than 1, so we move it one step rightward. Now you are at the very left side of the array and out of elements in the sorted part. So you can put the key's value, which is 1, into the position of index 0. Now you are at the very left side of the array and out of elements in the sorted part. So you can put the key's value to the position at index 0 and move the wall one step rightward. Now the wall is at the position between 7 and 10. Now your focus becomes 10, the last element in the whole array. You will start by storing its value to the key variable first, and then compare elements in the sorted part to 10. You will start from 7. Since 7 is smaller than 10, the comparison will stop here. Why? All elements in the sorted part are already in the ascending order that you want. And 7 is the last element in the sorted part, as well as the biggest. As long as 10 is bigger than 7, it's going to be bigger than every other element in the sorted part. That's why there's no need to do any further comparisons. You can simply move the wall rightward by one step. Since every element of the array is in the sorted part now, your job of sorting is done. To map the operations we covered to code, you will have this. Okay? There are two loops, the outside for loop and the inside while loop. The outside for loop traverses from left to right. This loop is about moving the wall. The key variable is always used to store the element that neighbors the wall in the unsorted part. Okay, the element in focus. Why does the outside for loop start from index 1 instead of 0, you may wonder? Because the sorted part starts with a single element at index 0, and the unsorted part starts with the element at index 1. Okay? The outside for loop moves the wall rightward by focusing on every element in the unsorted part that neighbors the wall, and it starts with the element at index 1. As you can see, underneath the outside for loop, the first thing you do is to store the value of the element in focus into the key variable. Okay, that's the job of the line 2. Next, this inside while loop only gets triggered when you have some elements in the sorted parts that are bigger than the key. Okay, that's specified by the two conditions of the inside while loop. If the key is bigger than the largest element in the sorted part, the while loop won't get triggered at all. What happens underneath the inside while loop? Once you have an element in the sorted part that's bigger than the key, it will move it one step rightward. That's what line 6 does. Line 7 simply helps decrement the counter j so that you can traverse from right to left to check the next element in the sorted part. In the end, it will place the key's value into its right position, either at index 0 or at the right side of the first element that's smaller than the key. That's what line 8 does. The index of the right position is j plus 1, because the last iteration of the while loop decrements j too much, one step further than where it should land, as the example you see on the screen. When the inside while loop finishes itself, the value of j will be negative 1. That's why you need to add 1 to j in the end to get the position of the key. Okay? It's everything about how insertion sort works. Based on the pseudocode, here's the time complexity function for the insertion sort. Well, that's a mouthful. All the symbols C1, C2, and all the way to C8, they stand for constant time, and the digits correspond to line numbers. With all the symbols, I know it's hard to figure out what it is, or even how we get here. Let me simplify things for you a bit. By hiding the inside while loop first, we will also hide its corresponding time complexity. For the remaining lines, the time complexity will be relatively easy to figure out. The first line runs for C1 multiplied by n time, where n is the input array size. Although the for loop starts at index 1, it still needs to go from index 0 first to get to the position of index 1. So it takes literally n steps, and each step takes a constant time C1. That's how you get C1 multiplied by n. Okay? The second line takes C2 multiplied by n minus 1 time. Considering that the for loop only runs for n minus 1 times, in each iteration of the for loop, line 2 takes a constant time C2 to get executed. A similar thing can be said for line 4 and 8. If you want a rough time estimate of the lines without the inside while loop, it's just a linear function that can be summarized as c multiplied by n plus d, where both c, d are constant numbers. So now let's bring back the inside while loop that we skipped. If you focus your attention on line 5, the corresponding time it takes to run is expressed as c5 multiplied by the sum of a series of t subtext j, where j starts at 2 and ends at n. Each t here represents the amount of time it takes to execute just the while loop line. I'm talking about line 5. Okay, so how many times the while loop is triggered, or say how much line 5 contributes to the time complexity function, really depends on the characteristics of the input array. And the problem is very difficult to figure out directly when the input array doesn't have a clear pattern. Sometimes the while loop gets triggered for 1 time, sometimes 10 times. We don't really know the frequency without knowing the pattern. As you learned from the part 1 lecture, we care about figuring out the time complexity functions for the worst case and the best case given an algorithm, because they make a clear boundary for the time complexity, as well as help us derive a time estimate for the average case. So instead of dealing with this uncertainty of the while loop directly, we can focus on the worst and the best cases. We will start with the worst case scenario. Think about what characteristics of the input array will lead to the code to take the max number of steps to run. Based on what we know about the algorithm, we know that sometimes you only need to compare one element in the sorted part to the key, and you don't need to run the while loop at all. That happens when the key is bigger than the largest element in the sorted part. Okay? Sometimes you need to compare every single element in the sorted part to the key and trigger the while loop to run forever. That happens when the key is smaller than every element in the sorted part. Okay? When the outside for loop iterates through the elements of the given input array, if every key is smaller than everything in the sorted part, we will be forced to compare every element in the sorted part to the key, or say, we will be forced to run the while loop to the maximum extent. That's the worst case. And the worst case only happens when the input array is in a perfect descending order, like this array that you see on the screen. So let's use this array as an example to figure out the time complexity of the worst case. The wall will start between 9 and 7. As the wall moves, the key keeps changing starting from 7. When an element in the sorted part is compared to the key and found out bigger, it involves the comparison first, then moving the element one step rightward, as well as decrement the counter j. So let's assume all those tasks, they take constant time to do. Okay? Starting from 7, it will take c multiplied by 1 time, because you need to do exactly one comparison and all those tasks. Then for 6, it will take c multiplied by 2 times, because you need to do 2 comparisons and double amount of those tasks. It will go on and on. If the input array size is n, it will take c multiplied by n minus 1 time for the last element in the array. Okay? The time complexity function will be the sum of all these items, like this. We can extract the c from all these different items, and the Tn can be expressed as c multiplied by the sum of 1 plus 2 plus 3 all the way to n minus 1. The sum from 1 to 2 to 3 to n minus 1 is roughly equal to n squared divided by 2. You can approach adding things up by adding the head to the tail. 1 and n minus 1. The next head to the next tail. 2 and n minus 2. It goes on and on until you reach the middle point. Each pair will add up to n, and there would be roughly n divided by 2 of such pairs. We multiply these two numbers, it will make the time complexity function a polynomial function, and the highest order, or say the highest exponent, will be 2. Okay? That makes the worst case for the insertion sort. What about the best case? We already know that in the best case, as we move the wall rightward, the wall that separates the sorted and unsorted parts, the key will always be bigger than every element in the sorted part. In that case, the comparison between the largest element in the sorted part and the key involves merely a single comparison and nothing more than that. In other words, the while loop doesn't run at all. A concrete example would be like this. We will start with a while separating 1 and 3. 3 will be the first key. As 3 is bigger than 1, you simply move the while rightward. Then 4 will become the key. Because 4 is bigger than 3, the biggest element in the sorted part, no further comparisons are needed. So you move the while rightward. And it goes on and on like this until the while is at the right end of the array. As you can see, this example of input array is in perfect ascending order. That's when you get the best case, and that's when the inside while loop doesn't get triggered at all. Without the inside while loop, the outside for loop takes c multiplied by n time to run, where c is a constant number. When you plot the time complexity function of the best and worst cases on the same 2D plane, you will have two clear boundaries and the area where the average case falls into. As one of the naive ways to estimate the average case, you can replace n with n divided by 2 in the worst case time complexity function, which will also give you the polynomial function where the highest order is 2. Okay? In this lecture, we used an algorithm example, the insertion sort, to go over how time complexity analysis is conducted on a given algorithm. Hope you learned something new. This lecture covers asymptotic analysis. Here's the roadmap of what we will cover. We will start by comparing asymptotic analysis to upper, lower, and average case analysis as two different dimensions of time complexity analysis. After that, we will cover the growth of functions, which is the foundation of asymptotic analysis. In the end, we will explore how asymptotic analysis is conducted on algorithms and summarize what we learned. We covered the worst, best, and average case analysis. This is one dimension of time complexity analysis. If you think about the time complexity analysis as an umbrella term, then the worst, best, average case analysis is one of those things that you do under this umbrella. From what we learned, we know that such analysis depends on the characteristics of the input. In contrast, the focus of this lecture, asymptotic analysis, is a different dimension of time complexity analysis. It is about describing theoretical guarantees of the performance of an algorithm, and it doesn't really care about the characteristics of the input. At its core, asymptotic analysis is about mirroring how algorithms perform as the input size keeps growing. Asymptotic analysis allows us to use asymptotic notations to simplify the time complexity functions of a given algorithm and make it easier to compare the relative performance between different algorithms. So you may wonder what are asymptotic notations and how the simplification works, and how the two dimensions, the worst, average, best case analysis and asymptotic analysis, are related. We will answer these questions one after another as we move forward. So let's dive into the growth of functions next. Growth of functions is the foundation of asymptotic analysis. Before we get into the details, here's a taste of what we will try to cover and define on this topic. We will try to define the upper and lower bound of a given time complexity function. These can help us simplify the efficiency of that time complexity function as the input size grows. We will map them to the symbols, as you can see on the screen. The upper bound will be denoted using big O and the lower bound using omega. Sometimes a time complexity function happens to have the same upper and lower bound. In that case, it will be denoted using theta. So let's introduce the formal definitions of the upper, lower, and tight bound one after another, starting with the upper bound. So here is the formal definition of the upper bound. The definition is written using a lot of math symbols. Let me help you decipher them in case a symbol is foreign to you. So all the symbols that might be foreign to you have been circled out, and their corresponding meanings are all made explicit. For example, the symbol like a reversed E says there exists something. The symbol like a V with a horizontal bar crossing in the middle says for any. Remember, this is the definition for the upper bound given a time complexity function. So this definition essentially says that given a time complexity function fn and another function gn will be the upper bound of fn if there exists two constant numbers to sustain a relationship between fn and gn. So what are those two constant numbers? First, you need a number c. Of course, c needs to be bigger than 0. Second, you need a specific input size n0. Yeah, as you can imagine, because n0 represents a specific input size, it has to be bigger than 0. So what's the relationship between fn and the gn? As the input size grows and it becomes bigger than n0, fn will always be smaller than or equal to c multiplied by gn. If this relationship holds, we will say that gn is the upper bound of fn. And this relationship will be expressed using big O notation, essentially by writing big O, then followed by a bracket that wraps up gn. Okay, so this relationship is visualized in the graph that sits underneath the definition. The x-axis is the input size n. The y-axis represents the time. As input size n grows and it becomes bigger than n0, c multiplied by gn will always be bigger than or equal to fn. When n is small, there might be some fluctuations, and it's possible that fn is, well, sometimes bigger than c multiplied by gn. However, that doesn't really matter. All we care is when n grows towards infinitely large, what would the relationship between fn and c multiplied by gn be? Okay, if fn is always smaller than or equal to c multiplied by gn, then we'll see that gn is the upper bound of fn. So let's look at a few examples to help you make sense of this definition. Okay, as you can see on the right side of the screen, there's a question. Given fn, this is a time complexity function. Given fn as 2 multiplied by n plus 2 and gn as n squared, can we see that gn is the upper bound of fn based on the definition? Okay, if we just plot these two functions on a 2D plane, they will look like this. Remember, n represents the input size, and it is the x-axis, and the time is the y-axis. Since negative n or negative time doesn't make sense, so all we need to focus on is this area, when both n and the time are positive. As you can see, as n grows, eventually gn will be bigger than fn, because gn is a square function which grows much faster than linear ones. At about 3, gn will be equal to fn. That's where they cross with each other. After that, gn will say bye-bye to fn because it grows much faster. Okay, is gn the upper bound of fn? To answer this question, we need to figure out if the relationship between fn and gn meets what's required by the definition. Are there some constant numbers, like c, or specific input size n0, to make c multiplied by gn always bigger than or equal to fn? So based on what we analyzed, this question is not hard to answer. The constant number c can simply be 1, and n0 can be 3. So as long as the input size is bigger than 3, this gn aiming 1 multiplied by Gn will always be bigger than Fn. In this case, we say that the upper bound of Fn is Gn, which is expressed as what you can see here. Now you see that we can use the definition to help us determine if a function corresponds to input size n is the upper bound of a given time complexity function. To make sure we are on the same page, let's look at some other examples. Okay, so on the screen, you can see a new example where Fn stays the same, but Gn is updated to just n. The question stays the same by asking if Gn is the upper bound of Fn. You may be tempted to say no, because as it stands now, Fn seems to grow faster than Gn. Both of these two functions are linear. But the slopes of Fn is steeper, which means that it grows faster. However, that's not how you are supposed to answer this question. The key to answer such questions is to stick to the definition. In other words, as long as you can find two constant numbers, c and n0, where n0 represents a specific input size, okay, then when the input size grows beyond n0, Fn will always be smaller than or equal to c multiplied by Gn. Then you can conclude that Gn is still the upper bound of Fn, regardless whether Gn in its current state grows more slowly than Fn. So instead of plotting these two functions directly, can we start by trying to find some constant numbers to make this work? Can we find a constant number c to make c multiplied by Gn grow faster than Fn? Well, actually, any number bigger than 2 should work. This is based on what you know from math. For example, we can make c as 5 and n0 as 1, and plot both Fn and c multiplied by Gn on a 2D plane. As you can see, c multiplied by Gn grows much faster now, and it crosses Fn at some point where n is smaller than 1. So any input size bigger than 1 will guarantee that c multiplied by Gn is bigger than Fn. As a result, we can find two constant numbers to sustain this relationship between Fn and Gn. We would say that the definition is being met, so we can conclude that Gn is the upper bound of Fn, which is expressed as Fn belongs to big O of n. From this example, you can tell whether the given Gn grows faster than Fn doesn't really matter. It doesn't determine if Gn is the upper bound or not. As long as c multiplied by Gn grows faster than Fn, it will be good enough to deem Gn as the upper bound. Whether c is 5 or 10 or even 100, it doesn't matter. Okay, let's look at another example. In this example, the question stays the same, but Fn and Gn are different. So both Fn and Gn are square functions this time, but Fn has more terms, such as 3 multiplied by n and 9. As it stands now, Fn does grow faster than Gn because of the extra terms. However, from the first two examples, you know that this comparison doesn't matter to some extent, as long as you can find another constant number c to make c multiplied by Gn grow faster than Fn, Gn will be the upper bound for Fn. For example, we can make c as 2. So c multiplied by Gn will be 2 multiplied by n squared, which grows faster than Fn. Considering the extra term in Fn, I mean 3 multiplied by n plus 9, when the input size n is small enough, it is still possible for Fn to be bigger than c multiplied by Gn, such as 1 or 2 as the input size is, which would require you to set this n0, the specific input size, accordingly and carefully. We can make it big enough to account for the early fluctuations. We can make n0 like 100, Given these two constant numbers, we can plot fn and c multiplied by gn. Okay? All we care is the area where input size n and time are bigger than 0. As you can see, c multiplied by gn grows faster than fn, and they will eventually cross with each other, while at the input size of about 5. After that, c multiplied by gn will always be bigger than fn. As a result, c as 2 and n0 as 100 can help sustain this relationship between fn and gn. So you can say that gn is the upper bound of fn, and you can express that as fn belongs to big O of n squared. From this example, you can see that some time complexity functions may have multiple terms being concatenated using plus. In those scenarios, all you need to care actually are the terms with the highest degree of the polynomial, or say the leading terms. The other terms with the lower degree of polynomial, or the other terms that grow comparatively more slowly, they don't matter that much when it comes to determining the upper bound. Okay? So now we have seen and cracked 3 question examples. Let's move to a different set of questions of different flavor. Like this one that you can see on the screen. It asks you to prove the given time complexity function Tn's upper bound is big O of n. So Tn is a linear function defined as 8 multiplied by n plus 5. To prove this, we will stick to the definition of the upper bound. To cast the upper bound definition to this question, all we need to do is to find a constant number c and a specific input size n0, so that 8 multiplied by n plus 5 will always be smaller than or equal to c multiplied by n when the input size n is bigger than n0. We know that the coefficient in a linear function determines how steep its slope is. In the given time complexity function, the coefficient is 8. To make c multiplied by n steeper, or say grow faster, all you need to do is to make c bigger than 8. You can make it a 9, for example, or 10. For example, we can go with c as 9 and find the n0 accordingly. In this table, I list a few values of n. When n is 5, it will make 8 multiplied by n plus 5 equal to 9 multiplied by n. Any numbers bigger than 5 will make 9 multiplied by n bigger. That said, we can choose n0 as 5 or anything bigger than 5, such as 6 or 7, as is listed on the screen. The logic to prove this question is to subtract 8 multiplied by n plus 5 from 9 multiplied by n. Then the remaining would be n minus 5. It will always be bigger than or equal to 0 as long as n is bigger than or equal to 5. That said, we have successfully proven this. Well, the trick is just to find those two constant numbers to sustain this relationship between fn and gn, as is in the definition. The question comes with a different style, or different flavor, by asking you to prove a time complexity function has a specific upper bound. The key to solve this type of questions remains the same. All you need to do is to stick to the definition of the upper bound. As long as you can find a constant number c and a specific input size n0, so that the given time complexity function will always be smaller than or equal to the upper bound function multiplied by c. Of course, when the input size grows beyond n0, you will be able to verify their relationship and solve this type of question. Now you have seen enough about the upper bound. Let's move to the definition of the lower bound. Okay, so this is the definition of the lower bound. It's similar as the upper bound. The symbols that might be strange to you have been marked out again. The definitions says given a time complexity function fn and another function gn, if you can find a constant number c and a specific input size n0 to sustain a relationship between fn and gn, then gn will be the lower bound of fn. So what's the relationship? Fn will always be bigger than or equal to c multiplied by gn when n is bigger than or equal to the specific input size n0. Okay? Gn being the lower bound of fn is expressed as fn belongs to omega of gn. The visualization sits below the definition. As you can see, the x-axis represents the input size n, and the y-axis represents time. As n grows beyond n0, fn will always be bigger than c multiplied by gn. Again, the fluctuation when n is smaller than n0 doesn't really matter. Even if this n0 is very big, such as 1 million or 2 millions, as long as it is a constant number, it will be fine. To make sure we are on the same page, let's look at a question example. So the question asks if the given gn is the lower bound of fn. Fn is defined as a square function, n squared plus 2 multiplied by n plus 3. Gn is defined as 10 multiplied by n. To directly plot these two functions to the plane, you will have this. The two functions, they will cross with each other at an input size of about 8. After that, as the input size grows, fn will grow much faster than gn. To determine if gn is the lower bound of fn, all we need to do is to plug in the definition of lower bound. If we can find two constant numbers c and a specific input size n0 to sustain this relationship between fn and c multiplied by gn, we will be able to conclude that gn is the lower bound. Based on what you see from the plot, based on what you see from this visualization, it's not hard to find such two constant numbers. For example, c can simply be 1, and n0 can be 8. When n, as the input size, grows beyond 8, c multiplied by gn will always be smaller than fn. As a result, you can conclude that gn is the lower bound of fn, expressed as fn belongs to omega of 10 multiplied by n. Okay, wait a second. Is the coefficient 10 inside omega necessary? Can we simply remove it? Well, yes, you can. In that case, you are actually trying to establish the relationship between fn and the different function, which is simply n. We change the constant number c from 1 to 10, we don't even need to change the plot at all. Beyond this question, it's actually very rare to include coefficients in the expression of upper or lower bounds, simply because they don't matter. If a function with coefficient is proven to be a lower or upper bound, its variation without the coefficient, or say with the coefficient value as 1, is also a lower or upper bound. That's the takeaway from this example. Okay, now let's move to the next definition, the tight bound. The tight bound is defined as follows. Let's mark out the math symbols and their meanings. The definition essentially says that, given a time complexity function fn and another function gn, if you can find 3 constant numbers, note that 3 is no longer 2, different from the upper or lower bound. You need 3 constant numbers now, c1, c2, and n0. To sustain a relationship between fn and gn, then gn is the tight bound of fn. What is that relationship? When n, the input size, is bigger than or equal to n0, fn will always be sitting between c1 multiplied by gn and c2 multiplied by gn. By that, I mean fn will always be bigger than or equal to c1 multiplied by gn and smaller than or equal to c2 multiplied by gn. Okay? So the visualization of the relationship between Fn and Gn may help further make sense of this definition. C1, C2, and N0 are three constant numbers. When n is bigger than n0, you would always have this sandwich-like relationship, and Fn will always sit in the middle. Let's look at an example to help you make sense of the tight bond. So the question is similar to what you have seen. It's asking if the given Gn is the tight bond of Fn. Both Fn and Gn are square functions. Fn is defined as 2 multiplied by n squared plus 2 multiplied by n plus 3. Gn is defined as n squared. To determine if Gn is the tight bond of Fn, all you need to do is to find three constant numbers, two coefficients C1 and C2, and one specific input size N0, so that they will sustain this sandwich-like relationship where Fn sits between C1 multiplied by Gn and C2 multiplied by Gn. Based on what we know from math, given a square function, the coefficients of the square term can control how fast this function grows. The bigger it is, the faster it grows, and vice versa. If we want C1 multiplied by Gn to grow more slowly than Fn, we need to make sure that C1 is smaller than this coefficient of 2, because that is the coefficient used by Fn. Similarly, we can make C2 bigger than 2, so that C2 multiplied by Gn will grow faster than Fn. That said, it's not hard to find three constant numbers. For examples, we can make C1 as 1 and C2 as 4, and plot Fn C1 multiplied by Gn and C2 multiplied by Gn accordingly. As you can see here from this plot, as the input size grows, C2 multiplied by Gn will eventually cross Fn at the input size about 3 and grow much faster afterward. In contrast, C1 multiplied by Gn will always grow more slowly than Fn. That said, you can easily set a specific input size, such as 10, to sustain this sandwich-like relationship. That said, Gn is a tight bond of Fn. You can express this relationship as Fn belongs to theta n squared. From this example, you can see that if the terms of the highest degree in two functions have the same degree, they will be each other's tight bond. The extra terms with smaller degrees or that grow more slowly, they don't really matter. If you think about all the examples we have examined for upper, lower, and the tight bond so far, if a time complexity function has multiple terms, only the term with the highest degree, or the term that grows the fastest, matter the most when it comes to determining the bonds. That's actually how bonds help simplify the measurement of growth of functions. Now, we have wrapped up all the definitions of upper, lower, and tight bonds. We are done with the growth of functions. We will move to asymptotic analysis next. So what's asymptotic analysis about? It's about combining what we have learned from the last two lectures and this lecture. Given an algorithm, it will be asked to find its upper or lower bound, or sometimes tight bond. For example, this is an algorithm that we examined in the first two lectures. This algorithm searches for and returns the max value given a linear data structure like an array. In the past, we analyzed its best case and worst case and derived time complexity functions accordingly. We know that regardless of whether you're talking about the best or worst case, its time complexity function will always be a linear function of it. Based on what you learned from growth of functions, you need to apply the definition of bonds and identify its upper, lower, and tight bond. That's what asymptotic analysis is all about. Okay? So for a linear time complexity function, both its upper and lower bound can simply be n. expressed as big O of n, or omega of n, expressed as big O of n, and omega of n. In case you wonder if you can say that the upper bound of this algorithm is big O of n squared, yes, you can. But that won't be as accurate or say as tight as n. Similarly, log n can be the lower bound of this linear function, but won't be as tight as n. Okay? When you apply the definition of tight bound, it won't be difficult to find its tight bound as n. So we pretty much skipped the steps of applying the definitions of bounds because we have just seen very similar examples. However, this example still tells us something about asymptotic analysis. Given an algorithm, you need to analyze its best and worst case to derive time complexity functions first. From there, you need to determine the bounds based on the derived time complexity functions. Okay, that's what asymptotic analysis is about. So let's look at another example, insertion sort. We analyzed this algorithm in lecture 2. In case if you need a refresher, the link to lecture 2 is in the description. So we analyzed the worst case for insertion sort and derived a time complexity function as a square function. The upper bound for the square function can be simply another square function with coefficient as 1 and no extra terms. We have seen how this works when we covered the growth of functions. Such an upper bound can be expressed as big O of n squared. In case you wonder, well, if n cubed is also an upper bound of this time complexity function. It is. It's just not as tight as n squared. You can also deduce its lower bound and a tight bound, which will both be n squared. Okay? However, it's worth pointing out that the upper bound of the worst case time complexity function is also the upper bound of this algorithm. Because other cases, I mean the best case or the average case, are more efficient and it takes less time to execute. So there's no chance for other cases to go beyond the upper bound of the worst case. As a result, you can think it as the upper bound of not only this time complexity function of the worst case, but also this algorithm. Okay? Similarly, we also studied the best case of insertion sort and derived its time complexity function, which is a linear function. The lower bound of a linear function can just be another linear function in its simplest form, which is n. Okay? Similarly, its upper and tight bounds can also be the same linear function, which is n. The lower bound of the best case is what we should pay attention to. It is expressed as omega of n, and it's not only the lower bound of the best case, but also the lower bound of the insertion sort algorithm. The rationale is similar as the upper bound of the worst case. No other cases are more efficient than the best case. If the best case doesn't go below its lower bound, neither would other cases. As a result, the lower bound of the best case is the lower bound of the algorithm. So from this example, you can see that although best case, average case, and worst case analysis is a different dimension from asymptotic analysis, they are still related. The relationship is somewhat self-explanatory. If you're looking for the upper bound of a given algorithm, go for its upper bound of its worst case. If you're looking for the lower bound of a given algorithm, go for its lower bound of the best case. Now, you should have a better and clearer understanding of the two different but related dimensions of time complexity analysis. The last thing we need to talk about under asymptotic analysis is the comparison across common upper bounds. Yes, upper bounds are typically what we care about the most because they measure the worst possible performance of algorithms. Some of the commonly used upper bounds are listed here on the screen, such as log n, n squared, and 2 to the power of n. If you plot all of them to a 2D plane with the input size as the x-axis and the time as the y-axis, you will be able to see which one is more efficient and which one is slower. For the record, because we seek efficient algorithms, as the input size grows, the less time an algorithm takes, the better. For example, log n grows much slower than n. So if an algorithm runs on big O of log n, that's great for us. In contrast, if an algorithm runs on big O of 2 to the power of n, that would be terrible. In case if you forget or have difficulty comparing two different upper bounds, you can always find some concrete numbers and plot the dots first, then concat them using lines. For example, a series of good input will start from 1, then multiplied by 2, such as 1, 2, 4, 8, then 16, etc. After calculating all the corresponding values using upper bound functions, you will have a series of dots. When you concat them using a line, you will have a rough picture of its growth rate. So if you have difficulties in memorizing the different relationships among these upper bounds, it's actually not needed, as long as you know how to get the job done. In this lecture, we compared asymptotic analysis to upper, lower, and average case analysis as two different dimensions of time complexity analysis. We also covered the growth of functions and explored how asymptotic analysis is conducted on algorithms. Hope you learned something new. This lecture discusses divide and conquer algorithms. Particularly, we analyze and discuss the time complexity of divide and conquer algorithms. Here's the roadmap of what we will cover. In this lecture, we will start by providing a general definition of divide and conquer algorithms. After that, we will dive into an algorithm example, a binary search. We will go over the algorithm and conduct a time complexity analysis on it. As we do that, we will introduce a general approach to analyze time complexity of divide and conquer algorithms, the recurrence tree method. So what's divide and conquer? You may have heard of the term for many times, but don't know its accurate definition yet. Divide and conquer is not a specific algorithm. Instead, it's a general algorithm design paradigm. An algorithm is like a specific recipe for solving a problem. An algorithm design paradigm is like a general cooking style or method, such as grilling, baking, or steaming. It provides a framework or philosophy for creating recipes. For example, divide and conquer is a cooking style that involves breaking the task into smaller pieces, like cutting ingredients into portions, and solving each part independently before combining them. Binary search, as an algorithm, is a recipe developed using this cooking style. There are three key steps in divide and conquer algorithms, including divide, conquer, and combine. The divide refers to dividing the problem into subproblems that are similar to the original but smaller in size. Conquer means to solve the subproblem recursively. If a subproblem is smaller enough, then you can solve that directly. Last, combine means to combine the solution to the smaller subproblems to create a solution to the original problem. All divide and conquer algorithms follow this pattern. To help you make sense of it, we will look at an example, the binary search. On the screen, you can see the pseudocode of binary search. What problem does it solve? It searches for a target element from a linear data structure like an array. Putting binary search aside, if your goal is to find a given target element in an array, you can of course traverse the array from the beginning to the end. If your target is found, then your job is done. If not, the target is not in the array. This is what we call linear search. In comparison, binary search is more efficient, but it comes with a big assumption. What's the assumption? The given array is already sorted. With that assumption, at each step, binary search divides the search space, or say the array, into two halves by comparing the target element with the middle element of the current range. Based on the comparison, it eliminates one half of the search space, either the left or the right one. Then, it focuses the search on the remaining half. In case you don't know how it works, let's take a look at the code and make sense of it using an example. The algorithm takes two parameters, the array and the target. Remember, the array is fully sorted. Let's assume it's in an increasing order. So binary search starts by making two indexes. The starting index at 0 and the ending index at array's length -1. The starting index is denoted as, short for start, and the ending index is denoted using E, short for end. While S is smaller than or equal to E, you will calculate and find the middle index. If the element sitting at the middle index is equal to the target, you would return mid, which is the index of the target element. If the element is smaller than the target, you would update the starting index to the middle index +1. By doing that, you basically eliminate the first half of the array, starting from S to the middle index. The reason is that if the element in the middle is even smaller than the target, everything comes before it, on its left, will also be smaller. So there's no point to compare them to the target anymore. By updating S to mid +1, you will continue this while loop, but you won't look at the first half of the array anymore. On the other hand, if the element is bigger than the target, you would update the ending index E to the middle index -1. By doing that, you will eliminate the second half of the array, starting from the middle index to the original ending index in the future iterations of the while loop. The rationale is similar. The array is sorted. If the element in the middle is even bigger than the target, anything that comes after it, on its right side, will also be bigger. So you should save your energy by searching in the section where elements are smaller, which is the left half of the array. Okay? So when the while loop terminates, yet the target is still not found, it would return -1, indicating that the target is not found. Let's go through an example to help you make sense of the binary search. On the right side of the screen, you can see a sorted array in increasing order. In case the two rows confuse you, the first row represents the values in the array, and the second row represents indexes of the array. The target to search for, in this case, is 2. So the starting index S and ending index E are initialized to 0 and 7 respectively. The middle index is calculated to 3. The corresponding element of the middle index is 5. 5 is bigger than the target. The array is sorted, so all the elements coming after 5, they would also be bigger than the target. There's no need to compare them to the target anymore. As a result, we will go to this line and update E to mid -1, which is index 1, whose corresponding value is 2. 2 is equal to the target, so we will return the index of 1. Then your job is done here. You see, it's much faster than traversing the whole array and comparing each element to the target. You essentially cut the array by half in each iteration of the while loop. Let's look at another example to make sure that we are on the same page. This time, the input array stays the same, but the target becomes 9. The starting index is 0, the ending index is 7, so the middle index is 3. And corresponding to an element, that's 5. 5 is smaller than 9, so this line will be triggered. You will update S to mid +1, which is index 4, because S is still smaller than E. so the next iteration of the while loop will be triggered. The mid is recalculated to 5 this time. The element corresponding to index 5 is 7. 7 is still smaller than the target 9, so this line will be triggered again. It will update S to mid plus 1, which becomes 6. Because S is still smaller than E, so the next iteration of the while loop will be triggered. In the next iteration of the while loop, the middle index is recalculated and updated to 6, whose corresponding element is 9. 9 is equal to the target. It will return the index, and the job is done. Now we should be on the same page of how binary search works. You may still wonder how this is divide and conquer. It's hard to see any divide and conquer here. While binary search is considered a divide and conquer algorithm, if the iterative implementation hides that from you, we can list the recursive implementation by its side. Both implementations achieve the same thing. The recursive version takes 4 parameters instead of 2, including the sorted array, the target value, the starting index, and the ending index. In this implementation, there's no while loop. If the element at the middle index is equal to the target, it would return the index. If smaller, it will call binary search again on the second half of the array, and return its result. Otherwise, it will call binary search on the first half of the array and return its result accordingly. Regardless whether it's iterative or recursive, binary search divides the search space into half by comparing the target element with the middle element of the current range at each step. That's what is known as the divide step. Based on the comparison, the algorithm eliminates one half of the search space. It's going to either be the left half or the right half. And then the algorithm would focus the search on the remaining half. That's what is known as the conquer step. While binary search doesn't explicitly combine results like some other divide and conquer algorithms, like merge sort, the process of halving the search space and eventually finding the target element aligns with the essence of the divide and conquer algorithm approach. So you know what binary search does and why it's a divide and conquer algorithm. Let's analyze its time complexity. Let's start with something simple. The best and the worst case analysis. The best case is trivial. It happens when the element sitting in the middle of the array is equal to the target. Like this example, where the target is 5, and the element sitting in the middle of the input array is also 5. In this case, this line will be triggered, and the middle index will be returned. The while loop will be terminated in one iteration. That said, binary search only takes a constant number of steps, or say constant time in the best case. What about the worst case scenario? The worst case means that the while loop runs for as many iterations as possible until the starting index is bigger than the ending index. In other words, the search space will be halved and halved for many times until it becomes empty. For example, when the target is 11, for the same input array, it will have a worst case. It will keep halving the search space for 4 times, starting with the whole array. Then to this, then to this, then to this. After that, S will become bigger than E, ending the whole while loop, and -1 will be returned. At the start, you have a sorted array of size n, which is the input array length. In our case, that's 8. In each step, binary search eliminates half of the elements in the search space by comparing the target with the middle element. If the target is smaller, it eliminates the right half. If the target is bigger, it eliminates the left half. In our case, the target is always bigger, so the left half always gets eliminated. After the first step, the search space is reduced to n divided by 2, which is 4 in our case. After the second step, it's further reduced to n divided by 4, which is 2 in our case. After the third step, it's n divided by 8, which is 1 in our case. This process essentially continues until the search space becomes 1 element or less, at which point the target is determined to be absent. So at each step, the search space size is divided by 2. This can be expressed mathematically as, after k steps, the size of the search space is n divided by 2 power 2k. Remember, n represents the input size, the size of the sorted array, where k represents the number of the steps. Each step represents an iteration of the while loop. So the process stops when the search space becomes 1. Okay? Rearranging this, you will have 2 power 2k is equal to n. Taking the logarithm base of 2 on both sides, you will end up with k is equal to log of n. Thus, binary search requires about log n steps to complete. Since there are log n steps in the worst case, the total time complexity is big O of log n. This conclusion is based on some intuition and some leap of faith. It's not based on a generalized method. We will get to the generalized method later. Before that, it's worth mentioning that many divide and conquer algorithms have a logarithmic component in their time complexity, especially when the divide step involves splitting something in half. Now you know that the time complexity of binary search based on our intuition. Let's get a more generalized method for analyzing its time complexity, and the time complexity of all divide and conquer algorithms. Before we do that, we need to introduce a new concept called recurrence relation. So, a recurrence relation is a mathematical equation that defines a sequence of values based on its previous terms. It describes how the time complexity of a problem is related to two things: the size of the input and the complexity of smaller subproblems created during the algorithm's execution. It's commonly used to model and express the time complexity of divide and conquer algorithms, such as binary search. When you have a recurrence relation, it makes solving the time complexity of divide and conquer algorithms much easier. By solving a recurrence relation, we can determine the time complexity of its corresponding algorithm. In other words, it is still a time complexity function Tn, where n represents the input size, but it describes the relationship between Tn at this step and Tn at the next step as the recursion is triggered. An example is provided to help you make sense of it. So what sits on the left side of the equation describes the total time complexity of this function Tn. The corresponding divide and conquer algorithm does some work at the current step, which takes a constant number of steps. In this example, that number of steps is 1. As recursion happens, the same function is executed on half of the input size. That's how you get T of n divided by 2, because the only thing changed here is the input size. This equation describes the time complexity of the current step and the next step. By step, I mean the triggering of the recursive call. This may still sound fuzzy. That's why we need to look at a more concrete example. Let's go back to the binary search. We know that binary search can be implemented iteratively and recursively. They achieve the same effect. To make it easier to understand how binary search works, we used the iterative version. Now, to make it easier for you to understand how we derive the recurrence relation of binary search, we will use its recursive implementation. Our goal is simple. We want to extract a recurrence relation for binary search. In other words, we want to describe the relationship between the time complexity at the current step and the next step. To scaffold your thinking, I have listed this expression here. As long as you can figure out what lines are executed at the current step and what time complexity of those lines have, you will be halfway through the task. So what lines are executed under binary search at the current step? These lines would be executed. Okay? That takes constant number of steps, right? Remember, we are talking about the worst case. So you can forget about the if condition. Either else if or else will be triggered. Both else if and else returns the recursive call of binary search. However, the arguments are different. By replacing s with mid plus 1 or by replacing e with mid minus 1, you're eliminating the search space or say the input size by half. As a result, the recurrence relation can be expressed as T of n is equal to T of n divided by 2 plus theta of c. T of n divided by 2 represents the time it takes to trigger either of the two recursive calls on the halved input size. Theta of c represents the constant number of steps it takes to run these lines. This is the recurrence relation of binary search. It describes the time complexity at the current step in relation to the time complexity of the next step. As you can see, the time complexity function t shows up at both sides. So this doesn't tell us how efficient binary search is. To answer that, we need the help from the recurrence tree method. This is the generalized method to solve time complexity of divide and conquer algorithms we have mentioned. It involves at least 4 steps, including get the recurrence relation, draw the recurrence tree, calculate the work at each step, or say at each level, and sum the total work. Let's use binary search as an example to make sense of this method. We already have a recurrence relation, so we are done with step 1. Step 2 is about drawing the recurrence tree. Think about that we are executing binary search on a set of arguments, including the array, the sorted array, the target, the starting and ending indexes. So the array is the example we studied, and the target is 11. The starting index is 0 and ending index is 7. A series of recursive calls will be triggered when the binary search is executed with this set of arguments. Like this. In every recursive call, the starting and ending indexes determine the search space, or say the problem size. As you can see, the problem size is reduced by half every time when the next recursive call is triggered. Based on such understanding, we can draw a tree-like structure to facilitate our investigation of the time it takes to execute a binary search on a generalized problem size of n. We will use 2 columns. The left column indicates the problem size, or say the subproblem size, as recursion is triggered. The right column indicates the time it takes to address the work at a step corresponding to the subproblem size in the same row. Of course, the time it takes to do the work on the corresponding step is outside of recursion, because the time of the recursive call will be accounted for in the next step. Why is this method named the recurrence tree method? Because as you list the subproblem size of recursions triggered at each step row by row, you will have a better idea of the number of recursive calls being triggered, which is helpful for you to sum up the time it takes at each step so that you can deduce the total time it takes to execute a binary search tree algorithm. So what is the initial problem size when the binary search is executed, assuming that the initial input is an array of size n? The problem size is of course n. The time it takes to do the work outside of the recursion at this step is simply these 3 lines. They take constant time to be executed. So we will list C in the same row corresponding to this problem size, where C is a constant number. The execution of this binary search on a problem size of n will trigger another binary search on half the problem size in either of the two recursive calls. The subproblem size is n divided by 2. However, the time it takes to do the work at this step remains these 3 lines, which takes a constant time to run. So we will list them side by side. Subproblem size is n divided by 2, and the time outside of recursion corresponding to this problem size remains C. This recursion will trigger another recursion on a further half the problem size. Yet, the time it takes to do the work outside of the recursion at next step remains the same. So we can list them side by side, the problem size as n divided by 4, and the time remains C. This process will continue at each step. It will reduce the problem size by half, like this, until it becomes 1. However, the time it takes to do the work outside of the recursion remains the same as a constant number. Now you have a tree structure fully drawn. Based on this structure, you have enough to calculate the time complexity function by adding up all the time in the right column together, because they are the actual time it takes to get things done in every recursive call that's being triggered along the way until the problem size becomes 1. To get the time complexity function, you need to figure out how many C's there are. In other words, you need to know how many recursions are triggered, or say how many steps it takes to reduce n until it becomes 1. This becomes a question that we studied if you focus your attention on the left column. How many times can you keep dividing n by 2 until it becomes 1? The equation remains the same. It takes k steps to achieve this. The relationship between n and k will be n equal to 2 power 2k. If you apply the logarithmic to both sides, you will have log n that's equal to k. That said, it takes log n steps to keep dividing n by 2 until it becomes 1. That said, there are log n of c. You can add them up to derive the time complexity function as Tn equal to c multiplied by log n. C as a constant number won't matter when you try to determine the upper bound. So the upper bound of Tn will be just the log n, expressed as Tn belongs to big O of log n. In summary, the recurrence tree method requires you to figure out the relationship between subproblem size of recursion at this and the next step, as well as the time it takes to address the work outside of recursion corresponding to a problem size. You will start with a generalized problem size n and develop a tree-like structure by filling out these 2 columns row by row, where each represents a problem size and its corresponding time to do the work outside of recursion. In the end, you need to add up all the time, or say combine all the time it takes to calculate the time complexity function. In this video, we covered the definition of divide and conquer algorithm and discussed the recurrence relation and the recurrence tree method that is used to deduce the time complexity of divide and conquer algorithm. We achieved this by covering the binary search algorithm. In the next video, we will cover a different divide and conquer algorithm, the merge sort. We will revisit recurrence tree method and cover a different approach to time complexity analysis on divide and conquer algorithm, which is the master theorem. This lecture covers the time complexity analysis of divide and conquer algorithms. Here's a roadmap of what we will cover. In this lecture, we will cover a new generalized approach to analyze time complexity of divide and conquer algorithms, the master theorem. We will also revisit the recurrence tree method so that you can compare the 2 generalized approaches to time complexity analysis of divide and conquer algorithms. We will use the merge sort algorithm as an example to start our discussion. On the screen, You can find the pseudocode of the merge sort algorithm. In case if you don't know how merge sort works, let's cover the basics of this algorithm first. On a large picture, merge sort is a classical divide and conquer algorithm. It recursively divides the unsorted array into two smaller subarrays until each subarray has only one element. This is the divide step. After that, it compares elements from the two subarrays and merges them in sorted order. This is done recursively, building up the sorted array from smaller sorted pieces. This is the conquer step. After merging all the subarrays back together, the entire array will become sorted. This is the combine step. Different from the insertion sort that we covered previously, merge sort requires additional memory for the temporary arrays that are used in the divide and merge process. Now, let's take a look at the code to help you get a better understanding of how merge sort works. Merge sort takes one parameter A, which is a linear data structure like an array. The first line is the condition for everything that follows. The condition says that the length of the array needs to be bigger than 1. Otherwise, don't run this algorithm at all. Of course, if an array has a size of 1, it's already sorted. Only when an array has a length that's bigger than 1, merge sort can offer some help. The merge sort algorithm can be divided into 3 code blocks. The first block does the divide. The second block does the conquer. And the third block does the combine task. Let's hide block 2 and 3, so we can focus only on the first block. The first block of code starts by finding the middle index of the input array. If you divide the input array by that index, you will have the left half and the right half. After that, this block of code makes 2 deep copies of the left and the right halves. Note that it's a deep copy. In other words, the variable left half and the right half here refer to 2 totally different arrays from the left part or the right part of the original input array. Okay, but the left half will end up having the same elements of the left half of the original input. The same thing can be said for the right half. It will eventually have the same elements as the right half of the original input after you finish running the first block of code. Any changes to left half, I'm talking about the variable, won't affect the original input and vice versa, because it's a deep copy. The same thing can be said, of course, for the right half. Okay, that's the first block of code, the divide step. The second code block is a recursive call on 2 deep copies, left half and right half, that were generated from the first block of code. We can think that after the recursive call of merge sort being applied to the left and the right half, both of the 2 deep copies would be fully sorted. That's all you need to know for now, and we won't look underneath the hood yet. We will revisit this soon. Now, all you need to know is that after you run the second block of code, both the left half and the right half would be fully sorted. Let's get a good understanding of what the third block of code does first. The third block assumes one thing, which is that the left half and the right half are 2 fully sorted arrays. Then, it moves on to merge the 2 sorted arrays into one big array by using 3 pointers, I, j, and k, to track the merge process. The first while loop does the merging by comparing the elements pointed by I in the left half and pointed by j in the right half, and copying the smaller element into A, the original input, at the position of the index k. When this while loop terminates, it's possible for either the left half or right half to have some elements that were never examined or compared or used in this process. That's where the second and the third while loop comes into play. The second and the third loops, they check if there are any remaining elements in either left half or right half that need to be copied directly to A. If so, they will do accordingly. You may notice that the merged elements are directly placed into the original input array, capital letter A. That will overwrite the existing elements, of course. But since left half and right half have all the original elements, the existing elements in A no longer matter, and the overwriting would be fine. Let's walk through an example to make sure we are on the same page about this block of code, about how the merging would work. Okay, as you can see on the screen, the left half and the right half are the two sorted arrays. A is the original input array, and will be used as a vehicle to store all the sorted elements. This process will lead to the original elements in A being overwritten. The original elements in A no longer matter because they have been stored in both left half and right half. As a result, we will hide them in our vision to avoid distractions, like this. Okay? The I, J, and K are the 3 pointers that are all initialized to 0. Okay? Index zeros. They are used to track the process of merging left half and right half into A. You will do so by comparing the elements pointed by I and J, and put the element that's smaller into their K points in A. In this example, as shown on the screen, I currently points at 1. J currently points at 2. Since 1 is smaller than 2, it will place 1 into the index of K, which is 0 in A. After this, it will move the pointers from either left half or right half if you have copied this element to A. In our example, we copied 1 to A, and 1 comes from left half, so we move I rightward by 1 step. Besides that, it would always move K rightward by 1 step, so that it can point to the next vacancy where you can place an element in without causing troubles. So we move both I and K rightward by 1 step. Then, you would continue the comparison process. The element pointed by I right now is 3, and the element pointed by J is 2. Since 2 is smaller, you would copy 2 into A at the index of K, and move both pointers J and K rightward by 1 step. Okay, the comparison would continue. The element currently pointed by I is 3, and the element pointed by J is 5. Since 3 is smaller, you would copy 3 into A and place it at the index K. After that, you move the index I and K rightward by 1 step. The next comparison is between 4 and 5. Since 4 is smaller, you would place 4 into A at the index K. After that, you move the index I and K rightward by 1 step. The next comparison now is between 7 and 5. Since 5 is smaller, you would copy 5 into A at index K, and move both J and K 1 step rightward. The next comparison is between 7 and 8. Since 7 is smaller, you would copy it to A at K, and move both I and K rightward by 1 step. Now you have depleted the left half, since I is bigger than the length of left half, so the comparison is over. The first while loop ends. Yet, you still have some elements in right half, as J is pointing at some element in the right half, so you can copy everything starting from J till the end in the right half directly to A. That's how the merging process works. Now you know what all the 3 code blocks do. Let's focus our attention on the second code block again, the recursive call. To make things easier to navigate, I will replace block 1 and 3 with comments, like this. So now there's only one thing that I want to bring to your attention. The recursive call are placed in the middle of the function definition. We know that code gets executed from top to the bottom, from left to the right. The first code block does the divide by making deep copies of left half and right half subarrays. The third code block does the combine task by merging two sorted subarrays back into one fully sorted array. If we execute merge sort on a given array, like what you see here on the screen, the order of execution will eventually lead to a visual like this. Okay? A good exercise to test your understanding of the execution order is to figure out whether the step A or step B firstly gets executed. Both A and B are highlighted in the visual. The answer is that A gets executed ahead of B, because code always gets executed from top to the bottom, from left to the right. So the recursive call on left half will keep triggering other recursive calls on their left halves until the subarray size becomes 1, because they get executed sooner than any other recursive calls on any right half based on their order. In short, you will keep dividing, but your focus is always on the left half until you have a single element array. Then it will trigger the execution of the first merge sort on the single element right half, which is 8. After that, it will reach the first combine step for the two element array, 5 and 8. At the combine step, or say merge step, merge sort will sort the two elements in increasing order. The two elements are already in the right order, so you won't see any changes here. Then it will move to execute the merge sort on the right half with two elements. In our case, that's 3 and 1. Then the same story will happen. It will make deep copies of 3, the left half, and 1, the right half, and then combine and sort the two elements into 1, 3, like this. Then the combine step on the 4 elements, 5, 8, 3, and 1, will be triggered to merge the two element arrays. It will end up with a sorted 4-element array, like this, 1, 3, 5, 8. The execution order on right half of the original input will be quite similar. You will start with a series of triggering of the merge sort on all the left halves until you have a single element, which is 4. Then the merge sort will be triggered on the right half with a single element 10. Then the combine step, or say the merge step, will happen to the two element array, 4 and 10. That said, they will be sorted. Well, they are already in the right order, so you won't see any changes. Then merge sort will be triggered on the two element array, 2 and 7, before you end up with two single element arrays, 2 and 7. Then you will merge them, or say sort them into 2 and 7. After that, you will combine, or say merge the two element arrays, 4, 10 and 2, 7, so it will become 2, 4, 7, 10. In the end, you will finally combine the two 4-element arrays. I'm talking about 1, 3, 5, 8. The other array is 2, 4, 7, 10. They are already perfectly sorted, so this step will sort the original input array, like this. Then you are done. That's a complete breakdown of the execution order of the merge sort being applied to an 8-element array example. So in summary, merge sort will keep dividing until you have a set of single element arrays. Then merges them back into a set of 2-element arrays, then 4-element arrays. The process continues until you have a fully sorted array of the same size as the input array. The merge process also takes care of sorting. Now you know how merge sort works, let's discuss its time complexity analysis. In the part 1 lecture, we learned recurrence relation and recurrence tree method that is used to analyze the time complexity function and the upper bound of divide and conquer algorithms. Let's revisit them here in the context of merge sort. Let's start with a simple question. What's the recurrence relation of merge sort? Assuming that we have called this function, this merge sort algorithm, on a given array A, like this example, the time complexity at this step, when we call merge sort with this particular argument as A, is Tn, right? We also know that Tn is equal to the sum of the time the 3 code blocks take to be executed. Well, last thing that we know is that the second block of code triggers a recursive call on data of half input size in comparison to A. So each recursive calls will take t of n divided by 2 time. It's the same function of merge sort being called on half of A. There are 2 of them, so the second block of code takes 2 multiplied by t of n divided by 2 time, like this. So we are halfway from establishing a relationship between Tn at the current step and the next step when recursion calls are triggered. The remaining part of this recurrence relation is to figure out the time the first and the third block of codes take. The first block of code has 3 steps. The 3 lines are about making deep copies of the left half and the right half of the original input array, which takes c multiplied by n time to do. You can approach making deep copies by traversing through the whole given input array. So it's going to be c1 multiplied by n, where c1 is a constant number. What about the third block of code? The first 3 lines initialize I, j, and k to 0. They take constant time to run. The first while loop takes the same number of iterations as either the length of the left half or the right half, whichever is smaller. After that, either the second or the third loop would get executed, traversing the elements that were not examined in the longer one between left half or right half. The length of the left half is roughly n divided by 2. Same for right half. The 3 while loops are placed one after another, so executing them takes maybe c2 multiplied by n time, which is in proportion to the input size. So that's c2 multiplied by n, where c2 is another constant number. Now, you have a recurrence relation between Tn at the current step and the next step t of n divided by 2 when the recursive calls are executed. We can actually simplify this equation a bit by combining c1 and c2 and replace them with a single letter c, which is another constant number. So the relationship can be simplified to Tn equal to 2 multiplied by t of n divided by 2 plus c multiplied by n. Okay? With the recurrence relation set, we can move to apply the recurrence tree method to figure out the actual time complexity function and its upper bound. Before we do anything, I need to remind you that the recurrence relation is composed of 2 parts, the work done in the current step and the work done in the recursive call. The time it takes to get the work done at the current step is c multiplied by n. Okay? The recursion takes 2 multiplied by t of n divided by 2 time. Using the recurrence tree method, we will list the subproblem size and the time it takes to solve the work at each step corresponding to the problem size in 2 columns side by side, like this. The current problem size is n, and the time it takes to solve the work at the current step outside of the recursion is c multiplied by n. So we can list them in this table like this. In the next step, the recursion is triggered on half of the input size, both left half and the right half. So the problem size becomes n divided by 2 for the left half and n divided by 2 for the right half. Since there are 2 of them, we will list them both. Merging for both left half and the merging for right half are both c multiplied by n then divided by 2. Since there are 2 of them, the total time will be the sum of the 2, which is also c multiplied by n. In the next step, step 3, it will trigger for merge sort on further half the input sizes. Each of those arrays will be of the size as n divided by 4. The merging for those arrays will be c multiplied by n then divided by 4. Since there are 4 of them, it will need to add them up to derive the total time it will take to solve the work at this step. In the end, it will have another c multiplied by n time in the right column. The next step will be similar. It will trigger merge sort on further half the input size. This time, that's n divided by 8. And the time it takes to merge each of those subarrays will be c multiplied by n then divided by 8. There are 8 of them, so the total time will be the sum, like this. You may have seen a pattern here. Regardless of the problem size, the total time to address all the work at that particular step is always going to be c multiplied by n. The process will continue until the problem size becomes 1, like this. So now, to figure out the total time it takes to execute a merge sort, you will need to add all those total merging time together. To do that, you need to answer a key question. How many of c multiplied by n are there? If you look at this tree structure that you have developed, this becomes a familiar question. How many times can you keep dividing n by 2 until it becomes 1? The same equation that you have solved. Okay? If you apply logarithmic to both sides, you will have the answer to the question. It takes k step to keep dividing n by 2 until it becomes 1, and k is equal to log n. That said, there are log n number of c multiplied by n, so you can calculate that Tn is equal to c multiplied by n, then multiplied by log n. The constant number c doesn't really matter, especially when it comes to calculating the upper bound. So the upper bound is n multiplied by log n. Now you have figured out the time complexity and the upper bound of the merge sort via the recurrence tree method. Let's move to discuss a different generalized approach to derive the time complexity analysis for divide and conquer algorithm, the master theorem. So what's the master theorem? The master theorem is a powerful tool that's used to analyze the time complexity of recursive algorithms, especially for divide and conquer algorithms. It provides a way to determine the asymptotic behavior of a recurrence relation. In other words, given a recurrence relation, the master theorem helps you find its bound. The definition of the master theorem is presented on the screen. Let's digest it bit by bit. I'm going to hide the 3 different conditions, so we can focus on explaining the context first. Okay? Given a recurrence relation expressed as Tn equal to a multiplied by t of n divided by b plus fn. A multiplied by t of n divided by b represents the amount of time the recursion takes. A represents the number of subproblems, and b represents how the problem size is divided at the current step. Fn is a term representing the amount of time required to perform the work at the current step outside of the recursion. Recall the recurrence relation of merge sort we just covered. It can be expressed like this. In this case, both a and b are 2, and c multiplied by n is the fn for the merge sort. The first 2 represents how many subproblems are there at each step of the recursion, and the second 2 represents how the problem is divided at each step of the recursion. And c multiplied by n represents how much time it takes to do the work at each step outside of the recursive call. Particularly, the majority of the work is merging. There are 3 conditions specified in the master theorem, based on the comparison between the growth rate of fn and n power to the log base b of a. If fn grows slower, then you have the first condition. If fn grows at the same rate as n power 2 log base b of a, then you have the second condition. If fn grows faster, and fn is the dominant growth term in comparison to the recursive term, you have the third condition. Okay, let's dive into these different conditions. In the first condition, when fn grows slower, the tight bound of Tn is theta n power 2 log base b of a. In the second condition, when fn grows at the same rate as n power 2 log base b of a, the tight bound of Tn is theta n power 2 log base b of a multiplied by log n. In the third condition, when fn grows faster than n power 2 log base b of a, and fn is the dominant growth term in comparison to the recursive term. Yes, that's what this regularity condition specifies. Then, the tight bound of Tn is theta of fn. To use the master theorem, you will start by comparing the growth rate between fn and n power 2 log base b of a, and determine which condition you are working with. After that, all you need to do is to plug in whatever the master theorem says. For example, this is a recurrence relation of the merge sort. To determine which condition this recurrence relation falls into, we will list the corresponding a, b, fn, as well as the growth rate comparison between fn and n power 2 log base b of a, like this. As you can see, a is equal to 2, b is equal to 2. Fn grows at the same rate as n power 2 log base 2 of 2, which is n power 2 1. So the recurrence relation of merge sort falls into the second condition. Okay? Because Fn grows at a linear time, and n power 2 1 also grows at a linear time. So the tight bound of the merge sort algorithm can be expressed as theta of n power 2 log base 2 of 2, then multiplied by log n, which is n log n. Let's see another example of the application of the master theorem, the binary search. The recurrence relation of the binary search is shown on the screen. We learned this from the part 1 lecture. To apply the master theorem to figure out its bound, we will list a, b, and the growth rate comparison between fn and n power 2 log base b of a, like this. In this case, a is 1, b is 2, log base 2 of 1 is 0, so n power 2 0 gives you a constant number 1. So fn also has a constant number c, grows at the same rate as constant number 1. As a result, you have case 2 again. So the tight bound of Tn can be expressed as is specified in condition 2, which is just a log n in the end, because the power of n is log base 2 of 1, which is 0. N power 2 0 gives you a constant number 1. When you multiply log n by 1, it's still log n. That's the second example of the application of master theorem. As you can see, its application is more blunt and direct than the recurrence tree method, but you will need to either memorize it, or you can refer to its definition somewhere if you want to use it. In this lecture, we used merge sort as a divide and conquer algorithm example to cover a generalized approach to time complexity analysis on all divide and conquer algorithms, the master theorem. We also compared the master theorem to the recurrence tree method. This lecture covers the time complexity analysis of Quicksort, and leads to the discussion on probabilistic analysis. Here's a roadmap of what we will cover. In this lecture, we will cover Quicksort as a sorting algorithm and conduct best and worst case analysis on Quicksort. The pseudocode of Quicksort algorithm is presented on the screen. Quicksort is an in-place sorting algorithm. It takes 3 parameters, the array, the first and the last index that defines a range of a subarray. The first thing the algorithm does is to check if the first index is smaller than the last index. If so, it will compute the index named split point by calling a method named partition. After that, it will split the array by the split point and call two recursive calls of Quicksort. The first recursive call comes with the arguments of a, the first index, and split point minus 1. The second recursive call comes with the arguments of a, split point plus 1, and the last index. In other words, the two recursive calls are on the left and the right subarrays of the split point. So from this line, we know that the partition method takes the same input as the quicksort algorithm and returns the index as the split point. But what does it do exactly? In short, the partition method uses the first element in A as the pivot value and moves all the elements smaller than the pivot value to its left side and all elements bigger than the pivot value to its right side. In the end, it returns the index of the pivot value. The partition method achieves that by using two pointers, L and R, to move the elements accordingly. Let's go over a concrete example to make sense of quicksort. So let's assume that the quicksort is being called on a given array as is shown on the screen. The first element in each subarray is always used as the pivot value. Well, by saying subarray, I'm not only talking about the subarrays, but I'm also talking about the original input array. So L and R here are the two pointers that are being used to move elements to either the left or the right sides of the pivot value. L is used to find an element that's bigger than the pivot. R is used to find an element that's smaller than the pivot. So how does that work exactly? As long as L is pointing to an element that's smaller than or equal to the pivot, it will keep moving it towards the right side. After that, as long as R is pointing to an element that's smaller than the pivot, it will keep moving it towards the left side. There are two scenarios when L and R both should stop moving. In the first scenario, L will be pointing at an element that's bigger than the pivot, and R will be pointing at an element that's smaller. In this case, it will swap the two elements pointed by L and R. In the other scenario, L will be at the right side of R. In this case, the job of the two pointers actually is finished, and you will do nothing but terminate this while loop. In the end, you will swap the pivot and the element pointed by R, so that the pivot element could sit in the middle. All the elements to its left side will be smaller than the pivot, and all the elements to its right will be bigger. Let's walk through this process. So initially, L will be pointing at 8. Since 8 is bigger than the pivot, so L has actually successfully found an element that's bigger than the pivot, and it will stick to its current position. R is pointing at 7, which is bigger than the pivot, so it will keep moving it towards the left side, like this. Now R is pointing to 5 now, which is still bigger than the pivot, so you will keep moving it towards the left. Now R points at 1, which is smaller than the pivot, so you should stop moving R as well. Next, you will swap the two elements pointed by L and R, like this. After that, you will start a new iteration of the while loop. In this new iteration, L is pointing to 1, which is smaller than the pivot, so it will move it rightward by 1 step. Now L points to 3, which is still smaller than the pivot, so you will keep moving it rightward. Now L points to 9, which is bigger than the pivot, so it should stop here. Then it comes to the turn of R. R currently points to 8, which is bigger than the pivot, so you will move it leftward by 1 step. Now R points to 9, which is still bigger than the pivot, so you will keep moving it leftward. Now L sits at the right side of R, so you will need to stop the while loop. At last, you will need to swap the pivot and the element pointed by R, like this. As you can see, now elements that are smaller than the pivot, they are all sitting to the left side of it, and the elements bigger than the pivot, they all sit to its right side. The partition method will return the index R, which is the index of the pivot. The returned index will serve as the split point for you to trigger 2 recursive calls of Quicksort. The first recursive call will trigger the Quicksort on the subarray at the left side of the split point, like this. This recursive call will trigger the execution of another partition method. The pivot of this subarray is 3. L and R both would be pointing to the element of 1. Since the element is smaller than the pivot, you will move L rightward by 1 step, like this. Now L will be sitting at the right side of R, so you need to stop the while loop and swap the element pointed by R and the pivot, like this. It's worth mentioning that all the operations happen on the same array, which is the original input array. This subarray with 2 elements 1 and 3 is merely a highlight instead of a deep copy. So you may also notice that whatever changes happen to this subarray also get reflected in the original input array. Again, Quicksort is an in-place sorting algorithm. Since the subarray to the left side of the pivot 3 is a single element 1, this recursive call ends here. Next, you will trigger another Quicksort on the subarray to the right side of this pivot, like this. The pivot of this subarray is 9. L will be pointing at 8 initially, which is smaller than the pivot, so you will keep moving it rightward, and it will stop when it is out of the bound, like this. R is already pointing to an element that's smaller than the pivot, so you won't move it at all. Since L is already sitting at the right side of R, the while loop will terminate. In the end, you will swap the pivot with the element pointed by R, like this. Quicksort will be triggered again on the left subarray of the new split point, the index of 9. In the end, the same process will happen, and the array will be fully sorted. Now you know how the Quicksort works to sort a given array in place. Let's analyze its time complexity. We will focus our attention on the partition method first. We went through a concrete example to figure out what happens in the partition method. It's about using and moving 2 pointers L and R, so that elements smaller than the pivot will be moved to its left side, and elements bigger than the pivot will be moved to its right side. This process is over when L sits at the right side of R. From the start to the end, the partition method traverses nearly every element in the subarray simply for 1 time, until when L sits at the right side of R. If we assume that the size of the subarray is n, the time complexity of the partition method is also n. We can express it as Tn is equal to C multiplied by n, where C is a constant number. We can also express its upper bound simply as a big O of n. With this knowledge, we can hide the partition method and focus our attention on the 2 recursive calls underneath the Quicksort. We will start by analyzing the worst-case scenario. When would the worst case happen? When the pivot is always either the smallest or the largest. Why and how? Let's use an example to demonstrate it. So you can find an input array A as a fully sorted array. When you call Quicksort on A, it will trigger a series of recursive calls. Each recursive call will only trigger another recursive call down the road instead of two. The reason for this behavior is that the pivot value of each subarray happens to be the smallest element. When the partition method is executed, elements are rearranged, which doesn't change anything, and the pivot value will stay where it always was. For example, in A, I'm talking about the example array that you see on the screen. 1 is the first and the smallest element, right? It's also the pivot. No elements will sit on its left side after the partition method is getting executed. For another example, 3 is the first and the smallest element in the subarray starting from index 1 till the end. 3 is also the pivot element in this subarray. When elements are rearranged in this subarray, no elements will sit on the left side either. As a result, each of the recursive calls of Quicksort will only trigger another recursive call on the subarray to the right side of the pivot, and the size of the subarray is only reduced by 1. So in the first call, the subarray is defined from index 0 to 6. In the second call, the subarray is defined from index 1 to 6. In the third call, the subarray is defined from the index 2 to 6. Although the subarray size is reduced gradually by one element each time, every recursive call will still execute its partition method, which runs on big O of n time, where n represents the size of the subarray. Based on that, the recurrence relation of the worst case, Tn is equal to T of n minus 1 plus C multiplied by n, where C is a constant number. The n and n minus 1 represents that the subarray size is only reduced by 1 in each of the sequential recursive calls. And C multiplied by n represents the work required by the partition method at the current step. Based on that, we can draw the tree-like structure between the sequential recursive calls. Similarly, we will draw the relationship between the subproblem size in the left column and the work required at each step in the right column. Initially, the problem size is n, and at this step, the partition method takes C multiplied by n time to get executed. So the first row will have n and Cn. This step will trigger another recursive call on the subproblem whose size is n minus 1. And this recursive call will take C multiplied by n minus 1 time in its corresponding partition method. So you have n minus 1 and C multiplied by n minus 1, like this. I also added the left subtree that comes with a problem size of 0, so that you know it ends here. The subproblem with the problem size of n minus 1 will trigger another recursive call whose problem size is reduced further by 1, so that's n minus 2. And the corresponding time to address the work at that step will be C multiplied by n minus 2, like this. The same pattern will hold until the subproblem size becomes 1. At each level, the subproblem size is reduced by only 1, like this. In the end, to calculate the time complexity function, all you need to do is to add up all the time it takes to do the work at each step, which gives you this. That will be Tn is equal to C plus 2C plus 3C plus all the way to C multiplied by n. You can extract the constant number C like this. When you sum up everything from 1 to n, you will end up with a square function. If you're not so sure, you can either refer to a generative AI tool on how this is calculated, or you can refer to our prior lectures. We covered this in the past. So the result will give you n squared divided by 2 plus n divided by 2. That said, the upper bound of this time complexity function is big O of n squared. It's everything about the worst case analysis of the quicksort algorithm. Now, let's move to the best case analysis. So what input array will lead to the best case scenario? If you have an input array whose pivot is always the middle element, it will end up with the best case. So what does that mean? Let's use an example to demonstrate it. Assuming that we have an array like what you see here on the screen, we always use the first element as the pivot. And the pivot will always be the middle element when you finish rearranging elements by executing the partition method. For example, 4 is the pivot element of A. When elements are rearranged at this step, 4 will sit in the middle. There would be 3 elements to its left and another 3 elements to its right. The quicksort on A will further trigger 2 quicksort being called on the left and the right subarrays. In the left subarray, 2 is the pivot, which will also end up in the middle after its corresponding partition method is executed. The same thing can be said for the right subarray. The pivot 6 will end up in the middle after its corresponding partition method is executed, like this. That said, every pivot is the middle element of its corresponding subarray, and every quicksort will trigger 2 more recursive quicksort on its subarrays. When recursion is triggered, the problem size is actually halved, as what you see from this example. So the recurrence relation will be Tn is equal to 2 multiplied by T of n divided by 2 plus C multiplied by n, where C is a constant number. The first 2 here represents the 2 recursive calls, and the n divided by 2 represents the halved problem size in the next step of the recursion. C multiplied by n still represents the amount of work that needs to be done by the partition method at the current step. Now we have the recurrence relation. Let's turn it into a recurrence tree. The initial problem size is n, and the time it takes to do the work at this step is C multiplied by n. Okay? In the next step, 2 recursive calls will be triggered, and both will have their problem size halved, so that will be n divided by 2. It takes C multiplied by n divided by 2 to do the work at this corresponding step, and the total time will be the sum of the 2, which is still C multiplied by n, like this. Okay? In the next step, each recursive call will trigger 2 more recursive calls separately, and the problem size will be further halved. In other words, there will be 4 recursive calls in the next step. Each will take C multiplied by n divided by 4 to do the work at this step, and the total time will be a sum of all of them, which is still C multiplied by n, like this. So this process will continue, and the problem size will keep being halved until it becomes 1. However, the time it takes to do the work at each step, I'm talking about the total time, it remains C multiplied by n. To figure out the time complexity function, all it takes is to add up all the time it takes to do the work at each step, which is Cn multiplied by the height of the tree. This is a problem that should be familiar to you if you have watched the prior lectures on the divided and conquer. How many times can you keep up dividing n by 2 until it becomes 1? The answer to this question manifests the relationship between the problem size n and the height of the tree h. So the key will be the solution to this problem. 2 power to h is equal to n. When you apply logarithmic to both sides, you will calculate h as log of n. That said, Tn will be equal to Cn multiplied by log n, which means that the upper bound of the best case is n log n. Okay? In this video, we covered the details of the quicksort algorithm and its worst and best case time complexity analysis. In the next video, we will cover the average case analysis of quicksort and a variation of quicksort algorithm, the randomized quicksort. We will use such topics as a vehicle to discuss and cover probabilistic analysis. This lecture covers the probabilistic analysis of algorithms. Here's a roadmap of what we will cover. In this lecture, we will conduct the average case analysis of quicksort and use it to discuss the probabilistic analysis. After that, we will cover a variation of quicksort, the randomized quicksort, and use it to deepen your understanding of probabilistic analysis. In the Part 1 lecture, we covered the quicksort algorithm, the worst case time complexity analysis, as well as the best case analysis. In this lecture, we will start by covering the average case time complexity analysis of quicksort. On the screen, you can see and compare the two recurrence tree structures of the worst and best cases. As you can imagine, the time complexity of the average case will be somewhere between the two. By saying that, I mean the upper bound of the average case should be bigger than or equal to the best case and smaller than or equal to the worst case. Given an arbitrary array as the input, it's highly unlikely that the array has the characteristics that fits in either the best or the worst case. There's some randomness being involved. To account for the randomness, we need to approach analyzing the time complexity of the average case a little bit differently. We would call this approach the probabilistic analysis. A comparison between the time complexity that you are familiar with and the probabilistic analysis is listed on the screen. The regular time complexity analysis, as you already know, doesn't assume randomness in the input and focuses on defining the characteristics of the input so that we will have the best, worst, and the average cases. In contrast, probabilistic analysis focuses on using the expected performance over all possible random outcomes to account for the randomness in the input. The one thing that we need to highlight here is the expected performance. It's a probability concept that we may need to refresh your memory on. In fact, there are three concepts that I want to make sure that we are all on the same page, including the uniform distribution, expectation of a random variable that's used to measure the expected performance, and the linearity of expectation. Let's go through them one by one. So what's uniform distribution? A random variable x is said to follow a uniform distribution if all outcomes are equally likely to happen. For a random variable x taking n discrete outcomes, assuming that each would happen with equal probability, then the probability will be 1 divided by n. Let's use an example to demonstrate the concept of uniform distribution. When you roll a fair 6-sided die, the possible outcome ranges from 1 to 6, right? Because it's a fair die. So the probability of the die landing on any side is the same, which is 1 divided by 6. Okay? The next concept is the expectation of a random variable. We mentioned that it's used to measure the expected performance of randomness. So how is that really defined? The expected value of a random variable measures the central tendency that the random variable takes. So it's a weighted average of all possible outcomes, where the weights are the probability of those outcomes. The way to compute the expected value is to sum up a set of terms. Each term is the product between the random variable and its corresponding probability. Let's see a few examples of expectation. The first example is still about rolling a fair 6-sided dice. The expected value of this action is computed as 3.5. How is that done? So you will sum up a set of terms, and each term is the product between a random variable, or say the outcome, and its corresponding probability. In this case, the probability of each outcome is the same. It's 1 divided by 6. The ending result is computed as 3.5. Okay? For another example, let's think about buying a lottery ticket. Assuming that the ticket has a 1% chance of winning $100 and 99% of winning nothing. The expected value of this scenario is the sum of the two terms. The first term is the product between 100 and 1%, and the second term is the product between 0 and 99%. So the ending result is simply 1. From these two examples, you can see that the expectation is computed as a weighted average of all possible outcomes, where the weights are the probabilities of those outcomes. That's how you measure the expected performance of randomness, which will be critical for us to account for the randomness of the pivot value given an input array for the quicksort algorithm. So the last concept we need to refresh your memory on is the linearity of the expectation. Just to be sure, the expectation here is exactly the same concept as we just discussed. It's computed as the weighted average of all possible outcomes. So the linearity of expectation is defined as the following. The expectation of a sum of random variables is equal to the sum of their expectations. For example, if you have two random variables x1 and x2, the expectation of x1 plus x2 is the same as summing up the expectation of x1 as well as the expectation of x2. Additionally, you may also want to know how to deal with the constant number that's multiplied to your random variable. For example, if you have a constant number c, then the expectation of c multiplied to x1 is a random variable, so this expectation is equal to c multiplied by the expectation of x1 itself. In short, you can extract the constant number out of the computation of expectation. Let's see an example. So this time, you're rolling two 6-sided dice. Of course, each dice is a fair 6-sided dice. If we use x1 and x2 to represent the outcomes of the first and the second dice respectively, we will be able to know that the expected value of both dice are the same, which is 3.5. This is the same thing as we just computed. The possible new thing here is the expectation of x1 plus x2. Well, that's equal to the sum of the expectation of x1 and the expectation of x2, which will give you 7. Now you know the three probability concepts. We will see their application in how we go from the recurrence relation to the time complexity function for the average case of quicksort. Instead of deducing the recurrence relation of the average case from scratch, I'm going to give it to you and try to make sense of it together. So here is the recurrence relation of the average case for quicksort. Same as all other recurrence relations, a recurrence relation is composed of two parts. They work down at the current step, and they work down in the recursive step. The n-1 here represents the time it takes to execute the partition method at the current step. From the part 1 lecture, you know that the partition method, as a helper method to the quicksort, traverses the input array for one time, so it takes linear time to get the job done. The other clumsy term represents the time it takes in the next step when the recursive calls are triggered. It is the expected value of the cost of the recursive calls. An obvious question that you may ask here is where the k comes from, or what is that? Well, the k represents an arbitrary position in the range between 0 and n-1. The position k here is the split point, or say the index of the pivot, after the partition method is executed. In case if you don't know what I'm talking about, you need to refer to the part 1 lecture. So where do you think the split point will land? Anywhere? Yeah, anywhere. Each of the n positions can potentially become the split point because we assume that the input array is randomly ordered. As a result, the possibility of the split point landing at the particular index k is equal to 1 divided by n. That's where the 1 divided by n comes from here. Next, what about t of k plus t of n minus k minus 1? What does that represent? Well, you know that k represents an arbitrary split point. If you execute the quicksort algorithm, what you will do next when you get a split point? You will trigger two recursive calls. One on the left subarray of the length of k, the other on the right subarray of the length of n minus k minus 1. Okay, so t of k here represents the time it takes to run quicksort on the left subarray. And similarly, t of n minus k minus 1 represents the time it takes to run quicksort on the right subarray. If k happens to be at the middle point, you will end up with 2 t of n divided by 2, which you have already encountered when we covered the best case time complexity analysis of quicksort. To account for the randomness, one thing that we need is the arbitrary position k. Okay? The other thing is how to represent the time it takes to trigger the recursive call. We used the expected value here to do so. The expected cost, or say the expected time it takes in the recursive call, is computed in the same way as other expected values by adding up a set of weighted terms. Each term is the product between the probability of the split point landing at index k and the time it takes to run the recursive calls on its left and right subarrays. Okay? The probability is the weight whose value is 1 divided by n for each random variable k. In relation to the term of expected value dominated by k, 1 divided by n is a constant number, so you can extract it and multiply it to the summation. That's why there's a difference between what you see in the recurrence relation and what you see at the bottom of the screen. The two terms are interchangeable. Now you know what the recurrence relation is composed of for the average case of the quicksort. How do we get from here, the recurrence relation, to its upper bound? Besides the recurrence tree method and the master theorem, we will attempt a new method here that's called the substitute method. Different from the recurrence tree method and master theorem that we covered in the past, the substitute method starts by making an educated guess on the upper bound, and then moves to prove the guess via induction. For example, given the recurrence relation of the average case for the quicksort we just covered, we can make an educated guess, which is the upper bound of the corresponding time complexity function is big O of n log n, expressed as Tn. The time complexity function is smaller than or equal to C, which is a constant number multiplied by n log n. Okay? So that's the first step in using the substitute method. The second step is to prove this guess via induction. If we can prove our guess is true, then we will be able to establish that the upper bound is simply big O of n log n. If we can't, we need to go back to step 1 by making a new guess. The key here in using the substitute method is induction. In case if you forget what it is, here's a common example that can help refresh your memory. Let's forget about the average case upper bound for now, and focus on this example on the screen. Okay, it's all about induction. Assuming that we made a guess, and want to prove this math formula, Sn, defined as the sum from 1 to n, I mean 1 plus 2 plus 3 plus all the way to n, where Sn is equal to n multiplied by n plus 1, then divided by 2. We want to prove that this formula holds for all the numbers of n, and we will do so by using induction. There are 3 steps that are involved in this process. Similar as what you do for recursion, you need to prove the formula holds for the base case first. For example, when n is small enough, and so the case becomes very trivial. When n is equal to 1. Sn, or say S1, can be expressed as n multiplied by n plus 1, then divided by 2. You can simply replace all the n's with 1, and you can easily tell that, well, this formula holds for the scenario when n is trivial enough, when n is equal to 1. The next step is to assume that the given formula holds for an arbitrary given number k, so that in the third step, you can prove that when the arbitrary number is 1 unit bigger, the formula still holds. In other words, you need to prove that S of k plus 1 is equal to k plus 1 multiplied by k plus 2, then divided by 2. You will get the job done by using the assumption you have established in step 2. Essentially, S of k plus 1 is equal to S of k plus another unit, which is simply k plus 1. Based on the assumption you have established in step 2, Sk can be replaced with k multiplied by k plus 1, then divided by 2. All it remains is to build a connection between these 2 steps. I'm talking about these 2 steps, or say, prove that they are equivalent to each other. In short, induction involves these 3 steps, starting with proving the base case. Then assume that the claim is true for an arbitrary number. In the end, you need to prove that the claim holds when the arbitrary number is increased by using the help of the assumption. For our case, I mean the upper bound for the average case, will be very similar. The first step is about proving the statement holds. In the base case, when n is equal to 1, the array size is 1, so the quicksort doesn't even need to run at all. So t of 1 will be smaller than or equal to 1 multiplied by log 1, which is also 1. So that said, the base case is proved. The second step is to assume the statement holds for an arbitrary input size such as k. As we do that, we will also try to simplify the recurrence relation a little bit by assuming that k and n minus k minus 1 tend to have similar sizes, considering that it is rare for either the best or the worst cases to happen frequently, so that the expected value term can be simplified to 2 divided by n, and then multiplied by the sum of tk, where k ranges from 0 to n minus 1. We will assume that when the input size is an arbitrary number k, we have t of k that's smaller than or equal to c multiplied by k log k. Okay, that's the second step. The third step is to prove that the statement holds, based on the assumption that we just assumed at this step. We already have the simplified recurrence relation between Tn and Tk. The recurrence relation provides a way for you to know how input size increases as recursion is triggered. It goes from k to n, where k is an arbitrary number between 0 and n minus 1. Beyond that, we have the help from the assumption that we made at step 2. Tk is always smaller than or equal to c multiplied by k log k. When we plug the assumption into the simplified recurrence relation, I mean to replace t of k with c multiplied by k log k, you will have a Tn that's always smaller than or equal to n minus 1 plus 2 divided by n, then multiplied by the sum of ck log k. If you still remember what you learned from calculus, You will know that the summation term can be approximated to its corresponding integral. Based on that, you can calculate its antiderivative as is shown here. K is an arbitrary number between 0 and n-1. As such, this term is going to be smaller than its counterpart, in which K is replaced with n. These concepts in calculus are beyond the scope of this lecture. If you forget what you learned or need to catch up with calculus, you can search for integra and antiderivative or ask a relevant question to a generative AI tool. That said, this step allows you to replace the summation term with the antiderivative where K is all replaced with n. Like this. Now, Tn is smaller than or equal to this formula, where K is all replaced by n. After some basic calculation, you can get rid of the constant number c, and deduce that Tn will be smaller than or equal to n log n. In other words, we have proved our guess via the induction method. The upper bound of this time complexity is big O of n log n. Given a randomized input array, the average case of Quicksort runs on big O of n log n. Note that the assumption of a randomized input array is important, because it means that hitting the best or worst cases would be very rare. However, if the input array is not randomized, the weakness of Quicksort is still noticeable, because the pivot is chosen using a deterministic approach, such as always going with the first element or the last element. If the input data is already sorted or nearly sorted, a deterministic pivot selection can lead to highly unbalanced partition, resulting in the worst case. So that's where the randomized quicksort algorithm comes into play. And that's exactly our next topic. Randomized quicksort aims to minimize the chance of hitting the worst case of quicksort when the input array is not ideal. So what does randomized quicksort do? Well, it does everything the same way as the regular quicksort algorithm, except for randomly selecting all the pivots. You can implement it in many different ways. One possible approach is to randomly select an element in the subarray and then swap it with the first element. After that, you can stick to using the first element as a pivot. If you go with this approach, you only need to change a few lines of the pseudocode in the implementation for the regular quicksort that we have shown to you. So this is the implementation of the regular quicksort, where the first element is used as the pivot. To change it to randomized quicksort, you will randomize the pivot every time as the first thing to do in the partition method. The helper method, named randomize, will choose an element randomly in the subarray, then swap it with the first element. The remaining code will stay exactly the same. The algorithm itself is not hard to grasp. What's the time complexity of the randomized quicksort? Instead of doing the analysis by tracking all the details, we will distill its time complexity to the expected number of comparisons performed by the algorithm. Why can we do that? Down to its core, randomized quicksort is still about comparing the pivot to every other element in every recursive calls. That said, the main computational cost in quicksort arises from comparing elements to the pivot during the partition process. In case you forget, this is the pseudocode of the randomized quicksort. The process of randomly picking an element and then swap it with the first element costs constant amount of time. So that said, the biggest cost comes from this partition method here, in which you compare the pivot to every other element in each of the subarrays when quicksort is triggered recursively. Okay. Because the main computational cost in quicksort comes from comparing elements to the pivot during the partition process, Focusing on just analyzing the comparisons avoids the need to explicitly tracking other details of the algorithm. Given these reasons, if we can figure out the number of comparisons performed in randomized quicksort, we will be able to establish the total runtime because the total runtime of quicksort is proportional to the number of comparisons performed. Remember, we are still dealing with the expected number of comparisons. The emphasis should be on the expected number that accounts for the randomness nature of this algorithm. To get the expected number of comparisons, we need to figure out a few things. The first is the probability of the comparison between two arbitrary elements in the input array. Let's use I and j to represent the two indexes of the two arbitrary elements. For the two elements to be compared, they need to be in the same subarray, and either of the two needs to be selected as a pivot. For a subarray to contain both elements at index I and j, the subarray needs to at least start from I and end at j. To express the probability of this scenario, we can use a formula like this. The probability of this scenario can be broken down into two different probabilities. The first is when element I is selected as a pivot, and the second is when element j is selected as a pivot. In the subarray starting from I and ending at j, each element stands the same chance to be picked as a pivot. So the probability of picking element I will be simply 1 divided by j minus I plus 1. The same thing can be said for the probability of picking element j. And just to be sure, j minus I plus 1 represents the size of this corresponding subarray. As a result, the probability of this scenario can be computed as 2 divided by j minus I plus 1. Here, we used some concepts from probability theory, in case you never learned or forget such things. You can search addition rules for disjoint events, or you can read more about it, or ask a relevant question to a generative AI tool. In short, when two events A and B are mutually exclusive, the probability of either A or B happens is equal to the probability of A plus the probability of B. The probability is a vital part in computing the expected number of two arbitrary elements being compared in a given array. Next, the expected number of comparisons. We need to figure out the total number of pairs composed of two arbitrary numbers at index I and j. Why do we need that? Remember, the expected number is computed as the following. It is the sum of a set of terms, and each term is a product of a random variable and its corresponding probability. The random variable here is simply always 1 because it represents the event of comparing two numbers. It doesn't have different values. We have figured out its corresponding probability already. All it remains is how many pairs there are, or say how many possible combinations of index I and index j there would be, given an input array. If you remember what you learned from the set theory, you may know that the total number of pairs can be computed by multiplying n with n minus 1, then divided by 2, assuming that the total number of elements is n. You can also express this mathematically. All it takes is to pick an arbitrary element from the input array first, then after that, pick another arbitrary element from the remaining elements. This can be expressed as a combination of two summations, like this. The outer summation iterates over all possible starting indexes of I, which starts from 1 and ends at n minus 1. The n minus 1 accounts for the pick of the next element j. The inner summation iterates over all possible sizes of subarrays starting at I plus 1 and ending at n. You can also think this combination of the two summations as an embedded for loop. So the outer for loop corresponds to the outer summation that iterates from 1 to n minus 1, and the inner for loop corresponds to the inner summation iterates from I plus 1 to n. Like what you see here in this box. The two summations compute to the same number as the total number of pairs, or say the embedded for loop run at the same amount of steps as the total number of pairs. It's just a different way of expressing the same thing. Now you have everything you need to compute the expected number of comparisons. The result looks like this. Here, we use C of n to represent the expected number of comparisons in relation to the input size of n. T of n is in proportion to C of n. So as soon as we figure out the upper bound for C of n, we will know that the upper bound for Tn. Let's get started. The first thing that we will do is to simplify C of n. I mean, to replace j minus I plus 1 simply with k. J minus I plus 1 represents the size of the subarray that contains elements at index I and j. The simplification allows us to use k to represent the size of the subarray. Next, we will approximate the inner summation using the harmonic number. In short, the inner summation is approximated as log base of natural number of n minus I plus gamma, where gamma is a constant number. The constant number can be easily dismissed when our goal is to figure out the upper bound. That said, the inner summation can be replaced by log base of natural number of n. The outer summation can be simply replaced with n multiplied by whatever comes out from the inner summation. As a result, C of n can be expressed as n multiplied by log n. In case if you don't know or forget the harmonic number is defined like this. The nth harmonic number is defined as 1 plus 1 divided by 2, then plus 1 divided by 3, and plus all the way until 1 divided by n, which can be approximated to log base of natural number of n plus gamma, where gamma is a constant number. You can read more about harmonic number or ask relevant questions to a generative AI tool in case if you have never learned it. Okay? Now we have the approximation for C of n. Given that T of n is in proportion to C of n, and log base 2 of n grows at a faster rate than log base of natural number of n, so that we can replace the base of natural number with the term that we are more familiar with to derive the upper bound as n multiplied by log n. That said, the upper bound of randomized quicksort is n log n. The randomization process basically rules out the likelihood of the worst or the best cases from happening. Due to its nature in randomness, we have to resort to the expected value to represent its time complexity. In this lecture, we covered the average case time complexity analysis for quicksort and the randomized quicksort, as well as its time complexity analysis. We introduced a new method to derive bounds, especially the upper bound of a given algorithm, which is the substitution method. Most importantly, we introduced the probabilistic time complexity analysis that uses the expected number to account for randomness. That's all we have, and I hope you learned something new. This lecture is on heapsort, and their time complexity analysis. Here's a roadmap of what we will cover. In this lecture, we will start by discussing the application scenario of heaps, or say where heaps can be useful. After that, we will cover the basics of the heaps. All heaps are binary trees, so heaps share many of the important properties of binary trees. Let's get started. Where can heaps be useful as a data structure, or say as a tool? You might have played one, two, or many games. Many of such games have millions of players, and also have leaderboard, like this one that you see on the screen. How do you track the top K players? Remember, there are millions of them, and their scores may change. There might be new players all the time, and those who decided to delete their accounts. In such a scenario where there are a lot of dynamic changes happening to the elements that need to be sorted, the sorting algorithms that we have covered may not be the best options, such as the merge sort or the quicksort. And a scenario like this is where a heap shines. In summary, when you need to perform sorting with incomplete data, or when there are constantly newly added elements, or old elements being deleted, yet you still need to perform sorting task, you should think about heaps. That's a quick overview of where heaps can be useful. Let's move to cover the data structure. As we get to the details, you will understand better why heaps are a good choice for sorting in a dynamic changing scenario. First thing first, let's cover the basics of binary tree in case your memory blurs or you have never learned it elsewhere. So for binary tree, we need to make sure that we are on the same page in terms of these concepts, including node, root, and leaf. What's a node? A node is a fundamental unit of a binary tree. It contains data, or say a value, and references, or say links, to its left and the right child if there are any. Other circles with values that you see on the screen are representations of nodes. So what's a root? The root is the topmost node of a tree structure. It is the starting point for accessing any other node in the tree. A tree can only have one root. In our example, the node with the value of 10 is the root node. So what's a leaf? A leaf node is a node that has no children. In other words, both left and right of that particular node should be null. A leaf node is an endpoint of a branch in the tree. In our example, all the highlighted nodes are leaf nodes. As you can see, they have no children. Based on the three concepts, let's define binary tree. A binary tree is a tree data structure in which each node has at most two children, usually referred to as the left child and the right child. Particularly, there is a special type of binary tree that's highly relevant to our discussion of heaps, because all heaps are complete binary trees. So what makes a binary tree a complete one? In a complete binary tree, all levels are completely filled except for the last level, which is filled from left to right, for example. This is a complete binary tree because all levels are completely filled. For another example, this is also a complete binary tree. As you can see, the last level is not fully filled, but it is filled from left to right, so it is a complete binary tree. Similarly, this is also a complete binary tree. Although its last level is barely filled with any nodes, just one node with a value of 3, which is on the very left side. However, the last level is indeed filled from left to right, so it is a complete binary tree. However, a tree like this is not a complete binary tree. It is still a binary tree, but not a complete one. It has 3 levels, but its second level is not fully filled. Now you know what's a complete binary tree, and you have everything you need to move on to learn about the definition of heaps. So what's a heap? First, a heap is a complete binary tree. Second, there are 2 types of heaps, max heap and min heap. In a max heap, the value of a parent node is always bigger than its children. In a min heap, the value of a parent node is always smaller than its children. In this lecture, we will focus on max heaps. As long as you understand everything about the max heap, you will have an equally strong grasp of the min heap. Both max and min heaps have the same basic operations, same time complexity, and serve similar purposes. So let's use an example of max heap to understand it better. An example of max heap may look like this. The root node has a value of 10, and every parent node is bigger than its two children in this heap. There are 3 levels in this max heap, and we count that downward, starting from the root node. This is merely a visualization of a max heap. A max heap is typically not stored in a tree structure like this. Instead, it is stored in a linear data structure like an array. How does that work? Let's prepare an array. The size of this array is equal to the number of nodes as you see in this tree on the left side. How do we use an array to hold all the values of a heap? We will place the values of a heap level by level, and from left to right. 10 is the value of the root node, so we place it at index 0. That's everything you have at level 1. At level 2, you have 2 values, 7 and 5, so we place them at index 1 and 2 in this array, like this. Then, you can move to level 3. The remaining 3 values go to index 3, 4, and 5, like this. Using an array to store a heap's value is convenient, but also puts an extra requirement on us. In a binary tree structure like this, given an arbitrary node, it's easy to tell which node is its parent and which node is its child. However, it's not so easy to do in an array. That said, you need to figure out the relationships between indexes of a node, its parent, and its children. We can deduce and generalize a relationship with a few examples. If you focus your attention on the node sitting at index 1, that's a node with a value of 7. Its parent is a node of value of 10 that sits at the index of 0. It has 2 children. The left child is 3 at index 3, and the right child is 6 at index 4. So we can map these values here, like this. What's the relationship between these indexes? It definitely involves subtracting 1 when it goes from a node to its parent. It may involve multiplying by 2 when it goes from a node to its child. Let's look at another example. The node at index 2 has a value of 5. Its parent is a node with a value of 10 at index 0. It only has a left child 4 whose index is 5. It doesn't have a right child, but if it does, the index of its right child will be 6. So we will add the indexes here. From this example, we can modify our guesses. In addition to subtraction by 1, it may actually involve a division by 2 to derive the parent node's index. 2 minus 1 will get you 1, but 1 divided by 2 will get you 0 if you limit your calculation to only integers. To get the index of the left child, you can do 2 multiplied by 2, then plus 1. To get the index of the right child, you can do 2 multiplied by 2, then plus 2. Let's look at another example to verify our guesses. If the given node is 3 at index 3, its parent node's index will be 1. It doesn't have any children. Let's assume that the heap will grow to the extent so that it now has 2 children. That will be here and here, and their indexes will be 7 and 8, like this. Given the node at index 3, if we subtract it from 3, then divide by 2, we will get 1, which is the same as the index of its parent node. If we multiply 3 by 2, then plus 1, we will get 7, which is the same as the index of its left child. If we multiply 3 by 2, then plus 2, we will get 8, which is the same as the index of its right child. That said, our guesses on how to derive the indexes of the parent and 2 children is largely correct. You can move on to prove this via induction if you want. You can also verify this by referring to an external resource or a generative AI tool. We will skip the proof part here and jump to its generalization directly. When we use an array to store the data of a heap, given an arbitrary node at index I, the index of its parent node is I minus 1, then divided by 2. The index of its left child and the right child are 2 multiplied by I plus 1 and 2 multiplied by I plus 2, assuming that it has 2 children, of course. This knowledge is important because it allows you to navigate around and go from one node to its parent, or left or right child using indexes. This knowledge will support us when we cover the basic operations of a heap. Beyond the mapping from a tree-like structure of a heap to an array, there are 3 features of a heap that you may want to know. They are very important when it comes to analyzing the time complexity of the heap operations. First, the relationship between the number of nodes and the height of a heap. Given a heap, if we assume that its leaf level is fully filled, the height of the heap, h, and the number of nodes n can be expressed as h is equal to log n. You might have already seen this in the past, and this is something that you can prove via induction. We won't be doing it here, but we can show you a few examples that will lead to the induction. When the number of the nodes is 3, the heap height is 2. Log 3 is about 1.6, which is almost 2. When the number of the nodes is 7, the heap height is 3. Log 7 is 2.8, which is almost 3. When the number of nodes is 15, the heap height is 4. Log 15 is 3.9, which is almost 4. You get the idea. Second, given a heap, if we assume that its leaf level is fully filled up, the relationship between the number of nodes at the leaf level is in proportion to the number of the total nodes at a fixed rate. In short, if there are n nodes in total in a heap, the number of nodes at the leaf level can be estimated as n divided by 2. You can prove this via induction if you want. More than that, you can further generalize this pattern to the number of nodes in other levels. If you go from the leaf level to the root gradually, level by level, the leaf level contains roughly n divided by 2 number of nodes. The second bottom level contains roughly n divided by 4 number of nodes. The third bottom level contains roughly n divided by 8 number of nodes. When you go up one level, you can estimate its corresponding node numbers at that level by further dividing n by 2. Intuitively, this pattern tells you that the majority of the nodes are near the leaf level in a heap. The leaf level contains 50% of all the nodes. The 2 bottom levels contain nearly 75% of all the nodes. In this video, we discussed where heaps can be applied, we covered binary tree, and introduced you to the concept of heaps, including how to store the data of a heap in an array, as well as some basic patterns of a heap. In the next video, we will cover the basic operations of heaps, including the insert and the pick method. This video is on heap, heapsort, and their time complexity analysis. Here's a roadmap of what we will cover. In this video, we will cover 2 basic operations of heaps, including the insert and the pick methods. After we cover each method, we will also go over its time complexity analysis. Let's get started. To simplify our discussion, we will stick to max heaps, instead of switching between max and min heaps. In case you forget, in a max heap, the value of a parent node is always bigger than its children. Before we get to the basic operations of heaps, we need to do some preparations first to set up the implementation. We will prepare a class to represent the max heap. Under this class, we will define the heap size in a variable m, and use it to further define and declare an empty array named data. This array will be used to store the data of the heap. The 2 basic operations will be simply 2 functions under this class, I mean the insert and the pick methods. The insert method aims at adding a new data point to the heap while maintaining the property of a heap. So what property? In a max heap, a parent node is always bigger than its children. When you add a new data point to the heap, you may break this property. So the insert method doesn't only add a new data, but also restores this property in case if it is broken. There are 3 steps involved in inserting a new data point to a heap. First, you will add the new element to the bottom level of the heap, or say the end of the array named data. For simplicity, let's just assume this step is easy to do. We won't worry about whether the data array is mutable or not, or whether it's full or not. We simply would assume that it's mutable and this array named data has plenty of space for you to insert new elements into it. Second, you need to compare the added element with its parent. If they are in the right order, your job is done. If not, you will have an extra step, which is to swap the element with its parent, and then repeat the prior steps, because the new element may still be too big and needs to be further bubbled up, which involves more swapping. Let's use an example to make sense of this. Let's focus on the heap sitting on the left side of the screen, and we will add a new element with a value of 11. As you can see, 11 is added to the end of the array named data, as it's visualized here in both of the array and the above heap. So step 1 is done. As it stands now, the parent of the newly inserted element 11 is 5. So the max heap property is broken. That means we need to move to step 3 by swapping 5 and 11. So the newly inserted element 11 goes from the leaf level to the second bottom level, or say from index 6 to 2. Now we will still focus on this newly inserted element and its new parent, which is 10 now. 11 as a child is still bigger than its parent 10, so we need to swap them, like this. And now 11 becomes the new root, which has no parent anymore, so we would stop here. One thing worth pointing out is that this tree structure you see here is merely a visualization, and the actual data is all stored in the array below the tree. As we do the swapping in the tree, we are actually swapping the elements in the array. The corresponding algorithm of this process is shown on the screen. For simplicity, we made some assumption to make this method easy to implement. Most importantly, this method as it stands now only deals with integers. If you wanted to deal with strings or objects, the comparison mechanism may need some customization. Under this assumption, the insert method takes a number as a single parameter and adds it to the end of the array. After that, it starts the process of comparing the newly inserted element with its parent. There are 2 things worth noting. First, the process of iterative comparison between the newly inserted element and its immediate parent is under a while loop, just in case you need to keep bubbling up the element for more than one time. If the parent is ever bigger than this newly inserted element, it means that the heap property is kept or restored, so you will break out of the while loop. Second, you rely on the generalized relationships among the indexes of a given node, its parent, and children to perform the swaps. For example, given the newly added element index as I, then the index of its parent can be calculated as I minus 1, then divided by 2. When the new element is bigger than the parent, we perform the swapping and bubble up the new element by updating the counter I. So what's the time complexity of this method? We will discuss its best, worst, and average cases one after another. The best case is relatively trivial. When you add a new element, and the element happens to be smaller than its immediate parent. In other words, the newly added element stays where it is added. For example, if you look at the heap on the left side, when you add a new element, such as 5, like this. 5 is smaller than its parent 10, so everything is alright, and the heap property is maintained. That means we will stop here. The time complexity of the best case is bigger than 1. What about the worst case? The worst case happens when you add a new element that's bigger than the root. For example, if we add 11 to the heap sitting on the left side, 11 will need to be iteratively bubbled up until it is swapped to the root level. In other words, it needs to be bubbled up for as many times as the height of the heap. What's the relationship between the number of nodes and the height of a heap? This is one of the features that we studied in the past. If a heap contains n nodes, the height can be estimated as log n. In the worst case, the insert method needs to perform swaps all the way from the leaf level until the newly inserted element becomes a new root, which means that there are log n number of swaps. That said, the time complexity of the worst case is log n. Okay? Now let's think about the average case for the insert method. The proper way to conduct the average case time complexity analysis typically involves calculating the expected value, and that's how we account for the randomness, and exactly what we will be doing here. To achieve a fair estimate of the average case time complexity, we will calculate the expected number of swaps that are required to achieve the insert task. Why? The time complexity Tn is in proportion to the expected number of swaps. So instead of involving all the nuances in calculating the time complexity function, we will simplify that to the expected number of swaps. There are different ways to calculate this expected value. We will go with the simplest approach and pick the random variable here as the event when the inserted element is being swapped at each level. So that's a constant number 1. This event may or may not happen at each level. If it happens, that's a 1. If it doesn't happen, that's a 0. Beyond that, we will see the bottom level or see the leaf level as level 0, and the second bottom level as level 1. And the level number increases as we gradually move from the leaf level to the root. The probability of the event of swapping is something worth a detailed discussion. To figure out what the probability or say the pattern of the probability is, we need to clarify some assumptions first. A key assumption that we will have here is that the newly inserted element is arbitrary and random. As a result, when it comes to comparing this newly inserted element to any element in this heap, the chance that the newly inserted element is bigger is always 50%. However, you're not just doing one-time comparison between the newly inserted element and another element in the heap. You're doing it level by level, which means that each level is an independent incident. If you can just focus on the example shown up here on the screen. The first comparison and a possible swap happens here at level 1. The chance of a swap happening here is 50%. I mean, a swap only happens when the newly inserted element is bigger. That's 50%. This is the first comparison between the newly inserted element and any other element in the heap. The second comparison happens here at level 2. If you get the opportunity to do this comparison, that means you have already performed a swap at level 1. And you have to account for that in your probability calculation. Based on the product rule, the probability of a swap happening at this level, I mean at level 2, is 50% multiplied by 50%, which will give you 25%. The first 50% is how you account for a possible swap that may or may not happen at the prior level, or say level 1. This example only has 3 levels. If you have a heap of h level where h is a big number, we can generalize this probability pattern. It's worth noting that the leaf level is our level 0. As it goes up, the second bottom level is level 1, then level 2, As you go up to the root, the level number increases. Then we will say that at an arbitrary level I, the probability of swapping is 1 divided by 2, then power 2i. Meaning that you need to multiply as many 50% as there are in all the previous levels to account for swapping happening in all those levels. With the 3 things set up, you're ready to calculate the expected number of swaps. The formula to calculate the expected value is always the same. It is the sum of all random variables multiplied by their corresponding probability. When you plug in what you derive on the random variable and its probability pattern, you will have this. The random variable is 1, so you won't see it here in the formula. As you multiply 1 to something else, that something doesn't change at all. Given an arbitrary level I, the probability is 1 divided by 2, then power 2i. I goes from 0 to h, where h is the height of the heap. If you expand this formula to a list of your items, you will have something like this. This is something that's not too difficult to calculate or say estimate based on geometric series. For us, all we care is to get an estimate instead of calculating it accurately, so we can relax the geometric series to infinite geometric series. In short, when you have a sum whose individual term is put together by multiplying a constant number a to r power 2k, where r is smaller than 1, then you can estimate the sum to be a constant number. And the constant number can be calculated in this way, in which you use a to divide 1 minus r. Of course, the upper cap of the sum is infinitely large. That's how you get the name infinite geometric series. Based on the infinite geometric series, you can estimate the expected number of swaps to be smaller than or equal to a constant number, as the upper cap in our case is h, which is certainly smaller than an infinitely large number. In other words, the expected number of swaps in our case is just another constant number. The average case time complexity function is in proportion to the expected number of swaps. That means it's in proportion to a constant number, so that it runs a big O of 1. Think about it. In a heap, the leaf level contains nearly half the number of all the nodes when it is full. If we assume that the newly inserted element is random, it is more likely to end up somewhere near the bottom rather than going up all the way to the root. That's the intuitive explanation why the average case is big O of 1. That's everything about the insert method. Let's move to discuss the pick method now. The pick method is relatively trivial. The only thing it does is to access and return the element at the root. So its corresponding pseudocode is just one line. That said, its time complexity will also be trivial. Regardless of if you're thinking about the best, worst, or the average case, it's always a constant time, which can be expressed as Tn belongs to big O of 1. In this video, we covered 2 basic operations of heaps, including the insert method and the pick method, as well as their time complexity analysis. In the next video, we will go over the last basic operation of heaps, the delete method, and dive into the topic of heapsort. This lecture is on heap, heapsort, and their time complexity analysis. Here's a roadmap of what we will cover. In this video, we will cover the last basic operations of heaps, which is the delete method. Of course, we will also go over its time complexity analysis, especially the average case analysis. For simplicity, we will only deal with max heaps in this video. Let's get started. So what purpose does the delete method serve? Well, the delete method doesn't delete a target node in a given heap. It only deletes the root node. In the end, it will return the value of the deleted root node. When you delete the root node, you no longer have a heap anymore, so you need to take some extra steps to restore its heap property. As such, the delete method involves a few steps. First, it will start by replacing the value of the root node with the value of the last node at the last level. As you do that, of course, you need to store the value of the root node somewhere else so that you can return it eventually when the heap property is restored. Second, it will delete the last node. I mean the one that you just used to replace the value of the root node. Third, it will perform a process known as heapify to restore the heap property. It will start this process with a new root node and keep comparing it with its largest child. If the parent is smaller than that child, it will swap the two nodes. It will keep doing this sort of comparison iteratively until the heap property is fully restored. In the end, it will return the value of the original root. Step 3 is the process that we know as heapify. The reason why it's worth mentioning is that it's not only being used here in the delete method, it's also used in heapsort as well. Let's try to apply these 4 steps to the example max heap sitting on the left side. Our goal is to delete the root node, but instead of plugging it out of the heap, we would approach this by replacing the value of the root node with that of the last node. By saying the last node, I'm referring to the node sitting at the very right side at the last level. And I'm counting the levels starting from the root. So in our case, the last node has a value of 5 and sits at the index of 6. When you use its value to replace that of the root node, you will end up with this. Of course, you still need to store the value of the original root somewhere else because you need to return it in the end. After that, you will delete the last node, as it has served its purpose and no longer useful to us anymore. Keeping it will only create redundancy we don't want or need. So deleting the last node, we will have this. So far, we went over step 1 and 2. As you can see from this example, the root node contains a value of 5 now, which is smaller than its children. So we need to take the step 3, the heapify process, to restore the heap's property. The current root has a value of 5, and it has 2 children, with values as 7 and 10. Both are larger than 5. 10 is the largest child, so we will swap 5 with 10, like this. After that, you will continue to focus your attention on the node of 5 and see if it is at the right place by comparing it to its largest child. So now the node of 5 has only one child, which is 4. 4 is smaller than 5, so 5 is at the right level, and we can stop here. In the end, you will return the value of the original root, which is 11. That's how the delete method works. To translate these steps to pseudocode, you will have a delete method. The delete method does a few things. The first 2 lines stores the value of the last node at the last level before removing it. The next 2 lines stores the value of the root before replacing its value with the last node's value. After that, it will call on the help from a method named heapify. In the end, it would return the value of the original root. We know that the heapify method corresponds to step 3, but what does that look like? The heapify method takes an integer as its only parameter, which is the index of the starting point of the heapify process. As you can see from the delete method, heapify 0 means that the starting point of this heapify process should be index 0, or say the root of the heap. Underneath the while loop of the heapify method, it would compare the value of the parent node with its largest child. The parent may have 2 children or only 1 child, and that's the job of another helper method to figure out. This method is called maxChild, which returns the index of the largest child. If the parent node is smaller, it will swap their values and update the index I to the index of its maxChild. If the parent and the largest child are in the right order, it will break out of the while loop. To make sure we are on the same page, the pseudocode of the maxChild method looks like this. It takes a single parameter representing the index of the parent node. Underneath this method, it computes the index of its left and right child, makes sure that both would exist, then compares the two, and returns the index of the largest child. Just in case you think the logic of the maxChild method is odd, it has an if and else statements. For the if statement, the condition has two parts. The first part is when the right child doesn't exist. The second part is the left child is bigger than the right child. In both of those cases, it will return the index of the left child. Okay? Otherwise, it would return the index of the right child. That's the logic of the maxChild method. It's not hard to see that the maxChild method runs on constant time because it only contains an if-else condition. The same thing can be said for the first few lines of the delete method as well. It takes constant time to run them too. The only thing that's worth our attention when it comes to the time complexity analysis is the heapify method. How much time does that take? To be succinct, we will hide the delete method and the maxChild method so that we can focus our attention on the heapify method. The time complexity of the delete method is in proportion to that of heapify process. As soon as we figure out the time complexity of the heapify method, the time complexity of the delete method will be self-telling. So what's the time complexity of the heapify method? In the best case, things are quite trivial. When you have a max heap composed of a single node, deleting it takes constant time, and the heapify method doesn't run at all, so that's constant time, expressed as T of n belongs to big O of 1. What about the worst case? The worst case must be when you have to perform swapping level by level from the root all the way to the leaf. For example, we have a max heap like this. When we follow the process of the delete method, we will replace the node 11 with node 3, and remove the last node afterward. Like this. After that, we need to rely on the help from the heapify method to restore the heap property. We will swap node 3 with its largest child, node 10, like this. After that, we need to continue this process by swapping node 3 with its largest child, node 5, like this. That's an example of the worst case. In other words, the heapify method needs to perform as many swapping as the height of the heap. What's the relationship between the number of nodes and the height of a heap? It's exactly the same as we studied for the insert method. If a heap contains n nodes in total, the height of that heap will be log n. That said, the heapify method involves log n number of swapping. Each swapping takes constant number of steps to run, so that the time complexity of the delete method under the worst case will be big O of log n. That's the worst case. What about the average case? The average case time complexity is in proportion to the expected number of swaps. I mean the swaps that are required to bubble down the new root element to its proper position, or say proper level. By new root, I mean the last node that you used to replace the original root. The random variable for this expected number can be the event when the new root element is being swapped at each level. So that's a constant number 1. Well, of course, it may or may not happen. If it happens, that's a number 1. If it doesn't, that's 0. When we discussed the insert method, we assumed that the probability of swapping at each level is 50%, because we have no way to know how big or small the newly inserted element is. So it's fair to assume the newly inserted element is random and arbitrary. So it has a fair chance to be either bigger or smaller than its parent at each level. However, that assumption is not applicable here when we are talking about the delete method. What we are dealing here is this. We moved one of the smallest elements from the leaf level to the root, and then gradually bubble it down. It's not a random element, and it's certainly smaller than elements at most, if not all levels. Based on that, we will do a rough estimate. I mean, an estimate that's probably rougher than what you have seen in the other videos of this series, but still acceptable. We will assume that the probability of swapping at most levels is 100%. Based on that, we can start computing the expected number of swaps. The way that you compute an expected number stays always the same. It's the sum of the set of items. Each item is the product of the random variable and its corresponding probability. When we plug in all the numbers, we will have this. Since both the random variable and the corresponding probability at each level are ones, we are essentially adding up a bunch of ones. And how many are there? The same as the height of the heap. As we learned in the past, if there are n nodes in total in a heap, then its height can be estimated as log n. So the expected number of swaps is in proportion to log n. The time complexity Tn is in proportion to this expected number of swaps, and it runs on big O of log n. That's the average case for the delete method. Now, we have covered the delete method of heaps and its time complexity of the best, worst, and average case. It's worth comparing the three different cases between the insert and the delete methods. The highlight should be the average case. The average case for the insert method runs on constant time, but for the delete method, it runs on big O of log n. Although you were given how things are computed and deduced mathematically, it's better to know why there's such a difference from a more intuitive approach. When a random value is inserted to a heap, it's most likely to be bubbled up for only a few levels, maybe 1 or 2 levels, and the number of that levels can be approximated to a constant number, because the randomness nature makes it increasingly less likely to be bubbled up at each level. Remember that you need to multiply all those 50% to calculate the probability of the newly inserted node to be bubbled up at the current level. When it comes to the delete method, the randomness assumption no longer stands. When you move one of the smallest elements to the root, it's most likely for it to be bubbled down to or near the leaf level again. Okay? That's why it takes log n swaps. As you know, log n here is the estimated height of the heap. In this video, we covered everything about the delete method of heaps, and its time complexity analysis of the best, worst, and average cases. In the next video, we will dive into the topic of heapsort. This lecture is on heapsort, and their time complexity analysis. Here's a roadmap of what we will cover. In this video, we will cover the highlighted topic on heapsort, including how to build a heap and how to apply a heap to sorting tasks. Of course, we will also cover their corresponding time complexity. For simplicity, we will stick to covering only max heaps instead of switching between max and min heaps. Let's get started. To be able to use a heap for sorting purposes, you will need to build a heap first. However, the data that you may need to process is highly likely to be in a linear structure, like an array. How do we build a heap given a linear data structure like an array? There are two possible strategies to get this done. We will go over them one after another. Let's do the more naive strategy first. Under this naive strategy, you will start by preparing an empty max heap, or say an empty array of the same size as the given one, but you will treat this array as the data storage for your max heap. After that, you can iterate through the elements of the given array and keep calling the max heap insert method to insert each of those elements into this new heap. By saying the insert method of the max heap, I'm referring to one of the basic operations of heaps. In case you don't know it, you can watch it here in one of the prior lectures. What's the worst case time complexity for this naive strategy? The first insertion will take a constant amount of time, because the heap so far contains no other elements yet. The second element will run on big O of log 1, where 1 is the size of the heap. Remember, the time complexity of the insert method runs on big O of log n in the worst case scenario, where n represents the size of the heap. The third element runs on big O of log 2, where 2 is the current size of the heap. This goes on, and the last element will run on big O of n minus 1. Okay, now you know the time complexity of each insert method being called to build the heap. All that remains is to add them up. Roughly like this. So what does this lead to? Based on the logarithmic product rule, you can combine all these different terms just like this. The ending result will be log of n factorial. We know that the factorial of n is certainly smaller than n power to n. Yet log n power to n can be converted to n multiplied by log n based on the logarithmic property. As a result, we have an upper cap that's more familiar to us, which is n log n. That's the naive strategy and its worst case time complexity analysis. It's worth saying that although this strategy is straightforward, it's rarely used in building heaps from arrays, because it's not very efficient. That is why we need to talk about the second strategy. Under this strategy, we won't prepare a new heap at all. Instead, we will treat the given array as a heap whose property needs to be restored. After that, we will traverse from the last non-leaf node to the root node. During this traversal, we will keep applying the heapify method to each of the nodes. So what heapify method? The same method that we covered when we discussed the delete method. The steps of the heapify method are presented here on the screen. The purpose of the heapify method is to restore the heap property of a subheap given its root index. Well, of course, here you have an assumption. The assumption is that the root node is a culprit, or say the root node is the one node that breaks the heap property. The heapify process achieves its purpose by iteratively swapping the root node value with its largest child until it reaches a proper level. Translating the step to pseudocode, you will have the same pseudocode that we covered in the past, like this. The heapify method takes a single parameter, I, that represents the index of the root node of a subheap, and it relies on the help from a helper method named maxChild to identify the largest child of a parent. In case if you didn't know heapify method, you may consider watching this video. Despite of knowing the heapify process and all the steps of the second strategy, there might still be a key barrier for you to get started implementing it, which is the index of the last non-leaf node. So the index of the last non-leaf node is always n divided by 2 minus 1, where n is the heap size, or say the length of the given array. that is used to store the heap data. For example, if you use the array on the left side as an example, its size is 6. Its last non-leaf node is 6, whose index is 2. We can use the array size 6 to divide 2, then subtract by 1. After that, you will get index 2, which is the index of the last non-leaf node. You can use induction to prove this if you want. Here, we will just take some leap of faith and use it as it is. Based on the given steps in this strategy, the pseudocode is extremely simple. You only have a for loop that traverses from n divided by 2 minus 1 to 0. Inside this for loop, you will keep calling heapify on each of the nodes you visit. Let's try to apply this process to an example so that you can get a better sense of how it goes. We will simply use the example on our left side. The last non-leaf node is 6. When we apply heapify on it, we are actually trying to restore the heap property of a subheap, which only contains 2 nodes, 6 and 4. Like this. Yet this is already a max heap, so we don't need to do anything. The for loop will take us to the next node, which is 7. When you call the heapify method on the node of 7, you are trying to restore the heap property of the subheap with its root as 7. Is this a max heap? No, 7 is a parent, its largest child is 10, and 7 is smaller than 10. So, the values of the 2 nodes need to be swapped. Like this. And now it becomes a max heap again, so we would move on. The next node to traverse is 3, which currently sits at the root level. When you call the heapify method on this node, you are actually trying to restore the heap property of the whole heap, with its root as 3. Like this. As a root node, 3 is apparently smaller than both of its children. So we need to swap it with its largest child, which is 10. Like this. After that, our focus is still on the node 3. It is still smaller than its largest child, which is 7. So we need to swap the 2, like this. Now, the node of 3 is at the leaf level, so we stop. Just to make sure we are on the same page. The heapify process on each of the subheaps that we just went over all happen in this original array. The tree structure here that you see is merely a visual representation. Now you know what this strategy is about. Let's talk about its worst-case time complexity, so that we can compare it to the more naive strategy. To calculate the worst-case time complexity, all we need to do is to add up the time it takes to heapify each subheap, expressed like this. There are roughly h minus 1 levels, where h represents the height of the heap. We want to heapify to any nodes at the leaf level, because we started with the last non-leaf node. That's how we get that h minus 1. At each level, there are a certain number of nodes. The heapify process on each of the nodes takes the same amount of time in the worst-case scenario. To get the time it takes to heapify all the nodes at the same level, you need to multiply the node numbers with the time it takes to heapify a single subheap. There are some things that we need to clarify as we start doing the actual calculation based on this idea. First, in this strategy, we apply heapify process backward from the last non-leaf node to the root. To make it more convenient for us to estimate the time complexity, we will deem the leaf level as level 0. As we move upward towards the root, we will increase the level number. So the second bottom level is level 1 in our eyes. So basically, we treat the level numbers in the same way as a for loop. Second, the number of nodes at each level can be estimated as is shown here. We covered this in the past, in case if you remember. In short, if there are n nodes in a heap, to get the total number of nodes at the leaf level, you just need to divide n by 2 to get the number of nodes at the second bottom level, or say level 1. You can just keep dividing n by another 2, so that will be n divided by 4. To get the number of nodes at the third bottom level, or say level 3, you simply keep dividing n by another 2. So that's n divided by 8. And it goes on and on towards the root. The same pattern holds for every level. If you combine what we just mentioned, we will go from the bottom to the top and treat the leaf level as level 0. That will give us a way to estimate the number of nodes at each level using this formula. So that's n divided by 2 power to I plus 1, where n represents the total number of nodes in a heap, and I represents the level number. Now we know how to estimate the number of nodes at each level. We can actually quantify the time complexity Tn. Tn can be expressed like this. The number of nodes at level I is n divided by 2, then power to I plus 1. The work per node at level I is in proportion to I. In case if you are confused by this, remember that when we call heapify on each node at a level, we are actually trying to restore the heap property of a subheap, whose root is at this very level. The heapify method runs on a time complexity in proportion to the height of this subheap. If you focus your attention on the term inside this summation, you will see that n has nothing to do with the summation at all. And you can actually extract it out like this. Now, the summation term becomes something that you have seen in the past. The geometric series. As the upper cap of the summation grows towards infinitely large, it can be estimated to a constant number. As a result, Tn can be estimated to simply n multiplied by another constant number. In other words, the time complexity of this strategy is simply big O of n, which grows at a linear time. As you can see, the second strategy is definitely more efficient than the first one. Fixing a broken heap is certainly much faster than keeping calling the insert method to build a heap from scratch. When you are given a linear data structure to build a heap, you should always think about this strategy instead of the more naive one. That's everything about how you build a heap. Let's move to discuss how to use heaps for sorting purposes. The scenario that requires sorting using heapsort is no different from when we use other sorting algorithms such as a merge sort or quicksort. You are given a linear data structure with elements, and you are asked to sort the elements. How do you do it using the help from a heap? You will typically follow a set of steps. First, you will start by building a heap from the input array. After that, you will repeatedly extract the max or the min value by calling the delete method on the heap iteratively. If you build a max heap, the delete method will extract the max value. If you build a min heap, the delete method will extract the min value. When you place all the extracted values in a different array, they will either be in ascending order or descending order. For example, if you are given an array like what you see here on the screen, when you build a max heap out of it, you will end up with an array sorted in the descending order. To map these steps to pseudocode, you will have this. The heapsort function takes a single parameter a, where a represents an array. The heapsort function starts by preparing an empty array. After that, it calls buildHeap function on a, which will turn a into a heap. After that, it calls the delete method iteratively to store the returned elements in the prepared array. The delete method is the same method as we covered in the last video, so we won't get into its details here. Heapsort largely relies on the help from two helper methods that we developed in the past, including build heap and the delete methods. We know that the time complexity of the build heap method is big O of n in the worst case. What about the for loop that iteratively calls the delete method? If we want to measure the worst case time complexity of heapsort, we have to have a good sense of the time complexity of this for loop. We already know the worst case time complexity of the delete method as log n, when n is the heap size. When the delete method is called for the first time, the time complexity will be certainly big O of log n, as the heap size is still n now. After that, the heap size becomes one element smaller, which is n minus 1. So when the delete method is called again the next time, its time complexity becomes big O of n minus 1, as the heap is one element smaller now. When the delete method is called again for the third time, the time complexity becomes log n minus 2. This will go on and on until you run out of elements in A, and the time complexity is gradually reduced from log n to log 1, like this. To get the total time complexity of the for loop, all it takes is to add all these different time complexity up, like this. Based on the logarithmic property, you can combine all these individual terms, so it becomes big O of n factorial. The factorial of n is always smaller than n power to n, and the log of n power to n is equal to n multiplied by log n. As such, we can estimate the worst time complexity of the for loop to a term that's more familiar to us, which is n log n. So the total time complexity of heapsort will be equal to big O of n log n plus n. N log n is the dominant term with a higher growth rate. As such, you can ignore n, which grows more slowly. That said, the time complexity of heapsort can be estimated as big O of n log n. In this video, we learned about heapsort, particularly how to build a heap efficiently and how to use a heap for sorting purposes. That's everything about this video. Hope you learned something new. This video is on Hashtable, its implementation, and the time complexity of its basic operations. Here's a roadmap of what we will cover. In this video, we will explore where hashtables are useful and how hash functions work. Let's get started. So where hashtables can be useful? A hash table is a unique data structure that supports fast data insertion, deletion, and searching. More than that, a hash table allows you to store and retrieve related pieces of data efficiently. Imagine that you have a collection where each item consists of two parts. One part that identifies it, like a name tag, while the other part that holds the actual information. This structure is known as key-value pair, and hash tables are designed to organize and look up these pairs quickly. A hash table is also handy when it comes to dealing with data duplication and uniqueness verification. So whenever you need to perform frequent searching on existing data, demand speed in data insertion and deletion, or have key and value pairs, you should think about using a hash table. Okay? To learn more about hash tables, you need to start by learning its core first, the hash function. Before getting to the hash function, let's define hash tables formally first. A hash table is a data structure that is used to store key-value pairs for fast data access, and it uses a special function to convert keys into indexes, which are used to determine the positions of where values are stored. A hash table is so efficient, and its basic operations such as search, insert, and delete typically run on constant time. This special function that we mentioned is the hash function. Let's use an example to help you understand what a hash table is and how hash functions work. As you can see on the screen, this is the setup of a hash table. It is composed of two arrays. The first array is used to store the keys, while the other is used to store the values. The indexes of the two arrays correspond to each other. For example, index 1 in the array representing keys correspond to the index 1 in the array representing values. If you have a key and value pair data, it will store the key at a specific index, and the corresponding index in the array representing values will be where you store that piece of value. Okay? Let's try to add some data into this hash table. For example, we have a set of key and value pairs like this. Each pair takes a row, and the data comes prior to the comma represents the key, and the data comes afterward represents the value. Imagine that we are running a big farm, and we have 5 cats, 2 dogs, and 3 foxes on the farm. So we are going to store such information into a hash table. To store the first key and value pair into the hash table, it will convert the key to a numeric value representing indexes. How do you do that? You will use the help from a hash function. For example, the hash function for this hash table is like this. It sums up the digits corresponding to each character, and then divides the sum by 11 to get its remainder. Just in case, there's a correspondence between each character and a number if you look up in the ASCII table. Based on that, we can compute the position of cat, which is 5 because the capital letter C corresponds to 67, A corresponds to 97, and T corresponds to 116 in the ASCII table. When you add them up and divide the result by 11, you will get the remainder as 5. The 11 here represents the size of both arrays. If you want to insert some data somewhere into these two arrays, you need an index that's smaller than 11. That's why the hash function is designed like this. Now you have the index for this pair of data computed. You can move to store it into the hash table. The cat is the key, so it goes into the array representing keys. The number 5 is the value, so it goes into the array representing values. Both are stored at the same index of 5. Next, you will move to the next pair of data, which has the key as dog and the value as 2. When you use the same hash function to compute the corresponding index of the key, you will get 7 in the end. So you will store this pair of data at the index of 7. Like this. Next, you will move to the last pair of data, in which the key is fox and the value is 4. When you use the same hash function to compute the corresponding index of the key, you will get 4 in the end. So you will store this pair of data at index 4. Like this. When it comes to searching for this pair or any other pair of data, you only need to have the target value going through the hash function to know its corresponding index in the hash table. After that, you can compare whatever is stored in the hash table, or say the arrays representing the keys, to the given target. If they don't match, it means that the target is not in the hash table. With only 3 pairs of data, everything seems perfect. What if we try to insert another pair into the same hash table? In this new pair, the key is ant, and its value is 1000. When you apply the same hash function to the key ant, it will compute its corresponding index as 5. However, in the same hash table, index 5 is already occupied with the pair of cat and the number as 5. So you can't store this new pair of data, ant and 1000, into the same hash table anymore. This issue is known as collision. A lot of efforts are dedicated to addressing the collision issues in hash table. Maybe the first thing that crosses your mind is whether a better hash function will get the job done. For example, we can improve this naive hash function that we have been using from this to this. The improvement that was made is all about here. Before you sum up the digits corresponding to each character, you can multiply them by the corresponding index of each character in that given word. Theoretically speaking, this hash function is a bit more complex and can help reduce the chance of collision, yet it doesn't fully address the problem. For example, when you start using this improved hash function, the indexes of the 4 pairs will end up as this. As you can see, you still have a collision. This time, the collision is between another 2 pairs, cat and a dog. Depending on which pair is inserted first into the hash table, the other pair won't be able to fit in. As you can see, improvements to hash functions don't fully address the collision issues, so we need a different approach to solve this problem. That's the topic of the next video on Hashtable. Now you understand where hashtables can be useful and what a hash function is. The next step is to learn about how hashtables handle collisions. In the next video, we will dive into one way to address collisions, open addressing, and we will use it to implement the basic hashtable operations. This video is on hashtable, its implementation, and the time complexity of its basic operations. Here's a roadmap of what we will cover. In this video, we will dive into one way to address the collision issues in storing data into a hash table, which is called open addressing, and we will use it to implement the basic hash table operations. After that, we will also cover the time complexity analysis of such basic operations. Just one word about collisions in case if you didn't learn about it. When you have some data pairs that need to be stored into a hash table, their key values will be fed to the hash function of the hash table to compute their positions or say the indexes in the hash table. Sometimes, 2 different pairs may end up with the same index. This is what we know as the collision issue. How does open addressing solve this problem? With open addressing, collisions are resolved by finding another open slot in the hash table. We call this process probing. It is handled via a probing function. Some common types of probings include linear probing, quadratic probing, and double hashing. Linear probing simply refers to the process of using a linear function to check if the next slot or the index is available. If not, keep moving to the next until it is available. Quadratic probing uses a quadratic function to identify the next available index. Double hashing uses a second hash function to identify the next available index. Let's use an example to explain how probing works. Think about this example. The hash function of this hash table is like this. It finds the digits corresponding to each character in the ASCII table, and adds them all up. After that, it divides the sum by the size of the hash table 11, so that the index can be retrieved. You have 4 pairs of data that you want to store into this hash table, like this, and you have already stored the first 3 pairs into the hash table. When it comes to the last pair, whose key is ant, and the value is 1000, you can't do it because it's supposed to have the same index as the first pair whose key is cat. When collisions like this happens, you can use a linear probing function like this to help you identify the next available position, so that you can store the pair ant 1000 into this hash table. So the probing function says when a collision happens, you need to recompute the index by adding a step number to the original index, and then divide it by 11, where 11 is the size of the hash table. Just in case if the next index is occupied, it will add 1 to the step number and recompute the index. It will do so recursively in case if the identified indexes are occupied. In our example like this, you will be able to get an index as 6 just by using the probing function for once. So index 6 is available in the hash table, so we can store the last pair of data into the hash table now, like this. The probing function that's used by the hash table is a linear function. It can certainly be replaced with a quadratic function or another hash function if needed. Now you know what open addressing is about and how it works. Let's move to the implementation of Hashtable. The implementation will be using this open addressing to handle collisions. Let's start with the Hashtable class definition. You will start by defining the size for the Hashtable class and declare two arrays of the same size, one array to represent the keys, while the other to represent the values. There would be two functions that are necessary for this class, the hash function and the probing function. However, we won't be defining them here. We will just fill them up with 3 dots as a placeholder. This is the starting point for the Hashtable implementation. Next, we will focus on implementing the 3 basic operations of Hashtables, including the insert, search, and the delete methods. We will start with the insert method. The purpose of this method is to add a paired data into the hash table, and it is where the collisions may happen and where collisions need to be handled properly. The insert method will take 2 parameters, one representing the key while the other representing the value. The two make a paired data instance. The first thing the insert method will do is to compute the index based on the hash function under the same class. Just in case the index is occupied, it takes advantage of a while loop to run the probing function until a next available position is found, then assigns it to the same index variable. So, after the combination of the hash function and the while loop, it's guaranteed that the index represents a position where a new paired data can be inserted into. The last step, of course, is to add this paired data into the hash table. The key goes into the array representing keys, and the value goes into the array representing values. Both will be at the same index that's computed above. The implementation of the insert method only takes a few lines, but it also poses some challenges when it comes to searching for or deleting an element. Because when the element at the index computed by the hash function is not the same as the target, it doesn't necessarily mean the target is not in the hash table. In such a case, you will need to check other indexes computed using the probing function. Let's look at the search method next to see how we would handle such a challenge. The search function takes a single parameter representing the key value, and uses the key value to compute the index based on the hash function. After that, it checks the key at that index against the given key. If they don't match, then the function needs to check all the keys at the indexes computed using the probing function, and compare them to the given key. If one of them matches the given key, it will return true and stop the function from running. Otherwise, it will return false in the end. If you compare the search and the insert methods side by side, you are going to see that they share a lot of similarities because how open addressing works. In both functions, you need to run the hash function for once, and potentially run the probing functions for many times to compute the indexes you may need to check. Now, let's move to the delete method. The delete function takes a single parameter as the key value. It computes the index using the hash function for once, and it may use the probing function to compute more indexes to find if the given key has been stored in the hash table. If the given key is found to be at one of those indexes, the delete method will replace both of the key and the value with null in the two arrays representing keys and values, and it will return true in the end. Otherwise, the delete method will return false. With open addressing, the space in the data storage of the hash table is valuable. As more paired data are inserted, it will be a matter of time that you run out of space. To address this issue, the hash table implemented using open addressing typically has another method to help adjust the size of the data storage. This method takes no parameters and only aims to double the size of the hash table. As a result, it's named resize. As you can imagine, it involves a process of replacing the old data storage with a new one that doubles the size, and copying and pasting all the existing data points from the old storage to the new storage. This method is often called when the hash table is about to run out of spaces. Now, we covered the implementation of hash tables when open addressing is used to handle collisions. Let's talk about the time complexity of its different operations, starting from the insert method. The best case of the insert method is when the probing function doesn't need to run at all, which means that once the index is computed using the hash function, you would have an available spot to insert your data. In that case, it only takes a few steps to finish executing this method, which means that the time complexity will be constant time, expressed as big O of 1. What about the worst case? When the hash table is full, and there's not a single spot where you can insert any new data, in that case, this while loop will be in proportion to the size of the hash table. Because you need to run the while loop to figure out that every index computed by the probing function is not available until the index is out of the bound of the hash table size. That said, in the worst case, the time complexity is in proportion to the size of the hash table, which is big O of m. In case you forget, we used m here to represent the size of the hash table. What about the average case? We need the help from the expected number here to account for the randomness. In other words, we need to think clearly about what assumptions we have, what the random variable is, and what the corresponding probability is for the random variable. To simplify the average case analysis, we will approximate the time complexity to the expected number of probes, considering that they are in proportion to each other. We have only one assumption to cover. We would assume that the hash table size is m, and there are already n elements in the hash table. As you can imagine, n is a number that's always smaller than or equal to m. Here, we need to introduce a new term known as a load factor. It's denoted as alpha. The load factor alpha is calculated by dividing n by m, and it is a common tool that's being used to measure how full the hash table is. If you plot the load factor, you will see that it ranges between 0 and 1, and when the load factor is getting closer to 1, it means that the hash table is closer to being full. When it's close to 0, it means that the hash table has plenty of space for new elements to be inserted. The load factor alpha is also used to estimate the probability of successful probing of the insert method. By saying probing, I mean when you get your index via either the hash function or the probing function, and then check if that index is available for inserting data or not. The probability of an unsuccessful probing is the same as the load factor, alpha. The probability of a successful probing is 1 minus alpha. That's all about the assumptions. Let's get to the random variable and its corresponding probability. We will pick the random variable as the number of probes required to find an available spot. In other words, to find an available spot, we need to check for I indexes. I is an arbitrary number that ranges from 1 to n. What about its probability? For each probing, the chance of encountering another existing element in the hash table is the same as the load factor, alpha. If you find an available spot after probing for I times, that means there are I minus 1 times of unsuccessful probings. Based on the product rule of probability computation, you will need to multiply the probability of I minus 1 of unsuccessful probing and the 1 successful probing at ith time. So the probability of finding an available spot after I probes is simply 1 minus alpha, then multiplied by alpha power to I minus 1. This part represents the final successful probing, while the remainder represents the I minus 1 times of unsuccessful probings. Now you have everything you need to compute the expected number of probings. The expected number of probings is computed in the same way as all expected numbers. It is a sum of items, and each item is a product between the random variable and its corresponding probability. We will relax the upper cap from m to infinitely large first, like this. After that, we will be able to estimate a part of the formula to a constant number based on infinite geometric series. Which part? This part. I mean the same formula, but without 1 minus alpha. Based on this, we can estimate the expected number of probings as a constant number, which computes as 1 divided by 1 minus alpha. It is worth noting that we see alpha as a constant number here when computing the expected number of probings, because alpha has nothing to do with the random variable I. However, based on what we learned from the load factor, we know that it changes dynamically as more elements are inserted into the hash table. As a result, we can conclude that the time complexity is in proportion to the load factor alpha, expressed as big O of 1 divided by 1 minus alpha. As for the search method, its time complexity analysis will be the same as that of the insert method. The major cost of the search method remains the same as the insert method, which is the computation of the index via the hash function and the probing function. I mean, this block of code. As a result, the best, worst, and the average case analysis of the search method are the same as the insert method. The same thing can be said for the delete method. Its time complexity analysis is the same as the insert method. Now you understand what open addressing is, how it's used to handle collisions, and the implementations of the basic operations of hash tables. In the next video, we will explore chaining, a different way to address collision, and how that will change the implementation of hash tables. This video is on hash table, its implementation, and the time complexity of its basic operation. Here's the roadmap of what we will cover. In this video, we will dive into one way to handle the collision issues in storing data into a hash table, which is called chaining, and we will use it to implement the basic hash table operations. So what's chaining? Chaining is a solution to handle the potential collision issues in storing data into a hash table. When chaining is used, the basic structure of a hash table will be an array, and each index in the array will be used to store a linked list. This idea helps address the collision issues. When it comes to inserting new data into a hash table, if two data points have the same index computed by the hash function, they will be added into the same linked list at that index, one element after another. So you will be able to chain them up at the same index. And that's why this method to handle collisions is called chaining. This structure introduces some challenges in searching for or deleting elements. For searching, when you are given a target key and compute its index, you will need to check possibly all the elements in the linked list at that index. The same can be said for the delete method. You will need to find the target element based on the given key first, which means that you need to check possibly all the elements in a linked list at a particular index. Let's go over an example to see how things work in a hash table when chaining is used to handle collisions. A single array like this would be good enough as the data storage for a hash table when chaining is used. We will name this array table, and it is initially empty but comes with a fixed size. The input data that you get to insert into this array is as follows. There are 4 key and value pairs in total. In each pair, the key and value are separated by a comma. For example, in the first pair of data, the key is cat, and the corresponding value is integer 5. To insert the input data into the hash table, you need to compute their positions by feeding the keys into the hash function. Based on the hash function, given a key, which is a string, you need to find the corresponding digits of each character in that key from the ASCII table. After that, you will need to add up the digits. In the end, you will divide the sum by the size of the hash table, which is 11. For example, the key of the first pair of data is cat, and when you feed the key into the hash function, you will compute its position accordingly, and the result is 5, which means it goes into the index of 5 in the hash table. When you do the same to the keys of the other pairs of data, you will end up with the following indexes. Based on the computed indexes, we will insert the data into their positions in the data storage. You may notice that 2 pairs have the same index. I mean the pair whose key is cat and the other whose key is ant. How do you insert them into the same index? With open addressing, that's not possible. So you have to find a different position for either of the 2 pairs of data. However, with chaining, you are able to insert 2 or more data pairs into the same index. The array named table is not being used to store integers. Instead, each element in the array is a linked list. Each data pair will be a node in one of those linked lists. Because of that, 2 pairs of data can go into the same index, and they will simply be 2 nodes, one connected to the other. Let's demonstrate that via an example. Starting with a pair whose key is a cat. It will be the first node of the linked list at index 5, like this. After that, you will insert the pair whose key is fox as the first node in the linked list at index 4, like this. After that, you will insert the pair whose key is dog as the first node of the linked list at index 7, like this. After that, you will insert the pair whose key is ant. It goes to index 5. Since there are already some other nodes in this linked list, you need to traverse all the nodes till you get to the end of that linked list, and insert a new node representing this pair of data, like this. So chaining is about using linked lists to chain up all the data pairs that are supposed to go into the same index. As such, no collisions would happen between such data pairs. Now you know how things work when chaining is used to handle collisions. Let's implement the basic operations of a hash table accordingly. We will start by preparing a hash table class. Under this class, we will create a linked list named table whose size is m. Each node in the linked list aims at storing a key and a value pair. So the class representing a node will look like this. For simplicity, we are assuming that each node deals with paired data whose key is a string and the data is an integer. Beyond that, we also need a hash function that helps compute the index given a key value underneath the hash table class. Now, we are ready to implement the basic operations of a hash table, including the insert, search, and delete methods. We will start with the insert method. The insert method takes 2 parameters. In combination, the 2 parameters represent a pair of data, because one represents the key and the other represents the value. The first thing the function does is to compute the index based on the given key. The index will be where the new pair of data be placed. After that, The function checks if there is already a linked list at the index in the data storage. If not, it will move to create a new one. After that, it will add the new pair of data as the last node to the linked list at the corresponding index. That's everything about the insert method. As you can see, the hero here is the linked list. It's responsible for chaining all the paired data as nodes that goes into the same index of the data storage. Let's look at the search method next. The search method takes a single parameter representing the key. Same as the insert method, the first thing the search method does is to compute the corresponding index based on the key. If there is a linked list at the corresponding index, the search function needs to check one node after another iteratively in the linked list. If the key is found somewhere, you will immediately end the iteration and return true. Otherwise, you will return false in the end. It's worth emphasizing that when you need to be sure that the given key can't be found in the data storage, you have to iterate through all the nodes in the linked list at the corresponding index. As you can imagine, if the length of the linked list to iterate over become long, the search could potentially take a long time. That's a search function. Now let's look at the last basic operation, the delete method. The delete method takes a single parameter representing the key. It will compute the corresponding index based on the key first, and searches for the node with the key afterward. It does the search in the same way as the search function, by iterating over all the nodes at the corresponding index. If a node with the key is found, it will delete the node in the linked list and return true. Otherwise, it will return false, as the key cannot be found in the data storage. That's everything about the basic operations of a hash table when chaining is used to handle collisions. Let's move on to discuss the time complexity of the basic operations. We will start with the insert method. What does the best case look like for the insert method? When you can insert the new pair of data as a node in a single step. That's when the new pair of data is inserted as the first node in a linked list. The time complexity of this case is bigger of 1 because it takes constant number of steps to do so. What about the worst case? In the worst case, all existing data in the data storage are stored in the same linked list. Like what do you see here in this example? If there are n pairs of data in a hash table, all of them are chained in the same linked list, and the new pair of data will also go to the same linked list. Then you have a worst case. That said, the time complexity of the worst case is big O of n, where n represents the number of pairs of data in the hash table, like this. Now, let's talk about the average case of the insert method. The key assumptions for the average case analysis is that the hash function distributes keys uniformly across all the indexes. We will assume that a hash table contains n nodes in total, and the size of the data storage is n. Then, same as what we covered on open addressing, the load factor alpha is calculated as n divided by m. The load factor measures how full the hash table is in general. To be specific, when chaining is used, the load factor alpha also represents the average node numbers per linked list, or say per index, because we assume that the hash function distributes keys uniformly. This is based on some intuitive understanding and often straightforward enough. If you want a formal mathematical deduction, you will need to pick a random variable representing whether an arbitrary number of key is hashed into a particular index, estimate its probability, and calculate the expected number of nodes per index, given n nodes in total. We will skip this step here considering how intuitive the n divided by n is to represent the average number of nodes per index. That said, the time it takes to insert a node at the end of a linked list is all about traversing all the nodes in a linked list, which is in proportion to the number of nodes, which we already know is represented by the load factor alpha. Additionally, to account the constant number of steps it takes to actually insert this new node, we also need to add 1 to those steps, which gives you 1 plus alpha. So the average time complexity of the insert method is big O of 1 plus alpha. You may wonder if the 1 is necessary here. It is, because alpha could possibly be a number that's smaller than 1, and a number that's so small and it's close to 0. Because when the hash table is empty enough, there are barely any nodes at any of the specific indexes. That said, 1 is truly necessary here. As for the search method, the time complexity analysis is the same as the insert method. The major cost of the search method remains the same as the insert method, which is to iterate through the linked list at the corresponding index. I mean, this block of code. As a result, the best, worst, and the average case analysis of the search method is the same as those of the insert method. The same thing can be said for the delete method. The time complexity analysis of the delete method is the same as the insert method. Now you understand what chaining is, how it is used to handle collisions, and the hash table implementations when chaining is used. That's everything about this video. Hope you learned something new. This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will start by discussing the application scenario of binary search trees, or say where binary search trees can be useful. After that, we will introduce you to binary search tree and cover one of its basic operations, the search method. As we do that, we will also conduct a time complexity analysis on this method. Let's get started. So, when binary search trees can be useful? First, binary search trees support searching when you have a dynamic data. When your data grows or shrinks a lot, a binary search tree can also do that without needing to reallocate those memories. In contrast, the sorting algorithm relying on using arrays for data storage cannot do that, like a heap or merge sort. Second, a binary search tree can support many tasks that are relevant but beyond just searching. A binary search tree allows you to perform range queries or successor or predecessor lookups. It allows you to efficiently find the next greater or smaller element, or retrieves elements within a range. Due to its efficiency and versatility, binary search trees have many applications in real world. For example, our internet. Domain name system lookups uses binary search trees for fast searching of domain names. The domain name system is like a phone book of the internet. It helps translate human-readable website names to IP addresses, like this one. So computers can find the IP addresses given a domain name. This process needs to be very, very fast because every time when you visit a website, your device performs a DNS lookup, and there are millions of people like you. That's where binary search trees shine. Okay, knowing where binary search trees can be useful, let's start exploring what they are. A binary search tree is a binary tree in its core. Just in case if you don't know enough about binary trees, a binary tree is a data structure where each node has at most 2 children, called the left child and the right child. It starts with a root node, and each node can have no more than 2 nodes branching from it, forming a tree-like structure. A binary search tree is a binary tree with a special feature. In a binary search tree, the left subtree of a node contains only nodes with smaller values. The right subtree of a node contains only nodes with bigger values. An example of binary search tree may look like this. You can focus your attention on any nodes, and then check its left or right subtrees to examine this special feature, or say property of binary search trees. For example, if you focus your attention on the root node with a value of 50, all the nodes in its left subtrees are smaller than 50, and all the nodes in its right subtree are bigger. For another example, you can focus your attention on the node with a value of 66 right here. Its left subtree only contains nodes that are smaller than 66, and its right subtree only contains nodes that are bigger. Just to be sure, a binary search tree doesn't contain duplicates, or say nodes with the same values. We will assume that every node is unique, or say the values of all nodes are different. Now you know what a binary search tree is. Let's talk about its implementation. Before you ever think about implementing a binary search tree, its basic unit, a binary search tree node, needs to be implemented first. The implementation of a binary search tree node bears a lot of similarities as a linked list node. They both can store some values in a node, and both store some references pointing to other nodes. However, in contrast to a linked list node, a binary search tree node has two references to its left and right children. Based on the definition of the node class, we can move to structure the binary search tree class. In the class representing a binary search tree, short for BST, we will start by declaring a node that represents the root node of the whole tree structure. In the class representing a binary search tree, short for BST, we will start by declaring a node that represents the root node of the whole tree structure. This will be the entry point to accessing other nodes in this tree. Beyond that, we will define a set of functions representing the basic operations required by a binary search tree, including search, insert, and delete methods. These methods need to be implemented one after another as functions. With the binary search tree skeleton set up, our next task is to implement the search function. As the name indicates, the search function, or say the search method, aims at searching for a given value, a target value. It certainly involves a few steps. Let's start by assuming that we have a binary search tree that has been defined and declared with many data points, like this one. To perform a search task on this given binary search tree, you need to start accessing its data first. So the first step is to access the root, and that's the entry point to any other nodes in this binary search tree. Second, you will compare the target value to that of the current node. If they are the same, then great, the job is done, the target is found. So you would simply return true in that case. If the target value is smaller than that of the current node, you will move to search in its left subtree. Remember, this is a binary search tree. All nodes in the right subtrees are bigger than the current node, so there's no point in comparing them to the target anymore. Similarly, if the target is bigger, you will only need to search in its right subtree next. In the end, if you reach a leaf node, yet still can't find a node with the same value as the target, it means that no other nodes have the target value. As a result, it will return false. Let's go through an example to further make sense of these different steps. For example, you are given a target value of 36 to search for in this binary search tree. Your starting point is the root node. 36 is smaller than the value of the root node, so you continue your search in its left subtree. You can safely ignore its right subtree because all the values in the right subtree are even bigger than the root node value. Next, we will compare the target 36 to the node of 31. The target 36 is bigger than 31, so you can continue your search in its right subtree, like this. Now you compare the target 36 to the node of 41. The target 36 is smaller, so you continue the search in the left subtree of node 41, like this. Now you compare the target 36 to the node 32. The target is bigger, so you continue the search in its right subtree, like this. The target is still bigger, bigger than the node of 34, so you continue the search in its right subtree, like this. Now you are at the node of 36, which has the same value as the target. After comparison, you will return true, and the job is done here. If you reach a leaf node, yet still can't find the node with the same value as the target, it's guaranteed that you can't find such a node elsewhere in the binary search tree. In such a case, you would return false instead. Now you know how the steps work based on this example. Let's convert it to the pseudocode. Here, we are doing some overloading methods in the pseudocode. The same function name, but with different parameters. The first function, this one, is the one that is exposed to the users. The second function is hidden from the user, but does the heavy lifting behind the scene. It doesn't have to be set up like this, but this setup makes the recursion easier. The first function is more like a wrapper that's exposed to the users, and the second function does the actual work. So let's focus our attention on the second function. This function takes two parameters, the target value and the current node. In its base case, it either returns true or false. It returns true when the target is found. It returns false when you go beyond the leaf node. How do you tell that you are beyond the leaf node? When your node becomes null. In that case, you return false. Well, the pseudocode is not a direct line-by-line translation of the steps we just described. The base case here is a combination of the case A in step 2 and step 3, like this. When the target is either smaller than or bigger than the target, you continue the comparison via the recursion. When the target is smaller, you run the search on the left subtree of the current node, and return the search result. When the target is bigger, you run the search on the right subtree of the current node, and return the search result. That's everything about how the search function is implemented. Let's discuss its time complexity. We will start with the worst case first. So what does the worst case scenario look like for the search function? Or say, what kind of binary search tree and a target value will lead to a worst case? Before picturing such a tree structure, we can at least say that the worst case will force you to compare every node in the tree to the given target value, literally every node. Knowing that, it's not so hard to find such an example. When you have a binary search tree that looks like a singly linked list, and the target to search for is the node sitting at the very tail, you have a worst case. An example can be the one that sits on your left. Technically speaking, a singly linked list can be a binary search tree, as long as the property of the binary search tree is maintained. In this example, every node happens to have only the right subtree, and each node is bigger than its parent, and the target to search for is equal to the value of the last node. For another example, you may have a binary search tree looking like this, still a singly linked list, but the nodes are not in the perfect ascending or descending order, and the given target cannot be found in this tree. However, as long as every node needs to be compared to the target in the search process, you will have a worst case. Assuming that a binary search tree has a total node number as n. In the worst case, every node is compared to the target in the search process, and every comparison takes constant time. So the time complexity of the worst case is linear time, expressed as Tn belongs to big O of n. What about the best case? The best case is somewhat trivial in comparison. Given a binary search tree like this example on our left, if the target value is the same as that of the root node, like this, you will have a best case, regardless of how big or small the binary search tree is. As long as the given target is equal to the value of that of the root node, you have a best case. In the best case, you only need to perform one comparison before the job is done. And such a comparison takes constant time. So the time complexity will be constant time, expressed as Tn belongs to big O of 1. What about the average case? It's certainly trickier than that of the best and worst cases. We need to use the help from the expected value to account for randomness. We need to make sure we are on the same page before we can start computing the average case, such as the assumptions we have, the choice of the random variable, and the probability. Let's start with the assumption. We would assume that the binary search tree is randomly constructed and relatively well-balanced. By saying that, I mean you don't have a left or right subtree that is significantly bigger than its counterpart. If the binary search tree has n nodes, with this assumption, we can safely say that the height of the tree is roughly log n. With this assumption set, we have two different scenarios to explore. The first scenario is unsuccessful search. For an unsuccessful search, we don't need the help from the expected number because unsuccessful search always ends up with checking the last node at the leaf level. Remember our assumption. There are n nodes in total in a binary search tree, and the tree is well-balanced, so the height of the tree is log n. Each unsuccessful search takes the same number of comparisons as the height of the tree. The time complexity is in proportion to the total number of comparisons, considering each comparison only takes constant number of steps, or say constant time to run. As a result, under this scenario of unsuccessful search, the time complexity is log n. That's the first scenario. The other scenario is successful search, which requires the help from the expected number. In other words, for this scenario, we need to identify the proper random variable and the corresponding probability. Same as the unsuccessful search, we will be estimating the number of comparisons instead of the actual time complexity because the two are in proportion to each other. Focusing on the expected number of comparisons saves us from the triviality of counting steps in time complexity analysis. But different from unsuccessful search, we will try to establish a recurrence relation on the expected comparison number before we ever attempt the formula of its complexity. We will pick the random variable as the number of nodes in the left subtree of the root, and use letter I to denote it. Given this random variable I, and the total number of nodes as n in a binary search tree, we will be able to deduce that the right subtree of the root contains n minus I minus 1 nodes, that 1 represents the root node. If the total number of nodes in a tree is n, the chance of each node being compared to the target is critical to none. Since the tree is randomly constructed, all the values are arbitrary, so each node has an equal chance to be compared to the target. That said, the chance, or say the probability, is 1 divided by n. This is not the probability of our random variable, but a super important piece of assumption. Based on this assumption, we can deduce that after comparing the target to the root, the chance it goes into the left subtree is I divided by n, because there are I nodes in the left subtree. In other words, the chance of the target being compared to nodes in the left subtree is I divided by n. Based on that, we can also deduce that the chance of the target being compared to nodes in the right subtree is n minus I minus 1, then divided by n. Now, we have everything we need to compute the expected number of comparisons, or say the recurrence relation for the expected number of comparisons. This recurrence relation can be expressed as the following. In this formula, say n represents the expected number of comparisons at the root, at the right side of the equation. 1 represents a single comparison between the root node and the target. This summation item represents the expected number of comparisons in the next step. This is an expected value, and that's why it is a sum of two items. and each item is a product between the random variable and its corresponding probability. I divided by n multiplied by c of I represents the expected number of comparisons when the search goes into the left subtree, while the other item represents the expected number of comparisons when the search goes into the right subtree. With the recurrence relation set, we can start deducing the actual formula of Cn that's independent of the random variable. First, we will use our assumption to simplify the formula. The assumption that the binary search tree is fairly balanced, which means that the left subtree and the right subtree have about the same size. Based on that, we can eliminate the expected comparison number of the right subtree and multiply the summation item by 2. Second, we will use a continuous approximation of the expected value over all possible subtree size to replace the summation item. After that, we can use the differential equation form and integrating both sides to get a formula like this. Third, when you exponentiate both sides of that formula, you will be able to estimate Cn to the natural logarithmic of n. It's worth noting that the natural log of n grows at the same rate as log base 2 of n, although it may not be so obvious to tell when you plot them on a 2D plane. You should trust the math formula. Natural log of n can be expressed as log base 2 of n multiplied by another constant number. In other words, the two are asymptotically equivalent. That's why we can use log base 2 of n to replace the natural log of n to estimate Cn. Based on that, we can conclude that the time complexity grows at the rate of log n, expressed as Tn belongs to big O of log n, regardless of whether the search is successful or not. Tn, the time complexity, grows at the rate of log n in the average case. Now you understand what a binary search tree looks like, where it can be useful, and one of its basic operations, the search function. In the next video, we'll dive into another basic operations of binary search tree, which is the insert function. This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will cover the insert method of binary search trees. As we do that, we will also conduct its time complexity analysis. Let's get started. To make sure that we're on the same page, I need to clarify on some assumptions that I have. First, we have set up the implementation of the node class to represent each node in a binary search tree. Each node has a value and 2 references leading to 2 different other nodes, the left and the right children. For simplicity, a node only deals with integers. Second, based on the implementation of the node class, we have also set up the skeleton of a class representing a binary search tree. And there's the search, insert, and the delete methods. We implemented the search method in the last video, and the insert method is what we are going to implement now. Third, imagine that we already have a binary search tree example that looks like this on the left side of the screen. With these 3 assumptions set, we are ready to discuss the insert method. What steps are involved in inserting a new node in a binary search tree? Same as the search method, you start with the root node. Second, you search for the correct position based on the given target value. This process is similar as what you will do in a search method. If the target value is smaller than the current node value, you would move to the left subtree. If bigger, you will move to the right subtree. If the same, you will silently stop. Just to be sure, we are assuming that the binary search tree doesn't allow any duplicate values. Last, when you reach to a position that is null, you will insert the new node at the null position. Let's apply these steps to an example to get a better understanding of what happens for the insert method. You have a binary search tree example on your left, and we are going to insert the value of 35 into this tree. We will start with the root node After comparing the root node value 50 to 35, you see that the target is smaller, so you move to the left subtree, like this. You will do the same to the node of 31 now. The target value 35 is bigger, so you move to the right subtree of 31, like this. The next node is 41. The target value 35 is smaller, so you move to the left subtree, like this. The next node is 32. Well, the target value is 35 and bigger, so you would move to the right subtree, like this. The next node is 34. The target value 35 is bigger, so you would move to the right subtree, like this. The next node is 36. The target value 35 is smaller than 36, so you would move to its left subtree. However, the node 36 doesn't have a left subtree, which means that the current position is null, and the right position for this new node of 35. So you will add the node of 35 to this position, like this. That's the full process of how you insert a new node into a binary search tree based on these given steps. Translating these steps to pseudocode, you will have this. As you can see, we are doing some overloading methods in the pseudocode again, just like in the search function. The two functions come with the same name but different parameters. The first function is the one that's exposed to users, while the second one is hidden from the users but does the heavy lifting behind the scene. This setup is user-friendly and makes it easy for the implementation. Since the second function does the actual work, so let's focus on it. This function takes two parameters, one representing the current node being compared to the target, while the other representing the target value. This function always returns a node to maintain the proper tree structure. If the current node is null, that means you have reached the right spot to insert a new node with a target value, so a new node with the target value will be returned. If the current node is not null, and its value is bigger than the target, it will call the insert function recursively on its left subtree and assign the function to the dot left reference of the current node. Otherwise, it will call the insert function recursively on its right subtree and assign the function to the dot right reference of the current node. In both cases, it will return the same node as is given in the parameters. Let's talk about its time complexity. So, what would be the worst case scenario, and what time complexity would that be? If you are forced to compare every node in a binary search tree to the target value, you have a worst case, like this. When you finish comparing every node value to the target, 35 will be inserted into the end of the binary search tree, like this. If a binary search tree contains n nodes, you need to compare every node value to the target, and each comparison takes constant time. Then, the time complexity will be linear time, expressed as Tn belongs to big O of n. That's the worst case. What about the best case? The best case scenario is when the insertion is finished in a single step, like the example that you see on the left side. When the given target value is 52, then it only takes a single step for you to insert the node with its value into this tree. When the given target value is 52, it only takes a single step to insert a new node with this value into this tree as the right child of the node of 50, like this. The insertion is finished in a single step of comparison, and it takes constant time to do so. As a result, the time complexity is big O of 1. Both the time complexity of the worst and best case of the insert function are the same as the search function. What about the average case? The analysis of the average case of the insert method is actually also the same as that of the insert method. In case you want a more detailed version of the average case analysis, you can watch this video. In short, Time complexity Tn of the average case is in proportion to the comparison numbers. To account for randomness, we needed help from expected value. The assumption of computing the expected value is the same as that of the successful search. Based on the assumption, we will be able to compute the recurrence relation for the expected comparison numbers. On the right side of the equation, 1 is the number of comparisons required at the root level, and the summation is the expected number of the comparison in the next step. I divided by n multiplied by c of I represents the expected number of comparisons when the insert goes into the left subtree, while the other item represents the expected number of comparisons when the insert goes into the right subtree. With the recurrence relation, we can deduce the formula of c of n independent from the random variable. Again, the deduction process is the same as that of the search method. It involves using the assumption of a balanced tree and what you learned from calculus, such as differential equation and how to exponentiate both sides of a formula. We will be able to deduce that the expected comparison number is log n, because the time complexity is in proportion to that of the comparison number, so it runs on log n time. That's the average case for the insert method. Now you understand everything about the insert method. In the next video, we'll dive into another basic operation of the binary search tree, which is the delete method. This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will cover the delete method of binary search trees. As we do that, we will also conduct its time complexity analysis. Let's get started. To make sure that we are on the same page, some clarifications first. First, we have set up the implementation of the node class to represent each node in a binary search tree. Each node has a value and two references leading to two different other nodes, the left and the right children. For simplicity, a node only deals with integers. Second, based on the implementation of the node class, we have also set up the skeleton of the class representing a binary search tree, and there's search, insert, and delete methods. We implemented the search and insert methods in the two prior videos, and the delete method is what we are going to implement in this one. Third, imagine that we already have a binary search tree example that looks like this on the left side of the screen. With these three assumptions set, we are ready to discuss the delete method. The delete method deletes a node based on a given target value. However, it is more complex than the search or the insert methods, because there are different cases. Actually, there are three different cases in deleting a node. The first case is when the target node is a leaf node. The second case is when the target node has a single child. The third case is when a node has two children. Let's go over the cases one after another. The first case. If the target node is a leaf node, we can simply delete the node by setting its parent's corresponding reference to none. For example, if we were to delete this target node with a value of 36, it's a leaf node. We can simply achieve our goal by setting the reference of its parent node 34 to none. Is node 36 still there? Yes, for a while before it's automatically cleaned as a garbage. So case 1 is relatively simple. All leaf nodes can be deleted in this way. The case 2 of the delete method is when the target node has only one child. In that case, what you do to delete that node is to replace the node with its only child, and you do so by adjusting the reference of the target node's parent. For example, if the target node that we want to delete from this binary search tree on your left side is the node 34, then you have a case 2, because 34 node only has a single child, which is 36. How do we do it? We will adjust the reference of the parent node of the target node. the parent node of 34 is node 32, and node 34 is the right child of 32. So we adjusted the reference of 32. By saying that, I mean the dot right reference of 32, so that it points to 36, like this. Is the target node 34 still out there somewhere? Yes, for a while before it's collected as a garbage. That's how you deal with a target node that falls into the case 2. What about case 3? Case 3 is the most complex one in comparison. When the target node to delete has 2 children, you have a case 3. How do you do it? First, you will find a replacement value. Where does that value come from? Either the smallest node in its right subtree, or the largest node in its left subtree. We have names for the 2 nodes where the value may come from. The smallest node in its right subtree is called the in-order successor. The largest node in its left subtree is called the in-order predecessor. Second, you will copy its value to the target node. Third, you will delete either the in-order successor or the in-order predecessor, depending on which node you used its value. Let's use an example to demonstrate how case 3 works. For example, the target node to deleting this binary search tree is node 66. This node has 2 children, so it's a case 3. Following these steps, the first thing that we do to get the value from its in-order successor or predecessor. For example, its in-order successor is the node 75. The node 75 is the smallest node in the right subtree. To find the in-order successor of a target node in a binary search tree, you will start by moving to its right subtree first. After that, you will repeatedly follow the left child of each node until you reach a node with no left child. That node is the in-order successor. Similarly, if your goal is to get the value of the in-order predecessor, you need to move into the left subtree of the target node first. After that, you will repeatedly follow the right child of each node until you reach a node with no right child. Then that node will be your in-order predecessor. In our example, the in-order predecessor is the node 65. Okay, that's step 1. Let's stick to using the in-order successor. In step 2, you will copy its value to the target node, like this. After that, you will go to step 3, which asks you to delete the in-order successor. In our example, that's the node of 75. Since node 75 is a leaf node, deleting it will be actually the case 1. In other words, all you need to do is to set the reference of the parent node of node 75 to null. So we will set the dot left of node 80 to null, like this. That's one example of how case 3 works. To make sure we are on the same page, let's try another example. In this example, the target node to delete is node 31. First, we need to find the value that will be used to override that of the target node. If you want to use the in-order predecessor, then we need to navigate into the left subtree. Since there's one node, and only one node in the left subtree, that's our in-order predecessor then. That's node 20. However, if you want to use the in-order successor instead, you need to navigate to its right subtree and keep following the left child of each node until you get to a node with no left child. The in-order successor is node of 32. If you were to use the value to replace that of the target node, it will look like this. After that, we will move to delete the in-order successor. This is a case 2 of deletion. In other words, we will need to adjust its parent node's reference. The parent of node 32 is node 41. Node 32 is the left child of node 41, and node 32 only has a single child, which is the node 34. So we will adjust the left child reference of node 41 to node 34, like this. Now you have completed the deletion of the node 32. These are the two examples of how the steps of the case 3 are carried out. Translating these steps of all cases to pseudocode, you will have this. As you can see, we are doing some overloading here in the pseudocode, just like how we dealt with the search and the insert methods. The two functions come with the same name but different parameters. The first function is the one that's exposed to users, while the second one is hidden from the users but does the heavy lifting behind the scene. This setup is user-friendly and makes it easy for the implementation. Let's focus our attention on the second function since it does the actual work. This function always returns a node to maintain the proper tree structure. If the current node is not null, then it will start the process of searching for a node with a given target value. It does so by comparing the target node's value to the target, and then navigate to the left or right. When the target node is found, it will start dealing with the three different cases we just covered. When translating the steps to pseudocode, we don't differentiate between case 1 and 2. The if and else if statements are for the scenarios when node.left is null or when node.right is null. If you want to separate case 1 from case 2, you actually can, like this. All it takes is to add an if statement at the top, then you have if, else if, and else if. But that's not really necessary if you want a more succinct version of the pseudocode. These are the lines that deal with a case 3. We rely on the help from a helper method named the main value to get the value of the in-order successor. After that, we replace the target node's value. In the end, we recursively call the delete method on the in-order successor. The last line will return the current node. It works its magic for both case 3 and when the target node is not found in the tree structure. The main value method looks like this. In the delete function, the main value was called on the right subtree of the target node, in case if you didn't notice, like this. Now you know everything about the delete method. Let's talk about its time complexity. We will start with the worst case scenario. What gives you a worst case? When you need to traverse every node in a binary search tree to delete the target node, like this example that you see on your left, then you have a worst case. The time complexity for the worst case will be big O of n, where n represents the size of the binary search tree. What about the best case scenario? If you don't account for the time it takes to search for the target node, the delete process is typically fast enough to be big O of 1, like this example that you see here on the left. Otherwise, you will need some special example to reduce the time it takes to search for the target node to a constant amount of time, like this example that you see here. The major cost of deleting a target node is all about searching for that particular node first. Adding both the search and the delete time together, it takes constant amount of time to delete the target node, like what you see here on the left. Let's talk about the average case. The average case analysis of the delete method is the same as that of the search and insert methods. If you want a more detailed analysis, you can watch this video. In short, the time complexity Tn is in proportion to the comparison numbers. To account for randomness, we need the help from the expected value. The assumption of computing the expected value is the same as that of a successful search. Based on the assumption, we will be able to compute the recurrence relation for the expected comparison numbers. It looks exactly the same as the average case for the search method, because the main cost comes from searching for the target node, and the delete operation has only a slight additional overhead, but can safely be ignored. On the right side of the equation, 1 is the number of comparisons required at the root level, and the summation is the expected number of comparisons in the next step. I divided by n multiplied by C of I represents the expected number of comparisons when the delete goes into the left subtree, while the other item represents the expected number of comparisons when the delete goes into the right subtree. With the recurrence relation, we can deduce the formula of C of n independent from the random variable I. Again, the deduction process is the same as that of the search method. It involves using the assumption of a balanced tree and what you learned from calculus, such as differential equation and how to exponentiate both sides of a formula. We will be able to deduce that the expected comparison number is log n because the time complexity is in proportion to the comparison number, so it runs on log n time. That's the average case for the delete method. Now you understand everything about the delete method. In the next video, we'll dive into the different types of traversal on a given binary search tree. This video is on binary search tree. Here's a roadmap of what we will cover. In this video, we will cover the different types of traversals on binary search trees and their time complexity analysis. There are 3 types of traversals, including the in-order traversal, pre-order traversal, and post-order traversal. We will start with the in-order traversal. The purpose of all the 3 types of traversals, including the in-order traversal, is to visit every node in a binary search tree. In-order traversal is a recursive function that involves a few steps, mainly including traversing the left subtree, visiting or processing the current node, and traversing the right subtree. It goes over these 3 different steps on every node in the binary search tree. Instead of applying these steps to an example directly, it's better that we translate the steps to pseudocode first, as many people struggle to understand how it works without seeing the placement of the recursions. Translating these steps to pseudocode, you will have this. This function is named in-order traversal, and it takes a single parameter representing the current node it's being dealt with. The first few lines underneath this function deals with the base case. The base case is about when to end the execution of the in-order traversal. These 3 lines, they correspond to these steps we covered. So for every node, it will start by recursively traverse its left subtree. After that, it will visit the current node. In the end, it will recursively traverse the right subtree of the current node. This visit method here is a helper method whose definition is up to you. You can define it in any way that suits your needs, such as printing the value or storing the value into an array. With the help of the pseudocode, let's go over an example to make sense of the in-order traversal. For demonstration purpose, we will call the in-order traversal function on the root node. I mean the root node of the binary search tree sits on your left side, and we will process the value of each node by storing it into a prepared array, like this one. While this array is empty, it comes with the same size as the binary search tree example on top of it. Based on the pseudocode, we will first visit the left subtree of the root, then process the root node. After that, we will visit its right subtree. Remember, the function starts with a recursive call and ends with another. It does the same to every node. For every node, it will visit the corresponding left subtree, process the node, then visit its right subtree. If you want an execution order of different nodes in the left subtree of this example, it looks like this. Now let's go over the execution order one node after another for at least the left subtree. Node 20 is the first node to be processed. or say its value will be the first one to be stored into this array, because it is at the most left side, like this. After that, the whole left subtree of node 31 will be visited. So you will move to process the node of 31 by copying its value into the array, like this. After that, you will visit the right subtree of node 31. You may think that it's the turn of node 41 now, but you need to wait because the node 41 has a left subtree. So you have to visit all the nodes in its left subtree before you ever start processing the node of 41. Okay? So you will start with the node 32. Node 32 doesn't have any left child, or say it doesn't have a left subtree. So it's a turn to process the node 32 by storing its value into the array, like this. After visiting the node of 32, it's the time to visit its right subtree now. So the next will be the turn of node 34, the next will be the node 36, like this. After that, it will be the turn of node 41 to be processed. You will write its value to the array, like this. Now you have visited every node in the left subtree of the root node. It is finally the turn to process the root node. Same, you will write its value, or say copying its value to the array that we prepared, like this. Well, for simplicity, I won't go over each node in the right subtree. The same steps would be applied to every node in the right subtree. For every node, you will visit its left subtree, then process the node, then visit its right subtree afterward. In the end, you will get every node processed, or say their values, copied into this prepared array. As you can see, the array is perfectly sorted in an ascending order. That's what in-order traversal will be able to do for you. Because of the nature of binary search tree, when you run in-order traversal on one and store the values into a linear storage, you will always end up with a sorted data structure. That's exactly why binary search tree is not only useful for searching, but also useful for sorting. Beyond in-order traversal, there are also two other types of traversals, the pre-order one and the post-order one. Let's look at both of them. The pre-order traversal changes the order of these three lines and makes processing each node the priority, and pushes the two recursive calls to the end. In contrast, the post-order traversal makes the two recursive calls the priority and pushes the processing of the current node to the last task. As you can imagine, these two types of traversals won't lead to a sorted linear data structure, but they are still useful in their own ways. When you need to capture the tree structure for reconstruction or process root first tasks, pre-order traversal is typically the one tool to use. When you need to do some teardown tasks or bottom-up evaluations, post-order traversals will be very useful. As for the time complexity of the binary search tree traversal, they are all the same. Since you need to visit each node only for once, the time complexity of each type of the traversal is simply big O of n, expressed as Tn belongs to big O of n. In this video, we learned about the different types of traversals on binary search trees. That's everything of this video. Hope you learned something new. Imagine you are designing a dynamic array. Most insertions are lightning fast. Each of them only takes constant time to run. But suddenly, you have one insertion operation that takes forever to run, because it needs to deal with an extreme case when the array is fully occupied. Did the algorithm break? Not really. Here's a twist. Even though some operations take longer to run, the average cost per operation can still be incredibly low. This is where the amortized analysis steps in, by giving us the real picture of the performance of one or more operations over time, not just in the worst moment. In this video, we will dive into when amortized analysis is essential, and walk you through the aggregate method, one of the simplest yet powerful tools in your algorithm analysis toolbox. So what's amortized analysis, and when can it be useful? The amortized analysis is a way to measure the average cost of a sequence of operations. By saying cost, I mean the time it takes to execute an operation. By saying operation, I mean just a method or a function. The insertion operation that we started with is a perfect example. If the insertion operation is executed for a number of times, how expensive is it on average? Should we be using the worst case time complexity to characterize its on-time complexity? As you can imagine, most insertion operations will simply take constant time to run, or say their time complexities are all big O of 1. This is somewhat self-telling. As long as there are still spots in the array, inserting a new element only takes a single step to complete. However, in rare cases, when the array is full, the insertion operation has to do some extra work before it can insert the given new element. When the array is full, the insertion method has to double the array size first. By saying that, I mean creating a new array that is twice the size of the original array. After that, it needs to copy the existing values from the old array to the new array. In the end, it can insert the given new element. The time complexity in this rare case, or say the worst case, is big O of n, because the process of doubling the size of the data storage and copying all the old elements will take such time. So now you see that the insertion operation of dynamic arrays typically takes big O of 1 time to run, but occasionally requires big O of n time to run in its worst case. Even though the worst case time complexity is big O of n, it doesn't happen often. It's not a good reflection of what usually happens when you insert many elements one after another into an array. That's why we need the amortized analysis as a way to measure the average time per operation over a sequence of execution, giving us a more realistic understanding of the performance. Without getting to all the technical details yet, let me just say that through some measures, the amortized analysis spreads the cost of occasionally expensive operation to the whole sequence of other operations to make sure the average cost, or say the average time complexity of all these operations, is representative of how much time it takes to run them. Whenever you have a sequence of operations to run, the amortized analysis will always give you a more realistic representation of their time complexity than the worst-case analysis. So in comparison to other types of time complexity analyses, the amortized analysis has a more targeted application. It focuses on understanding the average time complexity of a sequence of operations. Now you know what the amortized analysis is and when it can be useful. Let's talk about how it is done. There are 3 main techniques used in the amortized analysis, including the aggregate method, the accounting method, and the potential method. In this video, we will focus on the aggregate method. The aggregate method is one way to measure the average cost of a sequence of operations. This method achieves the goal by adding up the total cost of a sequence of operations. After that, it divides the total cost by the operation numbers. Translating this description to steps, you will have a guideline of how to use the aggregate method to estimate the amortized cost. The first step is to identify, or say consider a sequence of n operations on a data structure. The second step is about analyzing the actual cost of all those operations. So you need to add up the worst case time complexity of each worst operation in that sequence and compute the total cost Tn. The third step is to divide the total actual cost by the number of operations. Let's apply these steps to an example to make sense of the aggregate method further. Let's look at an operation on binary numbers. The operation is named increment. So what does this increment operation do? Given an n-bit binary number initialized as all zeros, this operation flips the rightmost bit by adding a single 1 to that bit. If the rightmost bit is 0, it will be flipped to 1. However, if the rightmost bit is 1, then the incremental operation will not only flip it to 0, but also propagate the carry to the left, which may flip more bits leftward. The number of flips represents the cost of this incremental operation. An example of a 4-bit binary counter looks like this. There are 6 columns in total. The leftmost column represents the decimal number, and its neighbor column represents the corresponding binary number with 4 bits. Bit 0, bit 1, 2, and 3. And in these 4 columns, they represent each individual bit of the corresponding number in the same row. They count from the rightmost to the leftmost. So bit 0 represents the rightmost bit, and bit 3 represents the leftmost bit. The first row is the starting point with all 4 bits as zeros. When the incremental operation adds 1 to the rightmost bit, it will become 1. That will lead to the second row. Now, in the second row, the rightmost bit is 1. If you continue to run the incremental operation, it will flip the rightmost bit, and the carry of 1 will be propagated to the second rightmost bit, and that will lead to row 3. If the incremental operation is run continuously, it will eventually have all the rows that are presented here. As you can see, when the incremental operation is continuously executed, the propagation may lead to different number of flips at each step. The worst case scenario is when all bits are flipped. That happens when you go from the row number 7 to row number 8 in our example. In row number 7, all bits are 1 except for the leftmost one. When the incremental operation is executed, the rightmost bit will flip, and the carry will flip all other bits. That's how you go from the row number 7 to row number 8. In this worst case scenario, the time complexity is big O of n. Remember n here represents the number of total bits. In other cases, the incremental operation takes less and varied time to run. For example, in the case of the first row, the incremental operation takes a single step to run, because it only flips 1 bit. In the case of the second row, the incremental operation takes 2 steps, because it flips 2 bits. If you have a sequence of incremental operations being executed, what's the average case time complexity per operation? If we use the worst case time complexity, I mean the big O of n, it definitely won't represent the cost accurately. That's where the aggregate method comes into play. To apply the aggregate method to this problem, we will follow the 3 established steps. The first step is to identify a sequence of n operations. We have already done that by analyzing that example. Just to clarify a bit, the n operations here, that number n has nothing to do with the n bit. They are 2 totally different numbers. If you think about the example we visited, the bit number can be 4, and the sequence number of the operations can be 8, like this. The second step is to add up all the cost of each operation. We will go with this example here. If we have a 4-bit binary counter and 8 operations, what's the total cost? When we discussed this example, we mentioned that the cost varies across different operations, but we didn't explore the pattern. However, we need to know the pattern of how the cost varies to figure out what they add up to. If you look at the 4 columns, starting from bit 0 and end with bit 3, you will see that the rightmost bit, I mean bit 0, always flips in each incremental operation. Bit 1 only flips for 4 times across the 8 operations. Bit 2 only flips for 2 times, and the leftmost bit, bit 3, only flips for 1 bit. The pattern here is that when you go from the right bit to the left bit, each bit flips half of the time in comparison to its right neighbor. until it gradually becomes 1. So from this example, we can generalize the pattern from 8 operations to n operations, where n is an arbitrarily large number. Like this, given n execution of the increment operation, the rightmost bit flips for n time, and the second bit flips for n divided by 2 times, and the third n divided by 4 times, and so on. So the total number of flips over n operations is the sum of n divided by 2, n divided by 4, then divided by 8, until it gradually becomes 1. The summation term is something that we can work with. We can rewrite the formula, also the term, to extract the n, and the remaining part will look like this. From here, we can express n as 2 power 2k, like this. K here represents the highest bit position. Based on infinite geometric series, this part, in the round bracket, can be estimated to a constant number. So the whole summation term can be estimated to a constant number multiplied by n. As a result, we have the total cost of n operations. The second step is done. The third step is to divide the total cost by the operation numbers, which is n. That will lead to big O of 1. When you use n divided by n, that will give you 1. So, the amortized cost per operation is simply constant time. In this video, we covered when the amortized analysis is essential, and how the aggregate method, as one of the amortized analysis methods, is applied. In the next video, we will cover a different method of the amortized analysis, the accounting method. Some operations feel like they are stealing time from the algorithm, while others feel like they are barely doing anything. What if we could charge each operation a fair price? Even some of them are secretly expensive. That's the idea behind the accounting method in amortized analysis. It's like giving each operation a budget. If you are just joining, this is a part of our deep dive into the amortized analysis. But don't worry, we will start fresh. In this video, we'll walk through the accounting method with a clear example, and see how assigning fake costs can reveal the real performance. So what's the accounting method? Same as other amortized analysis methods, the accounting method aims to provide a more accurate analysis of the cost of a sequence of operations. By saying operation, I mean a function or a method. The idea of the accounting method is about assigning credits to each operation. By doing so, it aims at spreading out costs of the expensive operations over multiple cheaper ones. 3 steps are involved in estimating the amortized cost using the accounting method, including defining a cost scheme, checking validity, and calculating the average cost per operation. Let's look at these steps one after another. The first step is to define a cost scheme. It's about assigning an amortized cost to each type of operations. Yes, there might be more than one type of operations. In this scheme that you develop, you will assign a fixed cost to each type of them to represent their time complexity. After that, you maintain a bank account that is associated with an object of that data structure. When an operation is executed, you will charge the fixed amount corresponding to its operation type. The fixed cost you assign in step 1 might be bigger or smaller than its actual cost. If the fixed cost is bigger, the operation is overcharged, and you will save the difference as credit in your bank account. If the fixed cost is smaller than the actual cost, that means the operation is very costly, so you will need to use the saved credits to compensate the deficit. That's the first step. As you can see, the cost scheme you design is very important for everything that follows up. The second step is to check the validity of the cost scheme you developed. So when a sequence of operations are actually executed, you will start charging each of them based on the scheme you developed in step 1. it will charge the amortized cost of each operation corresponding to its operation type. Given an operation, if the amortized cost is bigger than the actual cost, we would say that the operation is overcharged, and we store the difference as credit in the bank account. If the amortized cost is smaller, we see the operation is too expensive, so we need to withdraw the stored credits to help mitigate the deficit. In the end, you need to make sure that the total amortized costs of this sequence of operations are always bigger than or equal to the total actual cost. Otherwise, you need to go back to step 1 to revise your cost scheme. The third step is to calculate the average cost per operation. Same as other amortized analysis methods, you will do so by dividing the total amortized cost by the number of operations to derive the average cost. To get a better understanding of the 3 steps, let's go through an example together. Let's think about the operations of a stack. A stack is a linear data structure that can be thought as a stack of plates. You will add data one on top of another into a stack. When you remove data from a stack, you will always remove the data that sits on the top first. This is known as first in, first out, and that's an important feature of stacks. It's worth noting that the push operation only adds a single element into a stack, and the pop operation also removes only a single element from a stack. Beyond the 2 types of operations, there's one more that we want to discuss in this example. This operation is called multipop. It aims at removing k elements from a stack. The definition of this operation is shown up here on the screen. This operation takes 2 parameters, a stack and the number k. The while loop has 2 conditions. The first condition checks if the stack is empty or not, and the second condition checks whether k is bigger than 0. Underneath the while loop, this operation keeps taking advantage of the pop operation to remove elements from the stack. The k also gets decremented in every iteration of the while loop. As you can see, the multipop operation will remove at most k elements from a stack. If a stack has fewer than k elements, all of them will be removed. The summary of the 3 operations of stacks is presented in this table. If you focus your attention on the cost column, you can see that the cost, or say the time complexity of both push and pop operations are simply big O of 1. The cost of multipop operation is either the length of the stack or k, whichever is smaller. Based on this summary, you can tell that the worst case time complexity of stack operations is big O of n, where n represents the number of elements in a stack. However, we know that the worst case may not represent the time complexity of a sequence of stack operations accurately. Think about it. The worst case happens when you have a multipop operation whose second argument is n, where n is equal to the stack size. But it has its limit. You can only remove as many elements as you have added using the push operation. When a stack starts as empty, you can't just keep executing the multipop operation without adding any elements first. In other words, the worst case can happen for only a single time, but not always over a sequence of operations. That's why the amortized analysis is needed, and that's where the accounting method can help. To apply the accounting method to this example, we need to follow the 3 steps strictly. The first step is about defining a cost scheme. We already know the actual cost per operation type. Both the push and pop operations take constant time to run, and the multipop operation takes either the same steps as the stack size or the given number k to run, whichever is smaller. It's our turn to assign a fixed amount of cost to each operation type. Considering that the 2 different pop operations can't remove any elements that were not added first by the push operation, so we can assign a bigger cost to the push operation first, and something smaller to both of the pop operations. For example, we can assign the amortized cost of a constant number 2 to the push operation, and both zeros to the two pop operations. How does this work? We can explore that at the validity checking step. If it doesn't work, we will revise this scheme in the future. To check the validity of the scheme we just developed, we can run it against a tangible example. We will start by running a number of push operations first, like this. As we do so, we will keep track of if we are running a deficit or credit for each operation, and maintain a bank account to store all the credits. Because each push operation only takes one step to run, but we charged it 2 instead. So we would get the credit equal to the difference, which is 1, whenever we run the push operation. After running push operations for 6 times, we will be able to accumulate 6 credits in total. After that, we will run the pop operation for 1 time, like this. We know that its actual cost is 1, but we didn't charge anything on it, so we would have a deficit from this operation, which means that we need to withdraw 1 credit from our bank account to pay for it. So the total credit will go from 6 to 5. Next, we will run a multi-pop operation that aims at removing 4 elements from the stack, like this. We didn't charge anything from this operation, but its actual cost is 4, so there's a deficit of 4 that we need to use the credit from our bank account to pay for. That's why the total credit goes from 5 to 1. Next, we will run another multi-pop operation that aims at removing 3 elements from the stack. However, there's only 1 element in the stack now, so this multi-pop operation will only be able to remove 1 element from the stack after all. So the actual cost of this operation is 1. We didn't charge anything for this operation, so the deficit is 1, and it needs to be paid using the credit from our bank account. After the 3 pop operations, all credits have been used, and the stack goes back to empty. From this example, you can see that assigning an amortized cost of 2 to the push operation and 0 to the pop and multi-pop operations clearly works, as the total credit numbers never goes below 0, or say that the total amortized cost is always bigger than or equal to the total actual cost, regardless of whether it's the pop or multi-pop operation. The number of elements that can be removed from a stack is always limited by the number of elements that were added by the push operations. Generalizing this example, you will have this. If a stack starts as an empty one, to add an arbitrary number of n elements into a stack, you will need to run the push operations for n times. The actual cost of that is the same as the element numbers, which is n. It doesn't matter how many pop or multi-pop operations you can run on this stack, they can only remove n elements in total, and the actual cost of that is also n. In combination, the total cost of a sequence of push, pop, and multi-pop operations is 2 multiplied by n. Our cost scheme says that the push operation costs 2, while the 2 other types of pop operations cost nothing, which makes the amortized total cost also 2 multiplied by n. As a result, we can verify that the total amortized cost is bigger than or equal to the total actual cost, so step 2 is finished. The last step, step 3, is about calculating the average cost per operation. This step asks you to divide the total amortized cost by the number of operations, given n elements that are being added and removed from a stack. You need to involve at least n plus 1 operations. Imagine n push operations and 1 multi-pop that removes every element. That's the minimum number of operations. The maximum number of operations is 2 multiplied by n. Imagine n push and n pop operations in combination. Regardless of which extreme scenario you're looking at, the time complexity per operation is always big O of 1, because both cases lead to constant number of steps per operation. In other words, using the accounting method, we are able to verify that the cost per stack operation is a constant number, despite that the multi-pop operation can sometimes be very expensive. In this video, we covered how to use the accounting method to conduct amortized analysis. In the next video, we will cover a different method of the amortized analysis, the potential method. Not all expensive algorithm operations are as bad as they look. Have you ever wondered how dynamic arrays can still claim constant time inserts, even when they occasionally copy everything just to resize? If you are just joining, this is a part of our deep dive into the amortized analysis, but don't worry, we will start from fresh. In this video, we will walk through how to use the potential method to estimate the average cost of a sequence of algorithm operations. So what does a potential method do, and how does that work? This method defines a potential function. You can think of it as a way to measure the stored energy inside the data structure. The key idea is that when we perform expensive operations, they are not always costly on their own. Instead, they are releasing the potential that was built up by earlier and cheaper operations. Using the potential method to estimate the amortized cost involves 4 steps, as you see here on the screen. The first step is to define a potential function. The second step is to compute the amortized cost per operation. The third step is to perform the validity check over n operations. And the last step is to calculate the average cost per operation. Let's go over the details of each of these steps first. The first step is to define a potential function. What exactly is a potential function? Think of it like a way to store energy in a spring. Each time when we do a simple operation, it's like compressing the spring a little bit, storing energy. Later, when we need to do a more expensive operation, we can release that stored energy to help pay for it. In more formal terms, the potential function phi assigns a value, or say a number, to the current state of a data structure. The number represents the potential, or say how much work has been stored up so that we can use it later. The value is 0 at the very start, I mean the initial state, and will always be bigger than or equal to 0 as the state evolves, because it represents a potential. In physics, if you think about the kinetic energy, there's no such a thing as a negative potential. That said, if you come up with a potential function that sometimes generates a negative value, you will know that it needs to be updated. The second step is to compute the amortized cost per operation. If you know other amortized analysis methods, this may sound very strange because it may not be possible. However, using the potential method, this is something that you can do. How do you do that exactly? Think about you have a number of operations. The number is I. After operation I, we are looking at 2 things. The actual cost of that operation, or say how much work it really did, and the change in potential, or say how much the stored energy increased or decreased between the last and the current operations. To get the amortized cost, we simply add these 2 things together. The amortized cost after I number of operations is simply the sum of the actual cost of I's operation and the change in potential from the I minus 1's operation to this I's operation. The third step is to perform the validity check over n operations. The goal of this step is to verify that the total amortized cost can serve as an upper bound of the total actual cost. To achieve this, you will use the help from the relationship between the amortized cost and the actual cost per operation by summing up over n operations on both sides of this equation. After that, you can further simplify the computation of the total amortized cost based on the recursive nature of this relationship. The last step is to calculate the average cost per operation based on step 3 by dividing the total amortized cost by n. In case if you wonder what the difference between step 2 and 4, they are about the same, or say they are the same for nearly all the cases, and the difference is trivial and it doesn't affect the final result. An advantage of the potential method is that if you have a valid and working potential function, you can immediately deduce the amortized cost per operation. Going through steps 3 and 4 will make the process more robust and free of mistakes. Let's apply the 4 steps to an example to get a better understanding of how things work. We will go through an example focusing on the insertion operation of dynamic arrays. The array size starts as 1, and we will keep executing the insertion operation, which has 1 element to the array at a time. When the array is full, the insertion operation needs to do some extra work before adding a new element, which includes creating a new array that doubles the size of the original array, copying and pasting all the existing elements into this new array. And the new array will replace the old one as the new data storage. As you can see, the worst-case scenario of the insertion operation may not be representative of a sequence of them, so amortized analysis is needed. To apply the potential method to analyze the insertion operation, we will follow the 4 steps. We will start with a potential function. For example, we can use a simple linear function to compute the potential like this one, where n represents the number of elements in an array, and c represents the capacity of the array. The potential at the current state can be computed as 2 multiplied by n minus c. The initial potential when the array is empty is 0, of course. After the first insertion operation, n, the number of elements, becomes 1, while c, the capacity of the array, stays as 1. So it computes as 2 multiplied by 1 minus 1, that will give you 1. Resizing happens when you go from row 2 to 3, and from row 4 to row 5. In both cases, the potential computation doesn't go negative. The same can be said for all other rows. As you see from this example, the potential function always computes to a non-negative number. As the state evolves, the number of elements n can only be as big as the array capacity c, and that's when the difference between n and c is the smallest. After each resizing, n is 1 number bigger than c divided by 2, and that's when the difference between n and c is the biggest. As such, the potential function always leads to non-negative numbers, which means that the function is usable. Which also means that we can move to step 2 to compute the amortized cost per operation. In case you forget, we followed this formula to calculate the amortized cost per operation. We need to know 2 things: the actual cost and the change in potential. However, depending on the actual case, the actual cost of the insertion operation is different. Let's look at a case where there's plenty of spaces in the array, or say when no resizing is needed. In this case, the actual cost of inserting a new element into the array is simply 1. The capacity of the array, represented by c in the potential function, will stay the same, as no resizing happens. As such, we can compute the potential of the 2 neighboring states, like between n and n plus 1 operations. The potential after n plus 1 operations will simply be 2 multiplied by n plus 1, and then minus c. The n plus 1 here represents the number of elements after n plus 1 operations. Similarly, the potential after n operations will be 2 multiplied by n minus c, where n represents the number of elements after n insertion operations. So the change of potential between the 2 states is simply 2, a constant number. As a result, we can compute the amortized cost after n plus 1 operations, which is simply 1 plus 2. That gives you 3. The 1 here represents the actual cost of inserting an element when no resizing is needed, and the 2 comes from or above calculation on the change of potential. As a result, the amortized cost per operation under this scenario is bound by a constant number 3. Now let's look at the other scenario when resizing happens. Let's think about when the number of elements is n, same as the array capacity. When the insertion operation is executed now, it will lead to the array doubling its size. After copying and pasting all the existing n elements, the new element is added. So the new number of elements becomes n plus 1, which is also the actual cost. We can use a potential function to compute the potential after n insertion operations and n plus 1 insertion operations separately. After n plus 1 operations, the potential is calculated as 2 multiplied by n plus 1. After that, you would subtract 2 multiplied by n from it. The result is 2. The n plus 1 here represents the current number of elements in the array, and 2 multiplied by n represents the current capacity of the array. Remember, the array has already doubled its size by this time of point. After n operations, the potential is calculated as 2 multiplied by n minus n, where n represents both the number of elements and the size of the array. Remember, this is the time of point when the array is fully occupied. So the change in potential is calculated as 2 minus n. And the amortized cost after n plus 1 insertion operations is simply the sum between n plus 1 and the change of potential. The n plus 1 here represents the actual cost, where you copy and paste all the existing elements. After that, you add a new element. That's why it's n plus 1. The change of potential comes from or above calculation, 2 minus n. As you can see, the amortized cost when resizing happens is also bound by a constant number 3. That said, in both cases, a constant number bounds the amortized cost per operation. You may stop here and conclude that the amortized cost per operation is simply big O of 1. But it's better that you move to the next steps to verify that the total amortized cost always bounds the total actual cost. Let's do that. Step 3 is actually very much self-telling. We have this formula, a relationship between the total amortized cost and the total actual cost. The potential after an operation is a number bigger than or equal to 0, and the potential at the beginning when the array size is 0, and there is no element at all is simply 0. As such, the total amortized cost bounds the total actual cost. The verification is successful, so let's move to calculate the average amortized cost per operation. If you don't want to do that, you can simply stick to the result you have gained from step 2. If you want to go over step 4, it simply takes dividing n on both sides of the equation. Regardless of the resizing and copying and pasting all the elements, the total actual cost can be estimated to linear time. The same can be said for the potential change between the state after n operations and the initial state. From the 4-step amortized analysis using the potential method, we can see that, on average, the insertion operation runs on constant time. In this video, we learned about the potential method and explored how it can be applied to amortized analysis using an example. That's everything about this series on amortized analysis. Hope you learned something new.